second day of this 2024. So it's my pleasure to introduce Gauri Joshi, who is an associate professor at Carnegie Mellon University in the Electrical and Computer Engineering department, with I think courtesy appointment in robotics and machine learning. So Gauri did her PhD at MIT and then worked as a researcher for IBM TJ Watson before joining Carnegie Mellon. And I've known her for a very long time, and she's kind of very well known in the area of federated learning, where she has done like very fundamental contributions in understanding sort of the theory, but also the practice of how one can learn at very large scale in a distributed and heterogeneous way. So I'm very curious to see what she's going to talk about today.
Thank you very much, Dan, for the generous introduction, and thanks to the organizers for inviting me. This is my first time at the DISC conference. I'm excited to be here to talk about my work on federated learning. Let me adjust the mic. I think, can everybody hear me fine? All right. Yeah, my volume is pretty high, so it should be good. Right. So this talk is going to be about federated learning in the presence of heterogeneity. And I'm going to talk about 3 different types of heterogeneity: data, communication, and computational heterogeneity. So I'll first briefly introduce what is federated learning for those who may not be familiar, and then go into one work in a little more detail in each of these 3 parts of the talk. So this is all joint work, which is led by my amazing PhD students and along with collaborators at IBM, Google, Princeton, and others. So with that, let me get started to talk about why federated learning started as a field. So if you think about how training of machine learning models is done in state-of-the-art implementations today, it is mostly all done in cloud data centers. So typically you have a training data set which has n data points, and that induces an objective function like this, which is the empirical risk loss function over that data set. Since this data set is really large, training is typically done in a distributed setting. So the data set is shuffled and then split evenly across different worker nodes in the cloud. And then there is a parameter server which coordinates with all of these worker nodes. So it sends the current version of the model, which is represented by X here. It sends that to all the workers, which then compute gradients on their local data and send these back to the parameter server. And then the parameter server aggregates them and updates the model using a stochastic gradient descent update rule. So that's the general setup. And as you can see, this framework is synchronous. And it requires constant coordination between the parameter server and the workers. So there is a lot of room to improve the scalability of it. And there are several works on this in the distributed machine learning community that propose solutions such as asynchronous aggregation, or doing more local update at these workers, or overlapping communication and computation. So that's all very interesting work done in distributed ML community, some of which can also be applied in the federated setting. So this framework, although it's really successful for cloud-based training, it has a few limitations that prevent it from being applied to many modern applications. And that is because these worker nodes are typically homogeneous and available throughout training. And more importantly, this framework needs to have a centrally available data set, which can be shuffled and then partitioned across these worker nodes. And these assumptions do not hold in many modern applications where a lot of data collection is done at the edge. So nowadays, a lot of data is being generated on cell phones, IoT sensors, tablets, etc. And all these data can be used to train really informative machine learning models. So, for instance, on our cell phones, we all have some next word prediction service, which uses a language model. And then the training data for that language model would be whatever we type on our phone. So if we want to use standard machine learning training paradigms, we would have to send all that data to the cloud, which can be expensive and slow, especially because these devices are resource and bandwidth limited. And also, there are privacy laws that forbid sharing of data with foreign cloud servers. So, due to this, it's hard to apply the standard machine learning paradigm to such edge-based data collection. So this is where the area of federated learning came in. So federated learning was designed to operate within these constraints. And the key rule in federated learning is that data stays on the edge device, and instead model training is moved to the edge. So what happens in federated learning is that you have these edge devices, which have their own data sets that are collected from the user who's using that device. And then you have a central server in the cloud, which sends the current model to these devices. And then these devices do some local model training for a few rounds. And then the resulting models are aggregated by the central server. So this is how federated training generally works. And because this communication link only involves sharing model updates or gradients and not the data, it has better privacy guarantees and better communication efficiency than sending all the data to the cloud. So that's the basic idea. Now, let me introduce a little more notation, which I'll use in the rest of the talk to make things clear. So what we are going to consider is a system of M of these edge clients. And each client has a data set DI that induces a local objective function at that client. Okay, so Fi is the local objective function at the ith client. And then the global objective, f of x, is a weighted average of these local objectives. And the weights are proportional to the size of the data set at that client. So these weights Pi are chosen in this way because the global objective kind of wants to emulate where a scenario where hypothetically, if you had sent all the data to the cloud, then this would be the objective function at the cloud server. So this is the objective function, and our goal is to train a model X that minimizes this global objective. So for the purpose of this talk, I'm going to assume that we are going to train a single model, which will then be used by all the clients. But there are variants of this goal, such as in personalized federated learning, where you might want to train a one model and then fine tune it at different clients, or train multiple models to begin with. But here I'm going to focus on just having one single model. So that is the setup. And the algorithm, which I briefly alluded to earlier, is called federated averaging. In this algorithm, each client does tau local gradient steps before sharing their resulting model with the server. So the algorithm is divided into what are called communication rounds or training rounds. And in every round, the current model is sent to these clients, and then they perform these tau local SGD steps. And they will end up with different versions of the model because their local data sets are different. And then these models are then aggregated by the central server using this update rule, where eta g is called the global learning rate. These clients, they use a local learning rate, which can be different than the global learning rate. So this is the basic algorithm. And what we have been talking about here is in a centralized setting. But there are also applications where it might not be good to have a single point of failure, the central server, and or there might be privacy or trust constraints where these devices would rather collaborate directly with each other. So there are also a set of works in federated learning that consider this kind of arbitrary network topology connecting these clients without a central server, where each client can do local updates and then average its model with its neighbors. So what I'm going to do in this talk is consider the effect of heterogeneity and how it affects these federated learning systems. And what do I mean by heterogeneity? So if you look at this picture and the algorithm that I described, it might seem very similar to the parameter server setting. So you might think, what is the difference really here? But the difference really comes from the heterogeneity in the system, which allows it to scale to maybe thousands or even millions of these edge devices. So there are several sources of heterogeneity. Let me talk about a few of them. One of them is data heterogeneity. So as I said before, since these local objective functions are induced by different data sets collected by the clients independently, these are inherently heterogeneous. And because of that, as these clients do more and more local steps of training, their models can drift away from each other. And this causes some issues in conversions that a lot of works have tried to tackle in the past few years. So that is data heterogeneity. The second source of heterogeneity is communication heterogeneity. So since there are a large number of these devices, they do not all participate in every communication round. So at any point of time in this algorithm, only a small subset of these devices will actually be available to do the training. And that set can change from one round to the other. So this kind of stochasticity or partial participation can lead to some additional errors in conversions, which need to be tackled from an optimization perspective or through client selection. I also mentioned the decentralized setting. So in the decentralized setting also there is inherently heterogeneity that's coming from how the network is connected between these nodes. So some nodes can have higher degree, some nodes can have lower degree, which leads to different rates at which they will their models will mix with the rest of the models in the network. And finally, there's computational heterogeneity as well. So these devices may have different computation speeds or different memory, and they might even use different learning rates or adaptive local optimizers that cause the amount of progress in training at each device to be different. And when we aggregate such heterogeneously trained models, we need to make sure that the aggregation is consistent with the global objective. Right? So these are some sources of heterogeneity. And what we are going to do here is to understand how these affect the conversions of the federated averaging algorithm that I introduced and design some optimization techniques to improve that conversions. So that is the plan. I can take short questions after every part of the talk. If you have any questions, feel free to stop me. Yes.
Is there any concern that some of the devices would send adversarial or incorrect gradings?
Yes, so that is a concern in federated learning. Devices can send adversarial gradients and poison the model. I'm not going to mention about that here, but there are a lot of works in that setting as well. So let me start by talking about data heterogeneity. As I said, the problem comes from the fact that you have these local objectives that are different, and then as clients do more updates, their models drift away from each other. So to understand it in more detail and more specifically, how does the number of local steps affect the conversions? Let us look at a simple toy example with just 2 clients. And we'll look at 2 extreme cases where tau equal to 1 or a large tau and see how the algorithm's solution is affected by tau. So if you just have one local update at each client, and let's say there are 2 clients and their local minimas are x1 star and x2 star respectively, and the global minimum, which is the minimum of the average of these local objectives, is x star. So if we start with a global model, which is shown here, and each client does one local update and then we average the models, then you can see that the global model is updated according to this trajectory shown by the dotted blue lines. And then the direction of that dotted blue line ends up being consistent with the average of these local gradients, and it is consistent with the gradient of the global objective function. So that's because the global objective function is just a weighted average of these local objectives. So because of that, tau equal to 1 is not a problem in terms of data heterogeneity, because the global model makes steady progress towards the global optimum, which is x star in this example. But what happens if these clients do a lot of local updates? Let's look at that in this picture. If you have the global model and then each client does many local updates, then each client's model will end up close to their own local minima. And when you average these, you get this global model. And it might seem like we made a lot of progress in just one round of training here. The global model went from here to here. But the issue is that it does not progress further very well. If you do another round of local updates, then again, these models will go back towards these local optima. And when you average, you get stuck at this point, which is mismatching with the global optimum x star. So what federated averaging does is it doesn't operate at either of these, it's somewhere in between. It does a moderate number of local updates tau, and then averages the model, and then again does local updates. So what we can show is that if your tau, the number of local updates is small enough, or these local learning rates are small enough, then federated averaging can still converge to the global optimum. It's just that this heterogeneity that is due to the multiple local updates and different objective functions adds to some error in the solution. So I hope that gives you a good idea of how tau affects convergence. Now let me show some theoretical convergence bounds that quantify this more concretely. So these bounds are under standard assumptions like Lipschitz smoothness of these local objective functions, assuming that these local stochastic gradients that are used for these local updates are unbiased and have bounded variance sigma square. And then there is also a bound on how different these objectives can be from each other. So there's a bound on how much the local gradient differs from the global gradient, and that is bounded by sigma g square. So the sigma g square is the measure of heterogeneity of data. So with these assumptions, the error after, say, T communication rounds of federated averaging looks something like this. So you don't have to look at all of the terms here in detail, but at a high level, what is happening here is that these first 2 terms come from the error due to stochastic gradients and the local updates that are done at each client. And this third term is due to data heterogeneity. So you can see that sigma g square, that data heterogeneity bound, is appearing in this term, and this term is growing also with tau, which is the number of local updates, which magnifies the effect of data heterogeneity. So there's a lot of work in federated learning literature trying to address this client drift error term and trying to reduce it or eliminate it completely. So I'll mention a few of them here. One simple idea is to just set a small local learning rate. So this naturally will stop these client models from drifting away from each other. And the way to do that is you set the local learning rate like this and the global learning rate like that. And then that reduces this error bound to something like that, where the first term here is again the stochastic gradient error term, and this is the dominant term in terms of the scaling with the number of communication rounds T. And the second term is this client drift error term, which is now not the dominant term. It decays faster because we chose the learning rate to be small enough. So this is one way of addressing that issue of client drift. Another way, say if you don't want to slow down the local progress by setting a small learning rate, is to adapt the number of local updates. So if we look at that bound again, which I showed a couple of slides ago, the first term here decreases with tau, whereas these terms increase with tau. So there's a trade-off here in terms of tau. If you look at it in terms of a picture where you plot the training loss versus the number of communication rounds, at the beginning, a large tau is good because you get this fast drop. But then later on, large tau is not good because it leads to this error floor at the time of conversions. So what we can do is we can adapt tau and start off with a large value and gradually decrease it, and also adapt it to a learning rate schedule that may already exist in the system. So this is what one of our works few years ago proposed. So this is another idea to address client drift. But there are also a few more solutions. So another solution which is very popular is called FedProx, where we add to each local objective a proximal term like this, which penalizes the distance between the global model and these local models. So in terms of how the algorithm will work is that you start off from the global model, you do local update, and then these updated models are pulled back towards the global model to stop client drift. And then this continues. After this, you'll average and update the global model. So this is also another way of addressing client drift. One more approach is that these correction terms are computed by exchanging what are called control variates with the server. So these correction terms are designed to reduce the variance in these updates and effectively eliminate the data heterogeneity in the system. So this is proposed in another work called Scaffold a few years ago. So all of these methods, they are helpful in mitigating client drift, but a common pattern in them is that they slow down the local model progress in different ways. Of server learning rate. So the default is 1, but the theoretical results in some of these works suggest that you need to choose an even larger server learning rate in order to compensate for these local slowdown in the progress. But the issue is that if you set a very large server learning rate, it does not work very well in practice. So an example is shown in this picture where the numbers are test accuracies, where higher is better. As per the theory, you would operate in this bottom left corner where the client step size or client learning rate is really small and the server step size is large. But what ends up working well in practice is a moderate client learning rate and a server learning rate, which is just the default of 1 as in Fed averaging. So to address this issue and to avoid slowdown, one of my students, he proposed this method called FedEXP, which adapts the server learning rate according to the heterogeneity in client updates, and it lets the local optimization procedure be chosen freely. So by default, it can be just regular federated averaging or FedProx or any of these other algorithms. So let me mention about that in a little more detail in the coming slides. What is this adaptive server learning rate schedule? So this is inspired from an over-parameterized convex regime. So what we suppose these local objective functions that I have are convex, and they are over-parameterized, which means that there is a relatively large set of local minimum that optimize that objective function. So S1 star and S2 star can denote the solution sets of these local objectives. And the global minimum lies in the intersection of these sets. So then our problem of finding a global model or training a global model reduces to finding a point in the intersection of these convex sets. And there is an existing algorithm to do that, which is the projection on convex sets algorithm, proposed in 1967. What it does is it starts off from some point and then takes a projection of it on each of these sets and then averages the projection. And how much you move towards the average of these projections is controlled by the parameter lambda, which is also called the relaxation coefficient. By default, lambda is 1, but a follow-up to this is the extrapolated parallel projection method, or EPPM, which is the same as POCS, but it adapts this lambda in every iteration. So what it proposes is that lambda should be set like this, and by Jensen's inequality, this lambda will always be greater than or equal to 1. So intuitively, what this is doing is that if these projections are more asymmetric, then this lambda will be larger. Otherwise, it will take a small value. So how does this apply to our federated learning problem? Because we don't have convex objectives, we don't have exact projection operators there, but we do have something close. So we have local updates that are being done to the global model, and these local updates can be thought of as an approximate projection on these local objective function solution sets. And our global learning rate is playing the same role as the lambda in these algorithms. So what we did in this work is use the same learning rate schedule that was proposed in this EPPM method and applying it to the global learning rate in Fed averaging. So more concretely, this is the learning rate that we propose. It looks very similar to that lambda expression that I showed a couple of slides ago, with a couple of practical modifications. One is we need to add a constant to the denominator to prevent this from blowing up. And secondly, we have this max of this expression and 1, which ensures that this learning rate doesn't end up too small, and it is at least as fast as vanilla federated averaging. So this is the proposed learning rate schedule at the server. And let me show you some convergence guarantees and some experimental results to understand how this works in practice. So convergence guarantees for L-smooth objectives with bounded gradient dissimilarity and with full batch gradient descent at clients, the vanilla federated averaging algorithm, which has a default server learning rate of 1, has this convergence bound. What fedexp gives is something like this. So it looks similar. Some differences are that here in the denominator, you have this summation of the global step sizes, which are all larger than 1. So because of that, this term decays faster. Not order wise, but like in terms of constant, it is faster. However, that speed up comes at the cost of this additional error term, which depends on the data heterogeneity parameter. But this additional error term can be controlled by choosing a small enough client learning rate. So these are the convergence guarantees. And if we look at the experimental results, which compare this method with existing methods like the standard federated averaging and scaffold and ADAGRAD, etc. And in this table, what we are showing is the number of communication rounds that we need to reach a target accuracy. So we can see that fedexp requires these many communication rounds for the different data sets. And the other methods require 1.5x or 2x more rounds on average. And the plots here show that the trajectory of followed by test accuracy versus training rounds, which also is better in fedexp. So again, I want to mention that this method is only changing the global aggregation, so it can be combined with any of these local optimization techniques. So that was one example of a work on data heterogeneity. So what we covered so far is that data heterogeneity is caused by having a number of local updates greater than 1, and the fact that these data sets are heterogeneous. And some ways that we looked at to address it include local correction and then adaptive global aggregation. Let me take questions here. Yeah, so it's like a stationary point of that objective. So for non-convex objective functions, many of these bounds, they can only show conversions to a stationary point of the objective. Any questions before I go on to the next part?
Regarding data heterogeneity, you don't seem to use information in every client about the data distribution that they have loaded. Could that be used?
So it's indirectly used because these clients are doing local updates. So the models that they will send back will capture the local data distribution. But we don't explicitly share that because of privacy reasons. So indirectly, it is captured in the models.
What I mean is like they have different data sizes, they have different distributions over like I don't know, classification data set, with the different labels. That is you're assuming that is not revealed in any form because that's like a privacy.
Yes. So that distribution, it can be heterogeneous across the clients, as you say, and we don't really have control over that, and it's also not shared with the server directly.
Is there a particular privacy guarantee that this algorithm gives, or is it just that there's some type of implicit privacy because only gradients are shared?
Yes, so you're right. So just this algorithm by itself doesn't have an explicit privacy guarantee because by looking at the gradients or model updates, you can infer the data in some cases. So what is done is the differential privacy is added on top of this generally. So these gradient updates or model updates, you add noise to it, either locally before sending or globally at the time of aggregation in order to get differential privacy guarantees. So let me go on to communication heterogeneity. So here, I mentioned there are two forms. One is in the centralized setting and one is in the decentralized setting. So I'll very briefly talk about the centralized setting in just one slide and then spend more time in the decentralized setting, which I think will be of interest to this community. So in the centralized setting, communication heterogeneity comes from the fact that only a small subset of these clients will participate in every round. And that adds an additional error in the conversion. So in the bound that I showed earlier, we were assuming full client participation. If you have partial client participation, there will be an additional error in that convergence bound. And some ways to overcome that additional error is you could use old updates sent by a client as proxy whenever that client doesn't participate. And this can have a variance reduction effect on the stochasticity in data in client participation. Another approach, which one of my students proposed, is to select clients in a biased way. So instead of choosing clients uniformly at random from the population, if we prefer clients which have higher loss, then that can lead to faster conversions, although it can lead to some added error. So you have to select how much you bias carefully. So these are some ways to address partial participation of clients. Heterogeneity can also present itself in the decentralized setting. So let me talk a little more about this. So heterogeneous connectivity of nodes can lead to a trade-off between conversion speed and communication delay. So if you have a densely connected graph, then the convergence is faster because the models mix at a faster rate. But the communication delay in doing the averaging at every round is more because each node has a higher degree. So what I'm going to talk about is a work to address this trade-off by carefully controlling the frequency with which you communicate on each link of this network, while still keeping the conversion speed the same. So to introduce that, let me first talk about the standard decentralized SGD algorithm, which was proposed in many classic works, starting from 1980s, John Tsitsiklis, and then Osdagler and others. So in this standard decentralized SGD algorithm, you have these nodes that are connected by some topology. And then each node has their own local objective function. And our goal is to minimize the average of these local objectives. So in every round, each node will do a local update according to this stochastic gradient descent update rule. And then it will average the resulting model with its neighbors. The averaging is done according to this equation where the Wij's are the mixing weights, which are the weights given to each of the neighboring models when we average locally at each node. And then these two steps are repeated until convergence or consensus, where after a large enough number of rounds, all these nodes models will converge to the same model. So this is standard decentralized SGD, and there is a lot of work in optimization theory on analyzing the convergence and improving the convergence of this algorithm. However, there's relatively less work on looking at the delay introduced by this averaging in every iteration. So if you look at how much delay is incurred whenever you do consensus, it typically scales according to the degree of a node. So the time it will take to average with neighbors will be proportional to the degree. And then for the whole network, it would be proportional to the max degree. So what we want to do is to reduce this communication delay. So we don't want to incur this much delay. What if we want to reduce it? You can think of some simple ways of reducing that delay. One way is to just average less frequently. So maybe instead of using standard decentralized SGD, I can do more local updates. So at each node, I can do tau local updates without doing any averaging, and then average with neighbors. So this reduces the delay by a factor of tau, and this can save on communication. Another method is to sparsify the graph by activating each link with probability p. So in every iteration, each link has an activation probability, which we can control. And then if you activate the links with this probability, you'll again reduce delay by a factor of p. So these two methods work, but then they introduce a trade-off in terms of the error conversions. So if you look at the training loss versus the number of iterations or rounds of this algorithm, whenever you do infrequent or sparse averaging, the error will be higher at the time of conversions. And the communication delay reduction will benefit if we look at the training loss versus the actual runtime instead of number of iterations. So infrequent or sparse averaging will be really good at the beginning, where you get this fast drop in the training loss, but then later on you are hit with that higher error floor. So what if we can get the best of both worlds? So what we want is ideally low communication delay, but also maintain the error versus iterations conversions that is given by standard decentralized SGD. So that is what this method Matcha does. So it works with any topology. And if you look at the training loss versus wall clock time results that we get, you get a fast drop, but then at the end, you don't get that higher error floor that we saw in the cartoon plot in the previous slide. And this Matcha algorithm has a parameter called the communication budget CB, which we can flexibly control to decide how much we are reducing the communication delay per iteration. And the benefit is that in terms of training loss versus iterations, the error floor does not grow as much. So you can see that if we compare vanilla decentralized SGD and then Matcha with communication budget 0.5, then those two curves actually overlap. So we are getting effectively a free reduction in the communication delay. So how do we achieve this? What is the secret here? The key idea that this algorithm uses is that all the links in the network are not equal. So if you look at this example, some links are more important than others. So the red link here is more important or connectivity critical than the blue link. So what if we communicate more frequently on these connectivity critical links that will ensure fast conversions of error, and we use these other links less frequently that will save our communication delay. So this is the key idea. And the way the algorithm works is that in the first step, what we'll do is we'll take this given network topology and we'll decompose it into subgraphs. And then we'll assign some activation probability to each of these subgraphs. So in every iteration, you'll activate each of the subgraphs with the assigned probability and then perform consensus according to that activated graph. So what is the subgraph decomposition we should use? So if you remember, I said that the delay scales with the node degree. So a naturally good choice for a subgraph is a matching. So matchings have each vertex having at most one edge. So this allows for disjoint links that can communicate in parallel. and the communication delay per iteration is simply proportional to the number of active matchings according to the delay model, which I mentioned a few slides ago. So that's what we are going to do. We are going to decompose the graph into matchings. But then how do we choose these activation probabilities? Oh, before I go there, how do we find the matching? So I think this is well known to the community here that there are polynomial time edge coloring algorithms to find these matchings, and the number of matchings that we get as a result of this is equal to either Dmax or Dmax plus 1. So we can use those standard algorithms to find the matchings. And then how do we decide these activation probabilities for each subgraph? To do that, we'll solve this optimization problem numerically. So what is this optimization problem? The objective is to maximize the algebraic connectivity of the expected graph that we get. So this is the second smallest eigenvalue of the expected Laplacian of the graph. And maximizing this makes sure that the graph is well connected. And then this is done under the constraint that the sum of these activation probabilities is less than some upper bound that we can control by setting this communication budget CB. So this sum of the activation probabilities is just the expected number of active matchings in every iteration, and we want that to be less than some bound. So if we choose CB equal to 1, then this will just reduce to standard decentralized SGD, where you just activate the whole graph in every iteration. But if you choose CB as less than 1, then it will activate only a subset of the links in every iteration. So once we get these activation probabilities, we can generate a sequence of these graphs. And this can be done without runtime overhead, either beforehand or by sharing random seeds such that these nodes can generate the matchings at runtime by without explicitly coordinating with other nodes. So this is the overview of the algorithm. Now let's see how it works by looking at its effect on the delay and the error. So if you look at the effect of this algorithm on the communication time or the delay versus the node degree, then what we can see interestingly is that as compared to vanilla decentralized SGD, which is shown in gray, you get a sharp delay reduction for the higher degree nodes, but not as much for the lower degree nodes, which makes sense intuitively because these higher degree nodes are more likely to have the less connectivity critical or redundant links. So they will experience a larger delay reduction when we set the activation probabilities. In terms of error conversions, maximizing this algebraic connectivity leads to a lower spectral norm of the mixing matrix, which gives faster error conversions. So if we look at that, the spectral norm versus the communication budget, which is this parameter we can control. So lower spectral norm is better here. Vanilla decentralized SGD is at this point. And matcha, if you see, as you decrease the communication budget, there are regimes where the spectral norm can decrease. So we are getting actually communication budget reduction for free effectively in this regime where the spectral norm is the same or lower without increasing the communication cost. So this is why when we saw the experimental results earlier, we get fast conversions without compromising on the error floor. So these are the theoretical bounds, and the experimental results kind of match that. So in these experimental results, you might be wondering, what are these kinks in the graph? So those are points where we decay the learning rate. So there is some existing learning rate schedule that is predetermined, and this algorithm is just operating on top of that. So you can see that in terms of loss versus iterations, matcha is often almost the same or sometimes even better than vanilla decentralized SGD. And in terms of loss versus actual time, rather than just iterations, it is much better. And if we look at the effect of the topology itself, as you have denser topologies, the gain that we get from matcha is even larger because there are more of these redundant links which we can use less frequently and save the communication delay. So this is what I wanted to say about communication heterogeneity. I have, I think, 5 or 10 minutes. So finally, I want to very briefly mention a work on computational heterogeneity, and then I'll just wrap up and take questions. Any questions at this point? Yes. Mhm.
When you activate a link, I think you're activating it as an undirected link or bidirectional link, right? Meaning,
Yes, yes.
could you get further improvement if you activate links unidirectionally?
Yes. So we did not consider that in this work, but that's possible. Like considering a directed graph instead of an indirected graph might give an improvement. Yeah. No other questions. So finally, let's talk about computational heterogeneity. So here, the main issue that we are going to think about is what if these nodes do different numbers of local updates? How should we average the resulting models in order to be consistent with the global objective? So let's again look at a toy example to see what is the effect of these heterogeneous local updates. So if you have, again, 2 clients and then you start off with this global model, and then both the clients do the same number of local updates, then this is the global model that we get, and this trajectory will go towards X star if we choose small enough number of local steps and learning rate. But if you have a heterogeneous setting where, let's say, if the first client consistently does more local updates than the second client, and you still just average these models naively, then the average model will be skewed towards the first client. We will get a bias or a skew in the solution, and it won't match with the global solution that we are looking for. And the main thing to note here is that this kind of a skew cannot be fixed using the techniques that we use to tackle data heterogeneity, because inherently, if one client is faster than the other, by just slowing down the progress locally, we are just going to slow down the whole algorithm. So to understand this, what we did is came up with a generalized update rule, and then we were able to show that in the homogeneous setting, what you are optimizing is the true global objective which you want to optimize. But in this heterogeneous setting, if you just use standard federated averaging, then you are effectively optimizing a different objective where the weights given to these local objectives are proportional to the number of local updates that they are doing. So this is mismatching, as you can see, and what we need to do is fix these aggregation weights.
If one client is actually working much more actively than the other one,
Mhm.
is it clear that the global objective should still be equally weighted all of the clients?
Yes. Right. So I think what you're getting into is like fairness. So here we are still saying that the global objective is weighing them equally or in proportion of data set sizes. Yeah. So you don't want just the fast devices to be given higher weight. So federated averaging actually ends up giving these faster devices a higher weight without intending to do that. So The federated averaging update rule, what it does is that you have these global models, the global model, and once you update, you get these locally updated models. So it's just going to average that. So to fix this mismatch, what FedNova does is that it proposes normalized averaging. So what we do is whenever these local models are updated, you actually normalize these dotted blue lines by the number of local updates that were done. So now you have these green lines, which are the normalized local gradients. And then these are the ones that we'll average in equal proportion or in proportion of the data set sizes to get the averaged model. So this just simply fixing the aggregation weights by doing this kind of normalized averaging, we can make sure that the objective is consistent with the global objective. And what I'm showing here is just like how the number of local updates affect the conversions. We are not talking about different, say, local optimizers or learning rates, but this kind of a normalized averaging technique can also be extended to those scenarios where maybe the number of local updates is the same, but the different clients are using different learning rates. So just by fixing these aggregation weights, experiments show that it gives much faster and consistent conversions. And then since the local optimizer can be chosen freely, by just fixing the aggregation weights, you can get a significant improvement for all different local optimizers like vanilla, SGD, momentum, proximal gradient descent, etc. And to extend this to adaptive local optimizers like ADAM or AdaGrad, it needs a little more work. So we've done that in a different paper, which is cited here. So that's all about computational heterogeneity. So summarizing, the main takeaway that you should remember from my talk is that heterogeneity actually is not bad. It allows the system to be scalable and flexible, but we need to design algorithms that can deal with that in a seamless way for both data, computational, and communication heterogeneity. And then some other directions that I want to mention, I'll be happy to chat about this offline, is allowing model heterogeneity, concept drift, personalized federated learning, fairness, differential privacy, etc. So these are all different directions that people have pursued in the federated learning literature. So there is a lot of work on each of these, but there are still also open problems in these directions. So thank you, everyone. I'll be happy to take questions.
Thanks so much for the talk. Are there any other questions? Eris?
Okay. I think maybe what you're talking about is probably personalized federated learning. So let's say like these clients have different local data sets. So maybe if you consider the example of next word prediction, like when I type on my cell phone, I often type in a language that's not English, but I'm typing in English alphabet. So the predictions are just not good for me. Whereas a native English speaker might get good predictions from that model. So the way the federated learning community generally tackles this is that you still want to have a global model because there can be new clients that come into the system or old clients drop off. So we don't want to just purely have personalized models because the clients also benefit from collaborating with other similar clients. But what is done is that you start from the global model and then fine tune it locally and then use the fine tuned model. So that is what is done in personalized federated learning. By model heterogeneity, I mean the size and the architecture of the model can itself be different. And there are some interesting works that look at
Most-
it. Mhm.
I was wondering if you can have a hierarchy of knowledge or
Yes, so there are some works on hierarchical federated learning as well, because especially in settings like cross silo settings. So let's say you have different companies or institutions like banks or hospitals that have their own devices within the institution and they want to collaborate with others using a federated learning framework. So then locally they can do this in a hierarchical fashion, so each institution trains its own model, and then averages with others, with, with which it might have collaborative agreements. So yes, that can accelerate learning in a way that you can allow more flexibility. So first of all, you can allow heterogeneous local updates at these clients, but you can also do something like asynchronous aggregation. So the algorithm that I mentioned has to wait for all the participating clients to send updates. But if you do this in a hierarchical manner, you might be able to handle asynchrony. So some clients which are slower can just operate at their own speed, and that helps the system be more scalable.
Ceiling for a slow client that maybe it's not bandwidth limited, but it's just a limited.
Yes. So in when I talked about computational heterogeneity, it's sort of like doing work stealing, but it's not really like stealing work from the other client because the data is all local. But the clients that are faster can just do more local updates. So what you can do is fix a time window and let each client do as many local updates as they can, and then aggregate the normalized versions of those updates to get consistent global conversions. There was some
Antonio?
question.
Yeah.
how interesting would you study like dynamic systems in which the set of clients changes over time, the connectivity between clients changes over time? Is that something that has been widely explored or?
Yeah, so that's a really good question. So the set of clients changing over time has been studied, at least for this centralized scenario where just because of limited connectivity. So when this is implemented in practice, devices participate in training only when they're plugged in for charging because it consumes a lot of battery. So because of that, just inherently there's stochasticity in how they participate. So that has been considered, but considering dynamicity in the data is, I think, less explored. So something like concept drift, where the data distributions can change over time and maybe differently at different clients. I think there's a lot of room for work in that area.
So I wanted to end with a question for maybe for people who are interested in reading more. Like, are there any useful kind of introductory texts that you would recommend that people have a look at? Because I mean, as we know, the literature is very vast. So like starting with individual papers is maybe not the easiest thing.
Right. So maybe I actually have some archive links to the papers that I mentioned, but if you're looking for an introductory text, what I would recommend is there is a survey on federated learning, which a lot of us wrote together, like people working in the community, which is available online. But that survey is pretty long. So there is actually a smaller version, which is called a field guide to federated optimization. So if you're interested specifically in the optimization aspects of it, then that is a reference that I would recommend. I also have a monograph, like a short book on distributed machine learning algorithms that are in the data center setting, but a lot of those ideas like local updates, asynchronous SGD can apply to the federated learning setting. So those are some references.
All right. Thanks a lot, and thanks again for your talk.
Thank you.
So we segue directly into a mini session on linearizability. So if you want to know what the latest and greatest on that is, stick around.
Okay, so yes, welcome again to session 6 of DISC. This is again going to be on linearizability, and we have 2 talks in this session. So our first talk is entitled Hyperproperty Preserving Register Specifications. This is actually the co-winner of the Best Paper Award and also the winner of the Best Student Paper Award. So congratulations. And the talk is going to be delivered by Yoav. So take it away.
Thank you. So I'll be presenting the paper Hyperproperty Preserving Register Specifications. This is joint work with Ori Lav and Sharon Shoam from Tel Aviv University. Okay, so let's first present the general setting. We have some client program, usually some distributed protocol or some concurrent algorithm with multiple threads, which are interacting with some shared object. Okay, so this can be any data structure that they're all using, and they're interacting it with via invocations of methods, and they get responses for these invocations. And I want to know whether the client program satisfies some property when interacting with this specific shared object. And the way that I want to do it is to instead look at the program when it is using some specification, which is simpler, which is described in a more abstract, high level, and hopefully have some theorem that says that if the program satisfies the property when it's using this specification, then it implies that the property also holds if I replace the specification with the actual implementation. And the hope is that verifying the property when using the specification will be easier because, again, the specification is described in a higher level. And we also call this specification a reference implementation because it is, like the implementation, it is a piece of code describing how the methods are implemented, but is, again, described in a more abstract way. Okay. So one established result for this setting is that if the property I care about is a trace property, it's a property that you can check for individual executions of this system. So for example, that some bed state is not reachable, and you know that your implementation is linearizable, then it's enough to use an atomic specification where each method happens in a single atomic step. But it is also it's also known that this does not work for hyperproperties. Okay, so I will show this by an example. Okay, so let's say we have a program that is using a shared register. Okay, so this is the program with two threads executing code, and they interact with a register object via read and write methods. Okay, in this specific example, I have one writer and one reader, and they also have access to random coin tosses. And the property I care about, which is the hyper property, is that the probability that the value of A and B are equal is exactly 1/2. And what do I mean by that? I mean that it solves for any strong adversary that controls the scheduling. It can see the coin toss results and decide the thread scheduling based on the coin toss results, and decide any other non-determinism in the system. And here I have the program interacting with an atomic implementation of the register, where the write just stores its value in a shared memory location X, and the read loads the value from this memory location and returns it. And the property holds here, okay? Because, well, if the read happens before the coin toss, I have no chance to make them correlate. And once the coin is tossed, there is only a single value that can be read from the register. So with probability half, I will read the other value. And now let's see what happens when instead of this atomic specification, I'm interacting with a different implementation of a register. So in this implementation, the write is still atomic. It happens in a single step. But the read loads from the shared memory 2 times, and then decides non-deterministically which of the loaded values it returns. So this implementation is linearizable, but the property is not satisfied here. So essentially what I can do is I can schedule the thread so that the two loads load the two different written values by the other thread. And then I can schedule the coin toss, and again, the adversary controls the non-determinism, so it can ensure that the value that is returned correlates with the coin toss. So this shows that the hyperproperty that held when I use the atomic specification is not preserved when I switch it with an implementation that is linearizable. And more generally, the issue here is this: if I want this setup to work, what I actually need is strong linearizability. And the double load register, the register I just showed, which loads twice, is not strongly linearizable. So this strong linearizability is a stronger condition, which does guarantee that I can use an atomic specification, but this specific implementation does not satisfy it. Okay, so why not just always use strongly linearizable implementations? So the issue is that there are many impossibility results. Okay, so one example is that if I want to have the crash resilient, log-free message passing implementation of a register, then there is no way to implement it that is strongly linearizable. In particular, there is ABD, which is a well-known implementation which has all of these properties, is not strongly linearizable. And the problem I have now is that I still want to know what hyperproperties, what probabilistic guarantees I have for clients that use it in distributed settings. They use the ABD implementation to implement a shared register, and I want to know what hyperproperties I can get. So what are our contributions? So in the paper, and we present shared memory register specifications that enable this reasoning about hyperproperties for clients that use non-strongly linearizable implementation. Okay, and more than just build specifications for specific implementations, we actually show they are complete in a sense I will explain later, but essentially it means that entire classes of implementations that satisfy certain vulnerability criteria that are weaker than strong vulnerability can be reasoned about using these specifications. And the two main examples are right strong linearizability and decisive linearizability, which is a novel linearizability criterion that we define in the paper. Okay, so before to explain this notion of completeness that we define, that we present in the paper, I first need to mention a recent result that relates this preservation of hyperproperties to forward simulation. Okay, so forward simulation is essentially a pre-order on implementations, and it is equivalent to having this preservation of hyperproperties for every client program. So what this means is that I can focus on the implementations themselves, and if I establish this simulation pre-order between them, I can conclude that I have this preservation of hyperproperties for any client that is using this implementation. It means I can focus on the implementations themselves and forget for a minute about the clients using them. So using this, we can define a complete implementation. So if I have some class of implementation C, and the terminology here is inspired by complexity theory, but instead of reductions, I have this simulation. So I say that an implementation is C hard if it's bigger with respect to simulation than any other implementation in the class. And I say it is complete if it also belongs to the class. So, for example, we can restate what I showed in the previous slides and say that the atomic implementation is complete for the class of strongly linearizable implementations, okay? Because, as I said, you can argue about hyperproperties for the class using it. And to reformulate our problem, what we want to do is devise simple complete implementations for other linearizability classes that are not strong. And I want to emphasize the word simple because we do have a general construction which gives a complete implementation, but you want also implementation that is useful, that you can hopefully argue about the hyperproperties you gain when you're using this complete implementation in a way that is easier than using the actual implementation you care about. So the specification, the complete implementation is a specification, it should be simpler. And we are focusing on registers specifically. For right strong linearizability is a linearizability criteria. It's a weakening of strong linearizability that is specific for registers that was recently proposed. It includes any single writer register, and specifically the single writer of ABD is in this class. And we show in the paper that this, what we call the right strong register, is complete for this class. So what this implementation does, the write is atomic, and the read, it's essentially an extension of the implementation that loaded twice. This read can load an unbounded number of times as long as new values are loaded. And then it non-deterministically picks some value that it loaded and returns it as the return value of the read. And it captures the hyperproperties of singular writer ABD. And if I want to know some probabilistic behavior of single writer ABD, instead of thinking directly about how it behaves, I can instead imagine that I'm using this implementation, which is shared memory versus message passing. So maybe it's easier to argue about it in some cases. But I'm still left with other implementations I care about. So for example, multi-writer ABD and other multi-writer implementations that are not write strong. So for that, let's see another example of what are the difficulties when you have multiple writers. So in this client program, again, I have two threads using reads and writes. They're also using a barrier method. It's a synchronization method which ensures both threads reach that point in their execution before any of them can continue. So even though the read here happens completely after everything else is done, when I'm using multi-writer ABD, an adversary can force an equality between the read and the coin toss, which might be undesirable if the coin toss is private, right? But instead of getting into the details of ABD, let's see a shared memory implementation which captures the same behavior. So we call this the try not to store register. So here the read is atomic, and the write is the more complicated method. So what happens here is that when you invoke the write method, it loads from the shared memory the current value 2 times. And the idea is that if the two values are different, it means there was some other write that concurrently updated the shared memory. And it means this write can pretend that it wrote its value and then was overwritten. So it doesn't really have to write its value because it can pretend that it did this earlier and then was overwritten by a concurrent write. So he has this, it has this option to not store its value if it recognizes that some write happened concurrently. And the way an adversary can exploit it, it can ensure that 2 different values are loaded and then schedule the coin toss and based on the result decide whether to write the value or not write it. Yeah, so in the paper we present a specification that can be used to argue about multi-writer ABD. It's not exactly the try not to store implementation, but it essentially combines the repeated loads from the write strong implementation and the idea of writes that can choose to be overwritten from what I just showed. It's not exactly just combining these 2 implementations. There are some modifications. So essentially we use version numbers instead of looking at the actual value changes because we don't want data dependencies. If some write wrote a value that was already in the register, we still want to recognize it. So we employ version numbering. We also need to communicate when writes decide to be overwritten by the other writes, we still need to communicate their existence to concurrent reads to capture all behaviors of ABD, for example. So you can see all the details in the paper. And next I will present a new linearizability criteria, which we call decisive linearizability. And it is a class of linearizable implementations. It contains multi-writer ABD. And this implementation that we give is complete for this class. So what is decisive linearizability? So first I need to explain regular linearizability. So let's say that I have some execution, E. It's described it via intervals between an invocation and response of the methods invoked by the threads. And I say that it is linearized by a sequential history S. Okay, so in a sequential history, all the methods happen in sequence with no concurrency. And it is a linearization if I get it by sometimes deleting methods that didn't respond yet, and then ordering the method in the other method in some order which respects responses and invocations that are completely separate. So if the purple and the yellow methods have some overlap, I can order them any way I want, but if they don't have overlap, I need to respect their ordering. So another way to say it is to say that implementation is linearizable if I have a mapping which takes any execution to a linearization of that execution. And it is strongly linearizable if additionally I have the guarantee that if some execution 1 is a prefix of execution 2, then the linearization of the first execution is also a prefix of the linearization of the second execution. So usually people think of it as like the online version of linearizability. At each point of the execution, you need to have some linearization, and it needs to be good for any continuation past that point. You commit on this linearization, and any continuation is gives you a continuation of the linearization. So decisive linearizability is in between these two linearizability conditions. I weaken the prefix requirement, and I just require that if E1 is a prefix of E2, then the linearization of E1 is a subsequence of the linearization of E2, okay? So, for example, if I have a mapping which takes the execution here to this linearization, and then I look at an extension where the green method responds, and so I have several ways to linearize it, possibly. So the first way is just to add the green method to the end of the linearization, and this will give me a strong linearization mapping. Another thing I can do is to put the green method between the purple and the yellow methods, and this will not be strong because I don't have this prefix condition, but it will still be decisive. So what you can imagine here with the previous examples is that the green method is a right that decided that recognized that the yellow method also wrote a value concurrently, and then decided that it was actually linearized before it, that it was overwritten. So it can make this decision for a decisive linearization and put itself between the methods that were already linearized. And what you can't have in decisive linearizability is the third option, where given this bigger execution, I also switch the order between the operations that I already linearized for the shorter execution. So this is where the word decisive comes from, because once the ordering is decided between some operations, I keep this ordering between them. I maybe had some operations in between, but the relative order is kept. Okay, so to conclude, we provide in the paper simple shared memory register specifications, the write strong register, which I showed, and the decisive register, which you can see in the paper. So the write strong register can be used to study hyperproperties of single writer ABD. The decisive register can be used for multi-writer ABD. And we also have a general construction for a range of linearizability criteria. And this enables reasoning about hyperproperties of clients that use implementations from these several linearizability criteria beyond the strong linearizability. And specifically, we present the notion of decisive linearizability. And while we focused on registers in this paper, this criteria is defined in a way that it's not specific to registers and can be studied for other more complicated shared objects like stacks or queues, which we hope is interesting in future work. Yeah, and that's it.
Okay, thank you very much, Yoav. Are there any questions? Yes.
Yeah, so that's a good question. We don't have a composability proof in the paper, but we do think we have a sketch for it. We are currently working on it, but we do believe it's composable. It just we don't show it in the paper. I have a proof sketch if you're interested, but we do believe it is composable. Yeah.
Any other questions? Yes.
Snapshots, yeah. So I looked a little into snapshots, and it seems like it should be transferable. It is not completely obvious, but it seems like it should be transferable. Actually, for the write strong register, It was motivated by something simpler. From one of the papers I mentioned in the slides, there is a suggested implementation of a snapshot where it's a specification of a snapshot where you just take multiple snapshots and capture some non-strong linearizable snapshots. So we do believe you can show similar things for snapshots.
Yes.
Is there a simple interpretation of when I would need decisive linearizability? For instance, if I need to preserve trace properties, then I'm okay with linearizability. If I need to preserve hyperproperties or unparalleled distribution, strong linearizability, when would I use decisive linearizability?
Yeah, okay. So if you still care about hyperproperties, so like you said, you would want to use strong linearizability, but sometimes you just can't because in the specific setup, there are impossibility results. Yes, if you're in a message passing system and you need some progress guarantees usually, so you just can't use strong linearizability. It would be nice to use strong linearizability because then you can use the atomic specification, which is the simplest specification you can think of. So decisive linearizability is hopefully something you can obtain. It is not impossible. The price you pay is that the specification is less simple. Yeah, it is still relatively simple, but it's not like the simplest you can have, which is atomic. But it still gives you the same hyperproperties that you would get if you did establish strong linearizability, if you could. So the set of properties you can look at is still hyperproperties of the same kind with strong adversaries. It's just that the specification that you use is more complicated. But it allows you to argue about these hyperproperties in cases where strong linearizability is just not achievable.
Okay. There are no other questions. We should move on to the next talk. Thank you very much again, Yoav. Okay, so our next talk and our final talk of the session is entitled Communication Requirements for Linearizable Registers, and Raisa is going to be giving the talk.
Hi, I'm Raisa Nataf, and I'm a PhD student at the Technion under the supervision of Professor Yaron Moses. And I will present our work, Communication Requirements for Linearizable Registers. So first, just a quick reminder about what linearizability is. We say that the implementation of a shared object is linearizable if in each execution of it, each operation appears to occur instantaneously in a way that is consistent with the real-time order of the events in the execution and the sequential specification of the object. So for instance, for a register, the sequential specification says that a read must return the last return value. So here, if we have an execution like that, where we first have a write operation that writes A, and then after it ends, a write operation writes B, and then after this write, there is a read operation, then the real-time order requirement says that we need to linearize or order first the write of A, and then the write of B, and then the read operation. And now the sequential specification says that the read must return B, which is the last return value. But we could also have a run like that, where there is an overlap between the two write operations, in which case we can either linearize as before, write of A, and then the write of B, and then the read must return B. But we can also first linearize the write of B, and then the write of A, and in this case, the read must return A. Okay, so this was a reminder about linearizability, and linearizability is the gold standard for concurrent implementations of shared objects, and is really important for practical systems. But in asynchronous model, this can be quite hard to achieve. We have on one side the dependency of linearizability on real time, and on the other, the asynchrony of the model where there is no clock and no access to real time. So communication is required to overcome this tension. And here we ask the question of what is the cost of linearizability in asynchronous systems. And more specifically, how should operations in a linearizable register implementation should communicate? So for instance, if we have an execution where we first have a write that writes A and then a read that returns A, it is quite clear that communication is required from the write to the read. But we can also ask the question between two write operations that write two different values. Must there be communication or message chains between them? And even less clear, when we have first a read operation that reads some value, and then later a write operation that writes another value, must there be communication between them? We will answer all these questions, and in order to do that, we proceed in several steps. We first depend the analysis of the link between message chains and the ordering of events. Our results there are general for asynchronous models. And then we use these results in the context of registers and obtain lower bounds on communication for linearizable implementations of multi-writer, multi-reader registers. As we will see, this implies the necessity for read-write operations to interact with current sets of processes. And many work study linearizability and provide lower bounds for the worst case. But lower bounds for all executions and then including best case are rare, and this is what we provide in this work. Okay, so we are in the asynchronous message passing model. For ease of exposition, we assume time is discrete. We assume that values are written at most once. And finally, we are interested in obstruction-free algorithms that are resilient to up to F crash failures. And by obstruction-free, we mean that if we have an operation that runs alone, there is no other operation concurrent to it, then it must terminate given that up to F processes can fail. Now let's see a formal definition of message chains. So here you can see several processes, I, J, K, L, and we call a process time pair a node. So for instance, this is process I at real time t, and this is process J at real time t prime. And in an execution, processes can send messages. So for instance, here I send a message to K. A bit after K receives this message, it sends a message to L, and then later on, L sends a message to J. Then we say that there is a message chain from the node IT to the node JT prime. And formally, the definition is like that. We say that there is a message chain between nodes theta and theta prime in R if either a message is sent at the node theta and it arrives at theta prime, or I and J are the same process, but time t is smaller than t prime, or transitivity. There is some node, theta double prime, such that there is a message chain from theta to theta double prime, and from theta double prime to theta prime. And Lamport calls this relation the happens before relation, and previous results show that the only events that can impact a node are the ones that have a message chain to this node. And this leads us to the definition of the past of a node. So here again you can see some processes, I, J, K, and we look at the node theta, and we have several message chains. Then the past of theta is the set of nodes that have a message chain to theta. So here these are the nodes in purple or in the yellow part. And observe that here there are nodes that in real time are before t, but since they do not have a message chain to theta, then they are not considered to be in theta's past. And the boundary of the past of theta is a consistent cut, meaning that there is no message from outside the past of theta to the past of theta. And this property is crucial for our next theorem. So our first result is a fundamental property of asynchronous model. And it says like that. if we have a run R, we can take a node in this run and build a run R tilde in which all the events that are outside the past of theta are delayed by an arbitrary amount of time, delta, in a way that is indistinguishable to all processes. And the reason why we can do that is because the model is asynchronous, as because of the property that there is no message from outside the past to the past of theta. So how do we handle messages when we build R tilde? If we have a message like mu0 that is both sent and arrives in theta's past, then in R tilde its sending and arrival time are the same. But we can also have a message like mu1 that is sent in theta's past but arrives outside the past of theta. And in this case, we delay by delta only the arrival time. And finally, we can have a message like mu2 that is both sent and arrives in outside the past of theta. And in this case, we delay both the sending time and the arrival time of mu2. And observe that if we had a message from outside the past to the past of theta, then when building R tilde, in order to preserve indistinguishability, we would have to delay only the sending time. And we could obtain that a message arrives before it is sent, which is obviously impossible. Okay, so our delaying the future theorem is crucial for capturing the link between message chain and the real time of events, and we will use it in our next results. Now we look at registers. So we have operations, read-write operations, and they are not atomic, they take time. Operations start with an invocation and end with a response. They can contain some local computations and the sending or the reception of messages. We denote by letters X, Y, Z operations, or directly R and W for read and write, and operations operate on values, A, B, C. We denote XA smaller in R than YB, the fact that XA's response occurs before YB's invocation in R. So this could mean, for instance, that the write of A ends before the read of B starts, or any combination for X and Y to be write or read. Okay, and now our first result is that if in a run we have two operations, one on A and one on B, XA and YB, such that YB starts after XA ends, and YB completes, and it runs in isolation, there is no other operation concurrent to it, then there must be a message chain from XA to YB. So again, this holds for every combination for X and Y to be read and write. And in order to understand why, let's assume that there is no such a message chain. What we can do is build a run R prime that is identical to R until this point, the end of YB. And here we add a read operation. And now we can show that this read operation, no matter what X and Y are, must return B. Okay, until now everything is good. But now what we can do is apply our delaying the future theorem on the node that is the end of YB, and build a run R tilde in which we delay by delta everything that is outside the past, so XA and the read of B. And we obtain a run like that, where we first have an operation on B, and then an operation on A, and then a read operation that returns B. And this is a violation of linearizability. So we show why in the paper, but for now, to understand, think that Y is a write operation, and X is also a write operation, so we have a write of B, and then a write of A, and then a read operation that returns B. And this is a violation of linearizability because now B is no longer the last written value, because A has been returned after B. And again, this is a violation even if y and x are read operations. And observe that when I performs its operation, xa, it does not know if in the future there will be some operation that runs alone on another value. So it must construct a message chain. So, and again, I recall that xa and yb can be read or write of a and b. So we obtain that every register implementation must construct message chains between operations of all types. And another step in our understanding is that message chains are not only to communicate values, but they are for timing purposes. When we have a message chain from xa to yb, this guarantees that yb does not end before xa starts. So here, when we require a message chain from the read of A to the write of B, which can be somehow surprising, this guarantees actually that the read of A is not strictly after the write of B. Because otherwise, if there is a message chain, then we would have that there is a message chain that arrives before it starts. And it is impossible. Okay, and now our next central result that follows from our theorems is that every completing operation must have round-trip interactions with a quorum of at least f other processes. When I recall that f is the maximum number of failures. So here, in this example, f is equal to 2, and you can see then a round-trip interaction from p to k and back from k to p, and another one from p to j and also back from j to p. Okay, let's see a sketch of the proof. Assume that we do not have such round-trip interactions. So here, for instance, we do not have the message back from j to p. This run is actually indistinguishable to p from this one, in which its message chain to j arrives way later. And what we can do now is adding an operation on b, yb, that starts after xa ends. And observe now that yb must terminate even if it does not hear from processes k and p. Why? Because to i's point of view, it could be that processes k and p failed, but we are in obstruction-free algorithms. So yb runs alone, it must terminate given that two processes fail. So yb terminates, but here we do not have a message chain from xa to yb. So this contradicts our previous theorems. Okay, so to conclude, our work provides lower bounds on communication for linearizable implementation of registers. We saw here three main results. We saw that there must be message chains between almost every two operations. And thus, linearizable multi-writer, multi-reader implementations must construct message chains between all types of read-write operation pairs. As we saw, this implies that every operation must have round-trip interactions with quorum sets of processes. And our analysis is based on the fundamental and general theorem, our delaying the future theorem, which relates message chains and real-time order in asynchronous systems. Here are some related work. I won't have time to explain how they relate to our work, but if you're interested, then we can talk about that offline. And regarding future works, we plan to extend our analysis to other tasks, such as dimension replication, to other models, and to variants of linearizability. Maybe this is the linearizability as was defined before. And that's it. Thank you for listening, and I'd be happy to take some questions.
Okay, do we have any questions? Yes.
Is that really first presentation or is it actually important, like some changes?
We looked also at what happens when we do not have this assumption. Basically, the theorems are a bit quite more cumbersome. And by the end, it seems that the implication that we need, that operations must construct message chains still remain. But we need to change a bit the intermediate theorems.
Any other questions? Yes.
Any asynchronous stuff, but the particular theorems are only about registers.
Yes, modeling the future theorem is really general for asynchronous models. We did not have like to assume some read or write operations. And we applied it in the context of registers, but it can be applied for other objects.
Anything else? Okay, I had a quick question as well. I guess so. This delaying the future theorem. Can you use this sort of technique to get like concrete like lower bounds on like message complexity or something like that, or is it not that precise? I guess.
So now we use it in order to for lower bounds on communications. Can you maybe?
Sorry. So
Yes.
can you get like an exact number? So like I know that each operation has to send n messages or something like that. Is that?
We did not look at that, but it's an interesting question. Yes, but here, like an implication of our previous results is that processes must interact with f other processes. So at least at the beginning, there must be a message chain from the first one to f other processes.
Yeah.
So this is-
Okay. Awesome. Thank you.
I understand the is lower bound, right? But could potentially be much more like so it's still interesting to analyze, right? Because this is it's acting still okay.
Okay. Any other questions? Okay, so let's thank the speaker again. And that brings us to our first coffee break of the day.
So let's get started. Welcome everybody to the next session entitled Sorry You Cannot Compute That Here. And the first talk about what you cannot compute will be given by Gregory Chokler from University of Surrey. Okay.
So good morning, everyone. So I'm glad to be here. So this session is about what we can't compute, and I'm going to talk about what we can't compute in weak memory. And this is a joint work with my colleagues from UNAM and Lviv University, as well as University of Surrey, Armando Castaneda, Brijesh Dongol, and Ori Lahav. So let me first motivate weak memory and say what it is, more or less. So first of all, weak memory is important because it's a standard in modern hardware architectures. And you can think about C11 standard, but also GPUs and non-volatile memory, a remote direct memory access. They all have weak semantics. So what it is? So what has been weakened? So what has been weakened is this standard linearizable memory that we are all used to. So it's which we call strictly consistent memory here, SCM, and we want to make it more efficient. And this efficiency is achieved by delaying propagation of writes. So when I write something into memory, so that a write may potentially end up in a buffer, and that may propagate to memory and become visible at some indeterminate future. And this results in counterintuitive behaviors that complicate algorithm design and their correctness verification. So here is a kind of classic litmus test. So this is how we can do safe mutual exclusion, something that's called safe sleuth by Dijkstra in the linearizable memory. So there we have two processes, though so each process writes its own variable and then reads the variable of the other process. And both variables are initially zeros, and then I enter the critical section if the variable of the other process is zero, right? So what we can say about this algorithm in linearizable memory is that if, say, process one finds the variable of the other process equal to zero, it means that there is this happens before edge from its write to the write of the other process, and therefore we can't have this edge from this read to the write of the first process, because if we do, then we have a cycle and it's not linearizable, and therefore it guaranteed that if I see zero in the variable of the other process, then the other process would see one in my variable, and then we have mutual exclusion. So more generally, this is an instance of a synchronization pattern which is often used in linearizable memory, which is called read after write. So essentially, I write something and then write some variable, and then I read variable written by the other process. So this is how it works. So this breaks in any weak memory model, doesn't matter which. So what happens there is that visibility of writes can be delayed, and because of that we can have these cycles here. So it's perfectly possible that both processes would find zeros in the... Okay, so that demonstrates the difficulty of that. And actually we can more or less easily argue impossibility of mutual exclusion in a weak read-write memory. And there are many ways, of course, to do this, but one which is going to be useful in our context was introduced in 2000 in the PhD thesis of Jalal Kawash. And these take advantage of the following observation, that any two solo read-write traces can be arbitrarily interleaved, or as we're going to call it, merged, under weak memory. So that means that any interleaving of two solo read-write traces is a valid trace in weak memory models. So we can easily exploit this observation for impossibility proof. So first we have one solo trace, and the process is doing some reads and writes, and then it must enter critical section because it is solo. The same about this solo trace, right? And then we essentially just take the solo traces, merge them together, and we have this trace where both processes participate, but because this merge is valid, right? They don't see each other. They don't see any difference with the solid traces, and then they enter critical section, and we don't have mutual exclusion. Right. So how can we deal with that? So of course, in the weak memory, you have things like synchronization primitives that can be used. So these synchronization primitives can be either fences or read, modify, write instructions, such as compare and swaps. And it is easy to come up with the correct version of save sleuths using fences. So we can just insert a fence after the update of the variable. And this works under TSO. It doesn't work under all weak memory model, but it works for TSO, because fence and TSO would immediately propagate any locally buffered write to the memory, and then they become instantaneously visible to everyone. So that essentially reduces this to strongly consistent memory. So this works, but this is expensive, right? So these instructions are expensive, and we would like to the extent possible, minimize their usage in our program. So then it makes sense to ask the following question. So what can be implemented in weak memory, and what are the synchronization costs? And in particular, refining this a little bit, what I want to know is that what are the minimum constraints from the synchronization pattern for object implementation under weak memory? And we want to naturally measure that in terms of fences, read, modify, writes, and their placement. So so another goal that we had is that to come up with the generic framework that would abstract away intricacies of different weak memory specifications. So there is, as some of you may know, there is like a plentiful, let's say, a huge gamut of weak memories that have been defined, and we want something that can essentially be parametric. So I have a object that I want to know if I can implement it and at what cost, and I have specific memory model, and then I can somehow relate them to each other and get my impossibility result or lower bound. Okay, so those were our goals. And this is the generic mergeability framework that we came up with. So in this framework, we have two inputs. So one is the object type that we want to implement. The other one is memory model. So we just have their raw specifications. So the next thing you have to do is to come up with some mergeability properties of histories of the object. Okay, so that would kind of abstract away the tolerance to reordering of the object specification. Then I do the same for memory model. So we have seen one example already, right? And then the centerpiece of that is something that we call merge theorem, that essentially relates mergeability of object histories to mergeability of memory traces. And then we apply merge theorem, and then what we get back is the synchronization bound for implementing this object under memory model. Okay, so this is what it is. And let me briefly explain the merge theorem. So the merge theorem is kind of the most important thing. And what I'm going to show you in the slides is more or less the first 50 pages of the full version of the paper. So that was the most technically involved part of the paper, but hopefully it is intuitive. So first, we define strong and weak mergeability for memory, for traces of the memory model. So strong means that we can that every so giving the a pair of traces sigma 1 and sigma 2, they are strongly mergeable if any interleaving is allowed by the model, and they are weakly mergeable if only some interleavings are allowed. Okay, so we have seen already that for read-write memory traces in weak memory models, we have strong mergeability because all interleavings are allowed for all pairs of traces. So then we lift this exactly the same notion to histories of the object. So we have strong and weak mergeable histories just by the same token. And then here comes merge theorem. So if we have an implementation of object O, of object type O, then for all pairs of traces, pi1 and pi2 of this implementation, if the projection of these traces to object histories are not strongly or weakly mergeable, respectively weakly mergeable, then the corresponding memory traces must also be not strongly or weakly mergeable, right? So notice that I'm using contrapositive here because I want to use it for proving lower bounds. Okay, so which implementations we assume? So generally, it's just any linearizable abstraction-free implementation. So one thing that I want you to notice here is that the statement of this theorem is in some sense reminiscent of a cup theorem, but for this shared memory setting. So essentially what it says is that if you want consistent and available, which means linearizable and abstraction-free, then you can't have partition tolerance. So this mergeability of traces essentially captures the possibility of partitions in message passing. Okay. So, so now I just want to show you this framework in action. Okay. So first, we use this framework to see that it is general enough to capture all the similar results about computability in weak memory that exist in the literature. Okay. So so those were proved for strongly consistent memory and for mutual exclusion and objects with strongly non-commuting operations. Okay, so using our framework, after you have this machinery of Merge theorem, it's pretty much 10 lines to show that this result that have been previously shown in this work here is that mutex and this type of objects require read after write pattern that we have seen, or read modify write under strongly consistent memory. Okay, so that means that in a weak memory, we need to do something, for example, to enforce raw, to enforce read after write, like fences and things like that. Okay, so this was done before in papers that were long and technical, and we show that that can be done very easily in using our framework. But these results are not new. So what results are new, we believe, is that we can now use this framework to do something about weak object types. And by weak object types, I mean various objects with consensus number 1. So that includes register, max register, monotone counter, snapshot counter, etc. And we do this for two widely used weak memory models. So one is total store order, TSO, and the other one is acquire. And what we get back is the new synchronization bounds for this type of object implementations under TSO and array, under these two models. Okay, so I will show you some examples of, I will show you a quick example with the register, but very similar argument can be used for any other weak objects that I mentioned before. So we start from two solid histories of a register, right? So this B0 is the initial value. Then this interleaving here is not in the sequential specification of register. That means that registers are not strongly mergeable. So on the other hand, we know that that any two read-write traces are strongly mergeable in TSO and array, and then we apply the merge theorem, and we get that the fence is necessary to implement register in TSO and array. And indeed, just inserting fence right after here gives us the optimal implementation. And this is because fences have this push semantics when we apply them. So they actually push everything known to the process into the RAM. So we prove more general results that that there is a simple fence insertion strategy that you only need to insert a fence between before every write. If you have read followed by the write, then we need to insert the fence. And if write is the last operation of the of a specific object operation, then we also need to include the fence. And that gives us a TSO implementation. and this implementation is fence optimal. Okay, so how much time do we still have? 3 minutes. Okay, right. So, so the things are not that simple with release acquire. So, in particular, this implementation doesn't work under release acquire, and this is because the fences under release acquire have a weaker semantics. So they essentially have a pool semantics. So they just pull what is known to the other process into the view of this process. Okay, and also array is a kind of a causal memory. And here we have a situation that these two writes are not causally related, and therefore, as was mentioned in the recess talk, we don't have a chain of information propagation, and therefore it is perfectly fine in this case to return 1 after this write, which violates linearizability. So we can prove again using merge theorem that trailing fences are not strong enough to get implementation under release acquire, and in fact, what can be done is to add the leading fence as well. So here, this is a fixed implementation of the register with the leading and trailing fence, and this is also fence optimal in narrow bounds, and this applies to all these weak object types. So now this does not hold. Interestingly, this does not hold for snapshot and counter. So I don't have time to go in detail over this example, but there is a specific pair of traces of snapshot which are not weakly mergeable, and by merge theorem we get that in this case fence in the middle is necessary. So, and this also holds for counter. So this is just to summarize our results. So we have for TSO, we have the necessity of fence, and we have an upper bound with the trailing fence for this object, and this is type. For release acquire, we have a necessity of leading and trailing fence, and we have a matching bound for this object, but this does not apply to snapshot and counter. So for snapshot and counter, we need fence in the middle, and that establishes the for the first time, I believe, the separation between max register and all these objects and the snapshot, that all of them, all these objects are not separated in the existing measurements, so they all have consensus number 1, right? So, and here, just by accident, we discovered this interesting result. So here we have a question mark. It doesn't mean that we can't implement snapshot in array, but we are not aware of a fence optimal implementation, right? So the implementation must have leading and trailing fence, and then fence in the middle, but we don't have the implementation that matches that, right? Okay. So this is to conclude. So we introduced the new generic framework for proving synchronization lower bounds in weak memory models. We have merge theorem that relates mergeability of object histories to mergeability of memory traces. This subsumes the prior bounds for mutual exclusion of strong object types. And we have some, we believe, new lower and upper bounds for implementing weak objects under TSO and array. And if you are interested to further study the relationship between weak memory and distributed computing, we have a 3-year postdoc position at University of Surrey, jointly with Imperial College. So please talk to me.
Okay, are there any questions? People don't like weak memory, prefer strong one. So can I ask you something? So, so for example, since your kind of sales pitch is simplicity, if I take some complicated model like C++ or a fragment of C++, right? So it's complicated because it mixes multiple kind of different, like strong consistency, release acquire and demand, you know, something weaker. Then have you tried, is it going to fit into this frame, or because I have to like still like do some trace semantics or something for this model?
Yeah, so first off, really requires a fragment of C level, right? So that's and our results work for really require. But you're right, yeah. So we have not tried for more complex semantics, but I don't see why that won't work. So that's the whole idea is that but someone needs to sit down and figure out this box here, right? So then that's it.
Okay. Okay, let's thank the speaker. Oh, sorry. There is. Yeah.
Well, I have to say yes, because it's our work. But I'm. So there are alternatives. I don't know if you're familiar with loss of order paper, which is quite long and complex, and using things like covering argument and more like this classical distributed computing type of argument. It's this is what exists in addition to that, I believe, right? So that's this looks like the simplest to me. So I actually myself managed to use it in my everyday life. So that's a student asked the question if you can implement this object, and then okay, let's think about it. And I think it's pretty comfortable.
Maybe the simplest option is to work with you.
Yes.
Okay, on this cheerful note, let's thank the speaker again. Okay, so the next speaker.
Yeah.
Oh, okay. So the next speaker is Yanis Kutuli, and he's gonna talk about the simple computability theorem for correless tasks.
Yeah. So hi, thanks for the introduction. So I will talk about computability for correless tasks in the sub-AIS model. I'm Kutuli Yanis. I'm a PhD student of Emmanuel Godard, and we are from Marseille. First, I just want to talk about my model, the AIS model, and the simplicial complexes. So, this is the immediate snapshot model. You have instant graph, so they are communication graph. There is two processes, the white and the black. And so you can have that, it work? Yes. You can have that white send something to black or black send something to white in this graph. Or they can also exchange information. The main things to look at is the local view. For example, there is blocks that have the same local view, hence we can merge those two vertices to get something that we call simplicial complexes. And I will call this construction the chromatic subdivision. I can do this for more processes. So this is for 3 processes. I have many more graphs, but I can still merge them on local view, and I will again end up with simplicial complexes that is called the chromatic subdivision, just a level higher. So that's immediate snapshot, but we are interested in iterated immediate snapshot, and so we just take an infinite amount of steps of immediate snapshot. And so geometrically it looks like this. So if you look at the blue execution that is of size 2, you have at the first round white send something to black, and then black and white exchange some messages. So you end up in the blue segment there because you are there and you go down in the middle. You can do this for any other execution. I have 3 examples. You can start in the middle and then you go from black to white. So this is the red one, and you can do both times. Black send something to white, and you end up to the far right. Yes, good direction. The main thing to have in mind is that when there is a vertices between 2 processes, between two simplices, sorry, this is something about uncertainty. For example, if you look at the orange ones, this is black processes that does not know if at the first round white receive his information. And so when at the second round it get no information back from white, he still have the same uncertainty that had the first round. And so he is at the same position. So that was a bit an informal presentation of simplicial complexes and AIS, but now we can be a bit more formal. So the AIS model is just you take a Easton graph, so communication graph, and you ask for two properties. The first one is called immediacy, but the real name is transitivity. And so if you have three processes A, B, and C, such as that A sends something to B and B sends something to C, then A have to send something to C. Okay? The second one is containment. Containment it mimics the fact that this model is in fact a shared memory model. And so in a shared memory model, someone have to write something first in the memory. And so you say that in the graph, for any couple, it's either A sends something to B or B sends something to A. And now if you try to run the computation, you look at all of the instant graph for two processes, you end up with exactly the example I made before. And so for the AIS model, you end up with a simplicial complexes. And the simplicial complexes is this. So first, we want to define mathematically what is a simplex. If you take n+1 processes points in Rn, and they are linearly independent, this is a simplex. You can take the double bar to mean that you take the convex hull of this simplex. And then to form a simplicial complexes, I will not see a simplicial complex. And if you have a simplex in your simplicial complex C, and you have a subsimplex in it, then it is also in your complex. And now if you take two simplices that have an intersection, they have to intersect in another simplex that is also in C. If you are a bit confused about the math, okay, this is still triangle or segment, they have to intersect on another segment or another vertex. So nothing too complicated at all, I hope. Okay, why is it cool? It is because we can talk about a lot of distributed problems at the same time then. So this is a colorless task. So this is things like consensus or cassette agreement. And so we define this with an input complexes, where each simplex is a subset of input value. The output complexes, each simplex is a subset of output value, and then you define a map that goes from the input to the output. So this is the specification of your problems. And if you want to make a quick example, if you look at this point, this means that everyone starts with the value 0, and so they have to decide the value 0. If everyone starts to 1, they have to decide 1, and if not, they have to just choose one value and be anonymous on it. And so in this framework, there is a very famous theorem that is called the asynchronous computation theorem that says that for a task EO delta is solvable on a protocol on AIS if and only if there is a continuous function from F from I to O that respects the specification of the algorithm. We can look at the previous example, the previous task, and see that, okay, this task is not solvable on the AIS model because you want to have a continuous function from a segment to 2 point. And if you want to touch the 2 point, you are not able to find a continuous function, hence this is not possible. So you have a very direct proof, and you don't have to do a lot of computation stuff. So that was the basics of my subject. Now what we are really doing is we talk about general message adversary. So you take the communication graph of before, we call this, and if you take an infinite sequence of it, I call this dynamic graph. And if you take a set of dynamic graphs, this is a message adversary. And then, you can define some model of AIS by just taking, general message adversary of AIS. I have two examples. The first one is M1, where you take every execution, but you only remove the one where at the first round, black and white exchange some messages, Or you can take something that is a bit more interesting. This is the RNT, the Theresia model. And so how you define this, you say, okay, I keep every execution such that the number of processes that participate an infinite amount of times are of size n+1 minus t. Another way to say it is that I want at most to have t crashes. So we can model a lot of interesting things in this generalization of AIS. And so the main contribution of this paper is only one theorem. that say, okay, a colorless task EO delta is solvable on M, a submodel of IIS, if and only if there is a continuous function from I times GO of M to O that respects the carrier map delta, the specification of the algorithm. What is the function GO? And okay, we present this function GO last year at DISC. And basically what we want to do is to give to any execution a geometrical point. And I think it's more clear on an example. If you take this execution W, which is with G1, that is this graph, and then K3, which is just the complete graph, and you look at the prefixes of this execution, well, at the first round, you end up in this orange triangle. When you look at the prefix of size 2, you end up in this little orange triangle there. And you can do this an infinite amount of time, you will end up with 1 point. If it is a bit complicated, it's just that from an execution, you get at the end a geometrical point. Okay. So now you can read the main theorem now, and so the I times GO just means that, okay, for every input simplices, you put some message adversary and you give it a geometrization. A direct application you can see is, okay, now I can find a message adversary where the binary consensus is solvable. So this is a message adversary M. I remove this execution where everyone is synchronous at each time, sorry. And now what is the continuous function? It is that the top part of my segments go to the top vertex in O, and the bottom part goes to the bottom vertex in O. This is in continuous function, hence I have an algorithm for this message adversary. How do we prove this? I don't have the time to do everything, but we can be really quick about it. It is in 4 steps. The first step is, okay, we have a continuous function and we say that it is equivalent to some eta star condition. From this condition, we make what we call a terminating subdivision. We say that this construction is equivalent to have an algorithm that solves your task. And from this task, we can go back to a continuous function. I can detail 2 parts of this proof. The first one is, okay, this is the simplicial complexes. I can mark some vertex as terminated. This is in blue. I have removed 1 geometrical point in the middle of my triangle. Okay, I can do this again another time. So I make another subdivision where nothing is terminated. I get new point. I can also make them terminate. And the good thing is that since every point corresponds to a local view, I can just say, okay, in the algorithm, you terminate when you are marked terminated in the terminating subdivision. So you get from an infinite simplicial complexes, you get an algorithm that terminates for every local view in a finite time. The second part of the proof I wanted to show is, okay, the eta star condition means that how do we terminate the terminating subdivision? We use this condition, so we will take the time to read it. We take a function eta that from an execution, from the geometrization of an execution, sorry, associate a real number that is positive. And so for every point, every execution, there is a decision function, so a vertex in O, such that the neighborhood of my execution goes around the decision function, the decision on this execution. So in the schema, this is my neighborhood and it goes in the neighborhood of my decision function. This is the eta star condition. And so I can use it to terminate my algorithm. Okay, that's it for the proof. Now we just make 2 applications. This is not really new result, this is more new proof from these results. The first application is on set agreement task. Set agreement is when you have like n+1 processes, you want to decide at most n value, and that the value you decide are in your input problem. And so the characterization is that you just need to remove 1 geometrical point in your message adversary. How can we prove this? Okay, if we take back the theorem, the input complexes look like a ball. The output complexes is just the border of your ball. And your map is just says that, okay, I want to have an identity on the border of my ball. And well, there is directly a theorem that is called the no-retract theorem that says that you can't do this continuously. But if you remove 1 point, you can do it. So you have a direct proof of this characterization. Okay, the second application is more complicated. It's on T-resilient model. T-resilient model, again, it's where you want to have at most T crashes. Another way to say it is that the number of processes that participate an infinite amount of times is of size n+1 minus t. And now if you want to try to geometrize it, it's a bit complicated because it will look like a fractal. So this is for 3 processes and t is equal to 1. And how you can construct it is to say, okay, I have my subdivision. I remove every vertex. This is they are in red. Then I do another step of subdivision. I again remove every vertex. And if I do this an infinite amount of times, I get the geometrization of a T-resilient model. So this look like this is really complicated, but we still managed to work with it. On this model, there is a theorem by Erlin and Chavitz that says that, okay, a task EO delta is solvable on a T-resilient model if you have a continuous function from the skeleton of size t to O. The skeleton is just you take every simplex of dimension t or less. And their proof is basically, okay, since I know that not everyone will crash, I can just wait some processes, and after that I can just decide, and this is a very nice proof, very intuitive, but there were no topological proof of these results. And how we did it with Emmanuel is just we use a mathematical object that is very common for mathematicians, at least, that is called a fiber bundle. I don't really have the time to explain what it is because it is very long, but I have a beautiful slide for it at the end if you want to. So yes, that's it for this proof. To summarize, okay, colorless computability for sub-AES model is kinda solved. And what is nice about the theorem we get is that this is just about the existence of a continuous function in the standard topology of Rn. So this is Euclidean space, very nice, very easy to understand. So that's the main appeal. And now what I am doing now in my PhD, I try to get the same characterization for colorless task. This is a bit like the next talk Sergio will give, but we don't do the same things. I try to apply this theorem to condition-based set agreements with T-resilient submodel of AES, because Sergio told us it was still an open problem. And then we try to do this for other models that are not like AES, that have a nice subdivision on it. Thank you.
Okay, are there any questions? Oh, yeah.
So is there any hope to use some of these techniques for solving complex environments? Or do you think it's restricted to complexity?
Yes, but no. Like this theorem talk only about computability, but I think there is a nice paper in PodC this year that talk about approximate agreements and that give like complexity measure on it, and making iterated subdivision is like doing approximate agreement, kinda. So I think there is some connections, but the other part that you have to consider is that you have also to escape the infinite repetition of your subdivision. So if you can characterize those two parts, maybe you can have some complexity bound, but I think it is really complicated in the state of the art now to get something really good.
Okay, any other questions? Okay, then let's thank the speaker again. Okay, so the next speaker, Sergio. Okay, so the next speaker is Sergio Raxbaum, who's going to also talk about, about three process general tasks.
Yes, thank you. So it's the talk of previous talk of Yanis was a great introduction to what I will discuss. He already mentioned some of the basic notions, and here in this talk, actually, we are interested in a very basic question of which tasks are solvable in the weight-free model. You have just a set of asynchronous processes that may crash and communicate by reading and writing shared registers. And as Yanis was mentioning, there is a very clear direct connection with topology for a large class of tasks that is called colorless tasks. These colorless tasks are tasks that you can define without talking about process IDs, but just about input-output values like consensus, set agreement, approximate agreement, and many others. And the theorem says that a colorless task is solvable if and only if there is a continuous map from the input complex to the output complex respecting the task specification. So why this theorem is so nice? It's really a direct, clear connection with topology, very in both ways, a very deep connection that allows us, for example, to bring in tools from topology to prove things about distributed computing. And the most interesting example is a direct proof that actually it is undecidable which tasks are solvable, even for the case of just three processes. Okay, very good. But now the questions we are concerned is that actually not all tasks have characterizations in terms of continuous maps, only colorless tasks. So researchers over the years have tried to understand how to deal with this, with the general tasks that are not colorless in terms of continuous maps. And this is one recent example of a paper we published a couple of years in ITCS. But let me give you a concrete example so you can see exactly what is going on. This is what is called the majority consensus task. And an example on the left, you have an input configuration where the black process starts with input 0, the gray process starts with input 1, and the white process starts with input 1, represented as a triangle. And on the right, you have a relaxation of consensus. You have the top triangle that requires the three processes to decide 0, on the bottom, the three processes that are required to decide 1, but you are also allow a bit of disagreement in a non-symmetric way. You say, okay, I'm okay also if more processes decide the value 0 than the value 1. So I add three more triangles to the output complex represented, which are indicated here, where two processes decide 0 and only one process decide 1. And this is not a colorless task because you see you have to talk about the process IDs to really specify the tasks. So this majority consensus task is interesting because actually there is a continuous map from the input complex to the output complex. You can imagine how do you squeeze the triangle to be able to pass through the narrow part. There is a narrow part here represented by the vertex where process, here the black process decides 1, and it's kind of in a narrow region where you have to squeeze the input triangle to be able to pass and map it onto the three triangles that are marked in green there. So this is an example of a task that has a continuous map, but it is unsolvable, the task. So why? How do you prove that this task has no weight-free solution? Actually, our first contribution in the paper is to observing the issue that some tasks may have different reasons of why they are unsolvable. In this case, one way of proving the unsolvability of the task is to show that actually if you could solve majority consensus, you could also solve set agreement, and we know that set agreement is not solvable. But this type of reduction, also here the proof is very simple. Actually, in general, it's undecidable to do this type of argument due to the undecidability result that I mentioned at the beginning, given for three processes. What is interesting is that there is another way of proving the unsolvability of this task, which is decidable because it is very local and has to do really with the issue that I was mentioning, that there is a vertex here in the circle 1 that has a neighborhood that is disconnected. This is what is formally called the link of a vertex. The link of a vertex consists of all the edges which belong to triangles that contain that vertex. So the link of that vertex consists of two disjoint edges, the red edges. And what we propose in the paper is actually a way of transforming the output complex into an output complex O prime, where all the vertices have a connected link. So you can see the transformation on the right, where you look at the link of the green vertex that is marking with a circle, and you see that the link of that vertex is a graph that is now connected. It consists of those two edges. And once we are able to prove this transformation, then we can have a theorem of the type that we wanted, a continuous type of theorem, saying that a general inputless task T is solvable if and only if there is a continuous map from the input, not to the output complex, because we know that in general that's not possible, but to the modified output complex O prime, where all the local links are connected. And this is the main result of our paper, and there are various open questions. Of course, the first one is how to extend this theorem to more than 3 processes, but there are also interesting questions actually related to the previous talk of Yanis and to the next talk actually of extension-based proof. Also, this type of obstructions could be proven that way.
Any quick question?
Just I wanted to mention, I forgot that on Friday during the Hackda workshop, I will give a introduction that requires no background to all this general area of continuous functions and topology, where you can learn more about it.
Okay, nice. That's at 9 a.m. So
9 a.m.
if you have a flight that's not too early, you can still attend. Okay, if there are no questions, then let's stay. Oh no, Piotr. Okay. No, yeah.
What happens if you have inputs?
If you have inputs, yeah, in the full version, we are extending the proof to just the general case. There are a bit technicalities that make it not as clean.
Okay, let's thank the speaker again. And the next speaker, where's the next speaker? Okay. So okay, and the next talk is by Yusun Shi, who's going to talk about call-less tasks and extension-based proofs.
Hello everyone, my name is Yusun Shi, and I'm a graduate student. Today I will present the paper Colorless Task and Extension-Based Proof. This is a joint work with Weidong Liu. In this work, we gave a necessary and sufficient condition for colorless tasks to have no extension-based proofs of the impossibility of weight-free protocols in the NIIS model. Our method is decoupled from the setting of any concrete task, like the KSAT agreement task or the approximate agreement task. We also show some property of an iterated standard chromatic subdivision of a complex. A group of researchers pointed out the differences between valency argument and the combinatorial techniques used in the proof of impossibility of consensus and the NK-set agreement. In the FLP proof, an infinite execution can be constructed by extending an initial configuration infinitely often. In contrast, in those proofs use combinatorial techniques, the existence of a bad execution is only proved but not explicitly constructed. They introduced the class of extension-based proofs, a generalization of fallacy argument, which also shows the impossibility of a weight-free protocol for a task by repeatedly extend an finite execution to construct an infinite execution. An extension-based proof is an interaction between a prover and a weight-free protocol that claims to solve a task. The prover attempts to refute this claim by constructing an infinite schedule or by reaching a configuration where the protocol violates the task specification. The interaction proceeds in phases. Begin with phase 1. In each phase, the prover learns information about the protocol by submitting a finite number of queries to the protocol and maintain a finite set of configuration it has reached during the phase. If the prover is not able to find some error of the protocol, it has to end the current phase and choose some reached configuration C. The configurations in later phases are all reached from this configuration C. If at the end of some phase, the prover chooses some a configuration C such that in each configuration reached from C, every process is terminated, and the values output by process satisfy the task specification. In this case, the prover loses, otherwise the prover wins. We say a task has an extension-based impossibility proof if there exists an extension-based prover that can win in its interaction against any protocol that claims to solve this task. Several problems like the Anki set agreement have been shown to have no extension-based proof of impossibility. So a question arises here: is there a topological property of tasks that characterize when they have extension-based proofs? By the famous ACT, a weight-free IIS protocol that solve a task can be represented by a map from an iterated standard chromatic subdivision of the input complex I to the output complex O that does not violate the task specification. Let U be some simplex of the input complex I. We define FIU as the subcomplex of the I standard chromatic subdivision of I, where processes in U are the first set of processes to be scheduled. So we define a weight-free partial protocol with respect to a simplex U as a map from FIU to O that does not violate the task specification. An example of a partial protocol with respect to one vertex is given in the right side, where I equals 2. The complex of red colors contain all terminal configurations of this partial protocol. A weight-free IIS protocol implies a set of weight-free partial protocols, each of which is with respect to one simplex. U in the input complex. But this is not true vice versa. Why? Because some configurations are defined by multiple partial protocols. You can see the green simplex, and it can be given different output values by different partial protocols. Since a full discussion
I'm sorry, I think we should kind of wrap up because we're out of time, right? There's a brief announcement.
okay.
So maybe if you could try to finish it quickly.
Okay. Since full discussion is too long, we will focus on the necessary and sufficient condition for approval to construct the partial protocol after phase 1. So a necessary condition is that there exists a partial protocol with respect to each simplex in I, and since we are talking about extension-based proofs, they have to give the same output values for some simplex, like the green simplex, and we show that this condition is also sufficient by designing an adaptive protocol that can win against any extension-based prover. Okay, thanks.
Okay, is there any quick question? No, so then fine, let's thank the speaker again, and we'll start the next subsession.
Okay, so for the final session before lunch, we start by Kaya Alptour giving a talk on a knowledge-based analysis of intersection protocols.
Thank you for the introduction. So this is joint work with Joe Halpern and Ron Vandermeiden. And I'm going to be talking about cars today. So as cars become smarter, we expect them to be able to communicate wirelessly. And in this scenario, it's conceivable that we can do something better than traffic lights. So we also want some kind of fault tolerance in this scenario, because I don't want my car to crash if my broadcast fails. And we'll also have it's conceivable that we'll have a time period where we have both human drivers and the smart cars, so that human drivers can be thought of as faulty in our model. And there are also many types of intersections, so we want our model to be as abstract as possible. So it shouldn't depend on the sort of topology of the intersection itself. And it should capture all types. So this question of inefficient traffic lights have long been recognized, and there's a lot of related work. And to the best of our knowledge, the related work can be summarized as these. So some look at specific intersection scenarios, so specific intersections with like 4 lanes. There are some others that do something like leader election, but without faults. And there's also a lot of simulation-based ones that really focus in on the implementation challenges. But in this work, we really want to take a theoretical foundation approach. So this is our model. There are an arbitrary number of agents numbered 1 to potentially infinite. There are incoming lanes, there are outgoing lanes that are numbered. And each vehicle, when they reach the front of some queue, has the option to execute some move, which is a move from an incoming lane to an outgoing lane. And we have a symmetric relation O that determines whether 2 moves are okay to be executed at the same time. So in this particular example intersection, the move 1,7 and 3,5 are compatible because they're just straight and parallel. And in this model, the arrival schedule of the individual cars and their planned moves are going to be adversarially chosen. And okay, given an intersection, the car reaches the front, and at each point, it has the option to execute two actions. It either goes or executes no op, in which case it waits. And communication is going to be broadcast based, so cars broadcast a message which reaches some radius within their current queue location. But for the purposes purpose of the protocols we will be discussing, we only assume one thing on the communication, which is that an agent in the front of some queue can broadcast this message to all the other agents in front of their respective queues. So the model is general enough to capture more complicated communication scenarios, which may depend on the intersection itself, but we'll be only assuming this weak condition. And we'll also only consider benign communication failure, so no lying. Within this framework, our specification is going to be to satisfy validity, safety, and liveness. So validity means you can execute Go only if you're in front of some queue. Safety means two agents executing Go means that they have compatible moves. And liveness means that if you're in front of some queue, then at some point in the future, you'll get to go through the intersection. And another way to think about this whole problem is in terms of distributed mutual exclusion. So this is kind of a generalization of distributed mutual exclusion. Yeah. So from the lane, you can go anywhere. So the lane determines your incoming. So we have the incoming lanes and the outgoing lanes, and your move is from which lane you want to go to which other lane. Yeah, there's no restriction, although the compatibility relation may restrict what moves are, yeah. Oh, no. So from the incoming lane, you can go to any outgoing lane. Yeah. So just a quick summary of our methodology. We'll be using the knowledge-based framework, and we really think that this is a natural application of it, given that we want to be immune from the specific shape of the intersection and work at this abstraction layer. We'll then define optimality criteria to see which type of protocols we want. And we'll also give a construction that achieves those optimality criteria via global to local construction. And that will make more sense in a minute when I get to it. So here's a quick recap of the knowledge-based approach. So we use the standard runs and systems model. So a run in our system is a function mapping time to global state. And global state is the conjunction of all the local states and the state of the environment. In this case, the state of the environment encodes which cars are in which queue and so on. And at some point, RM, we can interpret formulas about the state of the system. And the key definition here is going to be that of knowledge. So if I'm at a point, for all points that I consider indistinguishable given my view, so all points that have the same exact local state, if some formula phi holds in all those states, then I say that at this current point, I know that fact phi. So we'll be using knowledge-based programs to design these protocols. So these look like things like this. So I can have conditions on the knowledge of the agent. So for example, I may have something like, if I knows that I is the only agent in front of a lane, then it can go and otherwise follow traffic lights. And when we look at specific contexts that determine how we send the messages and how the intersection looks like, this will correspond to a standard test on the local state of the agent. So the implementation of this knowledge-based program in a specific context may look like something like, if I did not receive a reply, if not receiving a reply exactly corresponds to the knowledge test, then this will be the implementation. So we'll prove properties on the implementations of knowledge-based programs that we design. And some useful formulas, we say going I if the agent I is executing Go, and we say front I holds if I is in front of some lane. So what is our optimality criteria going to be? So one intuitive criteria, which is also used in the distributed exclusion literature, is that we want to eliminate unnecessary waiting. So there's no point RM where some vehicle I waits, even though it's in front of a queue, and it did not, its move wouldn't have contradicted anything that went in that round. So there's also a optimality criteria in the knowledge-based Byzantine agreement literature based on domination. So a protocol is optimal if nothing dominates it, and we define domination by the following definition. So we may have a protocol P and P prime, and we consider them on corresponding runs, so runs with the same adversary, so same arrival schedule, same failure pattern. So in exactly the same corresponding run, if one of them sends all agents earlier or at the same time, that means that that protocol dominates the other, if this property holds for all pairs of runs. So then a natural question to ask is, are these equivalent? And turns out they're not equivalent. So we'll give it another go. So I'm going to do the exact same definition, except that now I'm adding the word lexicographical in front of all of them. And what does this mean? So the only change is in the definition of lexicographical domination. So now instead of looking at all agents at all times and the times that they go through the intersection, I look at the two corresponding runs and the first time they differ. And the moment they differ in some time in these two runs, one of them sends more than the other one. And for the rest of the run, I don't consider anything. Exactly like lexicographical ordering of words. So the first time they differ, one of them has to be better for it to be ordered ahead. So given this definition, we can then ask the same question, are they equivalent? And turns out yes, under some conditions. So to make things a bit more formal, I'm going to move on to the next slide. So for the regular notion of optimality that we first defined that turned out to not be equal, unnecessary waiting, eliminating unnecessary waiting implies that we get optimality, but the converse is not true. So there exists some context, even with full information exchange and no failures, there exists some context where P has unnecessary waiting and is also optimal. But if you go back to the lexicographical regime, we see that we have the analog of proposition 1 hold, so no unnecessary waiting implies lexicographical optimality. And we can also get a partial converse in the sense that if we assume the information exchange is sufficiently rich and the decision rule only depends on the agents in the front, then we can get the converse to hold. And intuitively, the main problem here is that eliminating unnecessary waiting is not always possible. So we want some optimality criteria that can work even in the cases with faults, so that we can work with it in the next slides. So that's why hopefully this motivates enough why lexicographical optimality kind of captures what we want with the intuitive criteria of unnecessary waiting. So then for our construction, we're going to use this God's eye view of the intersection. And what do I mean by that? So we define an intersection policy, sigma, to be a mapping from the histories of the entire run to sets of allowed moves. So this is sort of this external view on the global state that tells us which moves are allowed. And if we assume that this policy satisfies some conditions of safety and liveness, so for example, whatever sigma gives us is guaranteed to be compatible, and whatever sigma allows, it allows infinitely often, then we can think of it as if we just follow what sigma says, and if we have access to it, then we should be safe and live. The main problem here is going to be that, okay, given an intersection policy, we may not always know when it's allowing things because we don't have access to the global state, we only have local information. So the obvious knowledge-based program here is that if I know that I'm in front and I know that my move is allowed by this global sigma, then I get to go, and otherwise I wait. And as I said, the problem here might be that even though my move is allowed, I may not know it in time. And here we get some nice results to be able to shift our view from global to local and local to global. So under some assumptions on the context, and And if sigma is correct in the sense that it's conflict-free and fair, then the knowledge-based program that we just defined has implementations that satisfy validity and safety and liveness. We get validity and safety immediately, and for liveness, we need some extra strong assumptions. And similarly, for every correct protocol, so for every valid and safe and live protocol, there exists a policy that implements this program. So there exists some intersection policy such that we can slot it in and this relationship holds. So this gives us a nice way to construct protocols. So we can think of just who's allowed to go in the global state and then plug it in to see what kind of local implementations we get. But one problem here is going to be that we are not guaranteed lexicographical optimality, so we want to do a bit more. So in order to get stronger guarantees, we are going to slightly modify the knowledge-based program. So not only I get to go if I know that my move is given, my move is allowed by this global policy, I also can get to go if this condition VI holds. And VI is a rather long condition, so I'm going to just state the intuition here for a time. But roughly speaking, if I is in a lane where its move is compatible with all others that may potentially go with this protocol, breaking ties in some cyclic priority order, then I can go. And the intuition I can give there about the priority ordering is that, okay, I may know that my move will be compatible with people who are going right now, but someone else might think that too. And if we both decide to go at the same time, we may run into some safety violation. So we have to have some sort of way to break symmetry in cases like that. So just to give intuition about what the protocol, when implemented, does. So it will allow my move if it's permitted by sigma and if I know these facts. Otherwise, and my move, if I don't know that my move is allowed by sigma, I'll look at the cyclic priority order. And if I know that everyone that can go before me don't conflict with me, then I can get to go again. So to formalize that result, suppose the following conditions hold in the context. So we have synchrony, and at all times m, we have this cyclic priority order that is known by all agents, and the top priority in that ordering is shifted such that it stops at each lane infinitely often. So you can think of it as a numbering from the lanes as I defined in the example, like 1 to some m. And at each time step, we shift the ordering by 1 so that everyone gets visited infinitely often. And if I assume that sigma is some condition that can be known, then we get the following results. So there exists a unique implementation to this knowledge-based program that I gave that satisfies lexicographical optimality in addition to validity, safety, and liveness. And so just to get some intuition on this construction, we can have something like if sigma is just empty to keep things simple, and we have the exact cyclic order that I defined on the lane numbering that shifts by time, we can make this construction work. Although sigma can be something more non-trivial as well. So you can, since sigma gets precedence over all others, it can be things like certain agents, special vehicles like ambulances, and whatnot. There are several future directions that we can consider. We can look at stronger adversaries. I think one interesting case is also the case for strategic behavior. Maybe I can lie to go through the intersection faster at the expense of others. And also, I would be curious to hear about like how this can be implemented in practice on the vehicle-to-vehicle network stack in specific contexts. And that concludes my talk. Thank you for listening.
Thank you. Any questions? Okay, so I have one. This is about intersections. How would you go about larger regions? You have an idea of modeling it or extending this to a more scalable situation?
Yeah, I actually we considered looking at maybe at the city scale, so many intersections in existing at the same time, and we can look at more global properties like throughput. But I think that's interesting future work.
Okay. Well, thank you.
Thank you.
So, the next speaker is Louis Tseng, and he'll be speaking about the power of abstract MAC layer, a fault tolerance perspective.
All right, thank you for the introduction. So MAC layer, it's a median access control, and basically that tell nodes how to access the shared medium. And if you are familiar with the OSI model, it's in there too. But we are actually talking about abstraction here, which was proposed like 15 years ago and actually in disk. And it's a primitive that tried to capture the broadcast power provided by typical wireless MAC layer. And here, one interesting setup in this kind of model is a minimal setup, meaning that actually in terms of participating nodes, the algorithm layer doesn't have that information. So that's hidden underneath, which is handled by the MAC layer. And in terms of algorithms, what you can do is that you can broadcast a message, and then once it's complete, you get an acknowledgement from the MAC layer, say that, hey, it's completed. Or you could receive a message in an event-driven fashion. And here's this illustration. You have like three nodes. Suppose replica 1 broadcasts a message, and at the end, even though it doesn't know that R2 and R3 exist, it gets an acknowledgement say that, okay, everyone so far has everyone has not crushed so far has received this message. And like some extra assumption, more formalized way is that it's asynchrony, meaning that everyone message and the node can proceed in arbitrary speed. And we have a typical eventual delivery. If I'm not crushed, eventually everyone will receive the message. And this MAC layer acknowledgement is that I get a guarantee from the MAC layer saying that everyone received my message. And again, this is an illustration. I already mentioned the one on the right-hand side, and then on the left-hand side, it's more typical point-to-point network. You do unicast, but there you need to have explicit acknowledgement from others so that R1 knows actually R2 and R3 receive that. But on the right-hand side, everything is abstract away and is guaranteed by this acknowledgement. And there are some prior work on this MAC layer and non-fault tolerant test. And in terms of crush failure, and these two are the most relevant work. First thing is that even though this MAC layer thing is sounds very strong, but actually you cannot achieve deterministic consensus. And later on, again in disk, it's Newport and Robinson, they provide like two randomized consensus algorithms. So the first motivation of our work is that what about other primitives? And this work, we find out that actually the power of this MAC layer is very related to this thing, this shared object called store and collect object. And actually building on top of our simple algorithm, we can implement many useful primitives. That's with consensus number 1 on top inside abstract MAC layer. However, not all of the tests or like object with consensus number 1 can be built inside this model. And we prove that set consensus actually is impossible to achieve. And then we improve the storage complexity and then time complexity, like in terms of randomized algorithm. In particular, we improve the time complexity from O(n) cube log n to O(n) log n. All right, so the first test is about store collect. So what is a store collect object? it has like two API. The first is that you can store some value into the shared object, and then collect is that you want to observe or you want the object to return the most recent view. But here the view, the guarantee actually is very weak. You only need to satisfy regularity, not even linearizability. And here's some example. Suppose R1 try to store something, and then upon the completion of this store operation, everyone should store this X inside their own view of the object. And then once this completes, suppose that R2 want to collect something, and then obviously it should return X because that's the current view of that what's inside the object. Now let's get it more interesting. Even if like R2 trying to do the collect during the process of X, the R1 trying to complete in the store, and here it can return X, and even if like they are overlapping, but like in terms of regularity, this is fine. However, if this happen, like say R3 want to collect something and it returns empty view, then this is not good because this does not satisfy regularity, because at this point R2 has already observed X, and every operation, every collect operation after that should also return X. So in this example, it's not regular. Okay. Then in terms of abstract make there, how do we store that? And again, I'm showing this figure to kind of remind you what kind of guarantee is provided by this broadcast primitive. And then if you think about it a bit, actually it's pretty simple. I just say that, hey, I'm going to store X inside the object, and then I just let the message to be X. And the reason that it works is that after R1 get this acknowledgement, then actually everyone that has not crushed yet will get this message. Okay, so that's stored. Then in terms of collect, it's slightly more complicated because that actually here, if someone crushes, actually you are going to have inconsistent view like this. And this is possible because that when R2 try to store Y inside a shared object, it might crush. And in this case, R1 receive it and R3 doesn't receive it. However, we can again rely on this make layer broadcast to make sure everyone that has not crushed yet has the same view of the object. So in this case, R1 just said that, hey, my current view is XY, then everyone should update your object to my view. And then after the make layer give you the acknowledgement, then everyone that has not crushed yet will have the same view, so you can return XY in this case. And then based on this store collect object, then actually we can stack in the prior construction, which is by Atiyah and others that I published in SSS 20. And then there they provide a way to build like counter set atomic snapshot object and multi-writer atomic register on top of store collect in a fashion that you don't actually need the acknowledgement from a quorum or something. So that fits with our model. And now the second part. We talk about the randomized consensus. And then here, we want to have anonymity because that fits with this minimal setup of abstract made there. And then all the prior work actually requires some knowledge of the identity. And then the other thing is that we want to improve storage efficiency because that prior work actually require like kind of counting on like different identities so that they can decide when to terminate, and then that gives you at least like n log n of storage complexity, and we want to avoid that. So what's a randomized consensus? We need to have three properties. First, everyone needs to output a value with like probability 1, like eventually output it. And validity is that output must be some input, and agreement, everyone must have the same output. So the big picture of like our solution is based on the protocol proposed, or the framework proposed in distributed computing 2012, and it's like proposed for the shared memory model. There, they oscillating atomic commit object and consolidator object. Like you just like change it from one to the other, and then you can get the agreement. But in that framework, they need to have a no identity, and then they need to have knowledge of the network size n, and we want to avoid that. And we have like 3 techniques to kind of fix the issue. The first one, to save the space, we use make broadcast, which is like similar to what I show you about how we implement the store collect object. And in that case, we can kind of build all these different objects from the shared memory model inside abstract make layer model. And then the second one is that we don't know n, but we just like double the estimation size of n, and eventually we can get there, and then we will have a nice property to ensure that we can actually agree. And then the third one is that we don't want to kind of reuse all the objects, because we want to save space. So one thing we do is that we can jump to the future object if we see something from a higher phase, and then that's how we can reuse object without kind of redundant thing. All right, so let me quickly talk about like what is this consolidator and adopt commit. So consolidator is that the purpose of it is to help everyone to reach agreement with a non-trivial probability. And if you are from the message passing world, that's like kind of you do a coin flip. Of course, there are other type of conciliator, but in this world, we rely on the coin flip thing. And then the adopt commit object is to use that to detect when it's safe to output something, when it's safe to commit. And then there are 2 possible outcomes. The first one is that yes, it's safe to output some value. Then in this case, the output of this object will be some value. Then you can the node just like commit to that value, and you will not change. However, for some nodes, it might see inconsistent information. It might not learn everything it needs to know. So then you say, okay, I cannot commit, but I will output some value. And then this value cannot be arbitrary thing. It needs to be some valid value. And the reason that it cannot be arbitrary value is that because some nodes may say, hey, I can already commit. The other set of nodes say that I don't know what the value that I can commit. In that case, you need to make sure that the nodes that they don't commit, they still pick the value that is the same as the nodes that have already commit. So later on in the next phase, they can all agree on the same thing and satisfy the agreement property. So now here is our exponential algorithm. And first we broadcast the value. So that this thing, that everything I remember from this framework is that we use adopt commit and then conciliator, that's one phase. And then the algorithm proceed in multiple phases until the adopt commit object say that yes, everyone has agreed, then we can commit. All right, so the way we do that is first we propose a value, and then we try to learn what each other's propose something, and then if I'm the first one to propose something, I don't need to update state. But if I have observed some others already propose something, then I should update my state value in this phase to that value. And then the next one, I should propose the proposal that I learned so far again. And then I need to check whether there's any proposal from a higher phase. If yes, any future value should be better than what I'm currently know, so I jump to that. And then if no, then if there's no proposed value that is different than mine, that's where the adopt commit object say that, okay, you can commit, then I can output. So the first part is implementation of adopt commit object inside abstract make layer. And then the next part is the conciliator object. So this run to value is the output of the adopt commit value. And then I just exchange that. And then if everything I observe is actually the same thing, then actually I can, if I receive something from the higher phase, then I can jump again. If no, then I need to say that, hey, do I need to update my local state? Then here I use a local coin flip to decide what my next value to be. And this is similar to the Benno's idea. And then the improved algorithm is that we can change local coin flip by doing some communication to make it biased so that in each phase we have a constant non-trivial probability to agree. And then that's how we can get to O(n) log n time complexity. Roughly speaking, we need to have a O log n phase to reach the right estimate size of n. And then that's because of the doubling techniques. Every phase we fail, we double the size, and we will hit the right size in log n step. And then once we hit that, we will need constant run to reach agreement. That's because of property of bias coin. And then to do all this, it's like O(n) expected broadcast in each phase. So if you do the calculation, it get to O(n) log n. All right, so the summary is that the first part, we show that this abstract map there thing is related to store object collect, and then we show how to do a wave-free implementation for many objects like with consensus number 1, and then we present a randomized algorithm with improved complexity, and we also have we also have other two approximate algorithm that I don't have time to talk about, but it's inside the paper. All right, that's all. Thank you.
Thank you, Louis. Questions? Okay. Is there a matching lower bound to your?
That's a very good question. Our conjecture is that O(n) log n actually is a lower bound, but right now we don't know how to prove it yet.
Okay. Thank you.
All right. Thank you.
After lunch.
afternoon. So welcome to this afternoon session on agreement and replication. So we have a 2-hour session, a lot of exciting talks. So our first speaker is Jovan Komatovic from EPFL, and he would talk about efficient signature-free validated agreement.
So hello everyone, great to see you all here. So yeah, today I will tell you a bit about our paper called Efficient Signature-Free Validated Agreement. This is joint work with my great co-authors, Pierre, Seth, Ayaz, Rashid, Manuel, and Igor. Okay, so let me first tell you a bit about the problem we want to solve and about the results we actually achieve. So in this paper, we are interested in the MVBA problem, so the multi-valued validated Byzantine agreement problem. So here we have a set of processes, right? Some of the processes might be Byzantine, malicious, we will call them faulty, other processes are correct. There are up to T faulty processes and there are N processes in total. And the goal of this MVBA primitive is to ensure agreement on a single value, okay? Now, we have that the proposals made by correct guys are going to be valid according to some predetermined logical predicate, and the MVBA primitive also ensures that this decision V out is also valid according to the same logical predicate. So this is why this problem is called validated Byzantine agreement. Also, we consider that the values are of size L bits, and the goal of our work is actually, and what we want to also study here is we want to study the MVBA problem without any signatures. We want to study the MVBA problem without randomness, so we are interested in deterministic solutions, and we are interested in solutions that are synchronous. So we have a known upper bound on message delays throughout the entire execution. And finally, what we aim to minimize here is the bit complexity, so the number of bits correct processes exchanged throughout the entire execution. Okay, so regarding our results, we actually here introduce 2 signature-free and efficient MVBA protocols. So the first one is HashX. This algorithm relies solely on collision-resistant hashes. It exchanges NL plus N cube kappa bits. And as I will say in a couple of slides, it's going to be optimal for big L, for L being belonging to omega N square kappa. The second solution that we propose is the error-free EXT. So this algorithm relies on no cryptography whatsoever. So it's going to be safe and live even against a computationally unbounded adversary. And it's going to have a bit complexity of NL plus N square log N bits. So as I will show in a couple of slides, this is near optimal for every L. Both of our algorithms are going to be optimally resilient, and both of our algorithms are going to be early stopping. So early stopping means that these algorithms are going to terminate in O of f+1 rounds, where f is now actually the actual number of failures and not the upper bound on the number of failures. Okay? Cool. So let me walk you through some history, some related work. So let's first start with the resilience for solving the Byzantine agreement problem. So there is this paper from 1980. I'm sure everyone here is aware of it. So this paper actually studies Byzantine agreement with so-called strong unanimity. So here, it is mandatory to ensure that if all correct processes propose the same value, then that is the value that is decided. And this paper shows that if you want to solve that problem without any signatures, you need to have n greater than 3t, even in synchrony. Also, there is this FLM paper from 1985, and they show the same resilience bound just for the strictly weaker problem of Byzantine agreement with weak validity, where weak validity states that if all processes are correct and if they all propose the same value, only then that value must be decided. Otherwise, we can always decide some default value bottom. So what does this mean? Well, this means that if we do not want to use signatures, we need to have n greater than 3t. Okay? Now, there is this, again, a very, very fundamental result in the field, the seminal Dolev-Raichuk lower bound, which proves that if you want to solve Byzantine agreement in the deterministic manner, then you need to exchange t-square messages. And this year at POTSI, actually, there was a paper that generalized the Dolev-Raichuk bound to include all the flavors of Byzantine agreement, including the MVBA problem that we are interested in this work. Okay, so again, what do we know? Well, we now know that if we want to solve Byzantine agreement, we need to exchange NL plus N square bits. So the first NL term simply comes from the fact that each process needs to to receive the decision, the decided value, and the n square term comes from these two papers that show that even agreeing on a single bit requires n square messages. Okay. Also, the Fish and Lynch paper shows that, if you want to solve Byzantine agreement deterministically, you need to have O of f+1 rounds. And indeed, if your protocol terminates in O of f+1 round, we say that the protocol is actually early stopping. So I just want to remind you that both of our algorithms are early stopping. Okay, cool. So now what we have here is a paper from actually DISC 2021. So this paper is a paper that solves Byzantine agreement deterministically without any employed cryptography, and it does it with near optimal bit complexity. So this is great. This is what we actually want to achieve. The only problem, the only missing thing with this paper is actually that this paper solves only Byzantine agreement with strong unanimity, so it does not solve the MVBA problem that we are interested in this paper. So here you can see that. Now, I just want to say something very briefly here. Actually, what you can do with this cool protocol that only solves strong unanimity, you can actually use it to implement what we call interactive consistency, which will then allow you to solve MVBA problem that we want to solve here. However, there is this multiplicative linear factor that you need to pay. So as you can see here, there is this n square L bit complexity that we would like to avoid. Okay. Also, this year at POTSI, there was a paper that that showed how to solve MVBA problem that we are interested in with near optimal bit complexity. However, this protocol uses threshold signatures. So again, this is everything that we want to obtain, but we just want to remove the threshold signature assumption. So I will just briefly, again, restate both of our solutions. So again, we have one solution, the HashX, that only relies on collision-resistant hash functions, and it's going to be optimal for big L. We also have this error-free X algorithm that is safe and live even against a computationally unbounded adversary, but and it's going to be nearly optimal. It's going to be near optimal for every L. Both of our algorithms are optimally resilient, and both of our algorithms are early stopping. Okay, cool. So before I briefly introduce our two solutions, I want to tell you a bit about graded consensus. So this is one of the primitives that we are quite excited about in our lab, and it actually plays the crucial role in both of our algorithms here. Okay, so interface of graded consensus, very simple, nothing you're not used to. So process can propose, process can decide. For example, a process can propose a value x, but now the big difference, for example, in comparison to consensus, is that processes decide a value and they also decide a binary grade. Now, this binary grade simply represents the level of confidence the process has in its decision. I will explain this in a very second. So you can see this visualization, right? And here what we have is we have four values, V0, V1, V2, and V3. And this red inner circle is going to represent low confidence, and this green outer circle is going to represent high confidence. So let me show how this visualization helps with understanding of the graded consensus primitive. So the first property of graded consensus primitive that we care about is consistency, and this consistency property says the following. Graded consensus allows processes to disagree as long as all processes decide their values with low confidence. So what does this mean? This means that graded consensus is a strictly weaker primitive than Byzantine agreement. Here, disagreement is allowed, but only if correct processes decide their values with low confidence. So here you can see that there are three processes, they disagree. There is a guy that decides V0, V1, and V3, but it's okay because they all decide their values with low confidence. However, consistency also states the following. If there is somebody that decides with high confidence, there is no disagreement. So here, as you can see, there is somebody who decides V0 with high confidence. Everyone else needs to now decide V0 according to the consistency property. So indeed, these two processes on the left decide V0 with low confidence, but still, the important point is that there is no disagreement. Okay. The second property that we care about is strong unanimity. So this simply says that if all correct processes propose the same value, that is the value that is decided, and it's going to be decided with the maximum grade, with the high confidence. So if everyone proposes V0, everyone decides V0 with high confidence. Okay, cool. So what we actually do in this paper is we design two graded consensus algorithms. So we designed one algorithm for the hash-X Byzantine agreement protocol and one algorithm for the error-free X Byzantine agreement protocol. So for hash-X, we actually build an algorithm that is used only for agreeing on a hash value, concretely on a Merkle root, and it's going to exchange n-square bits. It's going to exchange n-square kappa bits, where kappa is the size of a hash value, the size of a Merkle root. Now, you can see this, very short algorithm here, and the point is that we actually relied on the paper from 2023 from Mattia and Welch, and on their implementation of asynchronous crash stop graded consensus primitive to actually build our algorithm for synchrony and for Byzantine failures. Okay. As for this graded consensus that we want to implement for error-free X, here we wanted to build a graded consensus that is going to work on long values and is going to achieve the bit complexity of nl plus n squared log n. And in order to build this algorithm, we are actually relying on this cool protocol that you have seen a couple of slides ago, the protocol that was published at DISC 2021. So when we were while we were reading the cool protocol, we figured out that you can take and extract a primitive that we call reduce cool from that algorithm, and this primitive is actually very useful to building Byzantine agreement. Graded consensus. The point is that this reduce cool algorithm, intuitively speaking, reduces the number of values held by correct processes to some stages. So at the beginning of this reduce cool primitive, every correct process will hold its value, but then in each iteration, in each phase, in each stage, we will remove potentially some of the values such that at the end, there can be at most one value that survives. Okay, so if at the end of this reduced cool primitive, there is process I with value Vi, and there is process J with value Vj, these two values are going to be the same. Importantly, it can also happen that not a single value survives. So by leveraging this reduced cool primitive, we are actually able to design this graded consensus algorithm in a very, very simple way by reducing it simply to graded consensus on a single bit, as you can see here. And yeah, I encourage you to take a look at our paper for more details about this. Okay, cool. So I will finally tell you a bit about our protocols. So first, I want to give you a very simple solution that utilizes graded consensus, but one which is suboptimal. So this solution is going to operate in views like Tendermint, PBFT, hot stuff, so I'm sure that people here will easily understand. So we will start in each view with an instance of graded consensus. Processes will propose something, they will decide something with some grade. Then we will have the leader, and the goal of the leader will be nothing than just to take the value it decided from the graded consensus and just broadcasting, just spread it around. And then we will have the second graded consensus primitive in this view. Now the question is, what is the value processes should propose to the second graded consensus primitive? Well, we have this very, very simple logic. If I am a correct process and I decide that with grade 1 from the graded consensus, from the first graded consensus, I keep my value. I ignore the leader's value, and this is the value I'm going with to the second graded consensus algorithm. Otherwise, if I decided with grade 0 from the first graded consensus, I just go with the value that I received from the leader. Now, if I decide something with grade 1 from the second graded consensus primitive, this is the value I'm going to decide from the entire algorithm. Okay, cool. So what's the problem with this solution? Well, the problem with this solution is the following. This solution ensures termination only when we reach a correct leader, right? Now, before we reach a correct leader, we can actually execute linearly many leaders, right? So this simply means, given that each view has of NL bit complexity, because of these two graded consensus algorithms, we will have n square L bits in the entire algorithm. So this is not something that we want. Okay, so what can we actually use to combat this and to reduce this n square L bit complexity? Well, we can use this, I would say, very well established paradigm, disperse, agree, retrieve, that is designed for the purpose of reducing the bit complexity in Byzantine agreement. So the idea is very simple. First, each process disseminates its value in a smart, efficient way using erasure codes like Reed-Solomon symbols, and then it obtains what we call a proof of dispersal. Now, this proof of dispersal guarantees two things. The first thing is that the value that this proof of dispersal corresponds to is valid, and the second one is the value that corresponds to this proof of dispersal can be retrieved during the retrieve phase. Now we use an MVBA algorithm, the agreement phase, to simply agree on a single proof of dispersal that we are then able to reconstruct using the retrieve phase. Now, this POD, this proof of dispersal, is usually a cryptographic certificate. You can think of it usually as a threshold signature on the digest of a value, like a threshold signature on the Merkle root of a value built over the Reed-Solomon symbols of that value. So that is great, but the question is now, obviously, because this requires signatures, how can we adapt this in the non-signature world? So what we actually do is we actually build what we called implicit PODs. So as I just mentioned, these explicit PODs are cryptographic proof. They contain cryptographic proofs. They're like a cryptographic certificate, and they are self-contained, right? If I have this explicit POD, I could give it to somebody outside the system. That guy can take a look at what's going on, and it can verify if the POD is valid or not. In this case, what we do for our solution is we implement this, as I said, implicit PODs that do not have this guarantee because they do not have any cryptographic proof of its validity or not. It's only that the design of the protocol itself guarantees that given a POD, you can actually take the value that corresponds to it, the value being valid, and actually rebuild it. So the implicit PODs that we are actually utilizing are not self-contained, and you cannot give them to an external entity that can then verify if they are correct or not. So the idea behind our first algorithm is simply to use this disperse, agree, retrieve paradigm with these implicit PODs to solve the problem in an efficient way. Okay, so again, I will stop here for the first algorithm, and you can take a look at our paper for more details. And I will briefly talk about error-free X. So again, this is our algorithm that uses no cryptography whatsoever. Yes. And here, what we are trying to do is we are trying to build on these two seminal papers from the 90s and this follow-up paper from 2021 from also at DISC. So the goal here is that we want to utilize again, the graded consensus primitive that we saw, and we want to utilize the classical divide and conquer technique. So the goal is, if we want to solve a problem among n processes, we will separate those n processes into two disjoint groups and then try to solve the problem in a smaller group. Now, if you put our graded consensus implementation with NL plus n square log n bits, you actually get the bit complexity of this solution that we want. Now, the only missing thing here is the fact that this is not early stopping. This is simply not early stopping because each of these attempts needs to be run for the maximum duration possible before we can abandon it if it is, for example, overly corrupted and quote-unquote it's broken, right? So in order to actually add early stopping on top of this, what we are doing is we are focusing and we are revisiting this paper from POTSI 2022 that achieves early stopping and optimal quadratic bit complexity, but now only on binary agreement. And we are able to by following the similar structure, we are able to modify their structure in order to obtain early stopping for long values while preserving our bit complexity. The key idea here is adding this finisher primitive, which is there to detect if agreement has already been reached, so that we do not need to run the second part of the algorithm and then save some time. Okay, cool. So just to conclude, we presented two papers here. They are both signature-free. They are both optimally resilient, and they are both early stopping. One uses only collision-resistant hashes. The other relies on no cryptography whatsoever. As for the open question, obviously, can we improve the bit complexity of these solutions? Concretely, I want to mention that for HashX, we can actually trivially modify this algorithm and obtain slightly better bit complexity than the one that we presented here, but it's still not super satisfactory. And obviously, for error-free X, the question is if we can remove the multiplicative logarithmic factor. Yeah, thank you for your attention.
For questions. Any questions? Okay, so I missed one thing. What is the model you're assuming? Is it synchrony, partial synchrony?
It's synchrony.
It's synchrony.
Synchrony, yes.
Right.
Full synchrony.
So why then you use views? You can just have rounds, right?
Yeah, but I mean, yes. So a view is just a set of rounds. Like it's going to be like 7, 8 rounds with but the important point is that we are calling them views because there is a predetermined leader of that view.
Okay.
And yeah, that's. But yeah, of course, they're rounds. Yeah.
And now you have a essentially matching result for a partial synchrony as well.
Yes. It's a follow-up. Yes, it's a follow-up
Next
result
year.
to this, where we actually studied the similar problem, but now in partial synchrony, and we are asking if we can solve if we can solve the problem without any cryptography and still match the dollar-Reichshoek bound. Yeah.
Okay. Yes, please.
Mm-hmm. Yes. So the point is the point that we are doing there is that throughout the so let me give a bit more detail. So in this Hashext, actually the dispersal and agreement phase are slightly more connected, so they are not clearly separated like in the traditional disperse their paradigm. So the point is that at some point there you will again, it's going to be a view-based algorithm. It's going to have leaders, and the idea is that the first correct leader, because we need to know that its value is valid, it will need to send the entire value. But our hope is that this will only be done by the first correct leader, so that we do not violate the NL bit complexity that we want. And then after this, potentially, if needed, correct processes will only work on the Merkle root of that value built over. They will take the value, they will encode it in the Reed-Solomon symbols, then they will build the Merkle root, Merkle tree, and then they will only play with the Merkle root. Yeah. For the dispersal, for the retrieval phase, we actually need to verify that indeed the Reed-Solomon symbol that you are giving me, that I should use for reconstructing, is actually the one that corresponds to this Merkle root that we actually agreed upon. Yes, exactly.
Right. So, no question. Okay. So let's send the speaker again.
Thank you.
Right. So our is Victor Schupp from Off-Chain Labs, who will sing us a song of simplex.
There will be no singing. I'll explain the title momentarily. So I'm going to be talking about atomic broadcast. So just to get everybody on the same page here, as usual, we have a committee of N parties, at most T of which may be corrupt, Byzantine, faulty, take your pick. Transactions are somehow submitted to the committee. I'm not going to worry so much about how that happens. The job of the committee members is to order these transactions, and we have the usual safety and liveness properties. Safety is that all honest committee members agree on the same ordering, and liveness is, you can go down a rabbit hole defining exactly how that should be defined, but it just basically means the protocol shouldn't get stuck. You can tack on notions of fairness, censorship resilience, but I won't be worried about those here. And then, of course, and just to be clear, this is an ongoing process, right? This is a never-ending process, like in a blockchain world, not just a single one-shot consensus, like in the last talk, MVBA is just a one-shot consensus. So we have our usual menagerie of communication models. I'm going to assume secure point-to-point channels, and you can make various assumptions. The most restrictive, as in the last talk, was that they're synchronous, so that there's some known upper bound on the network latency. This is, in my opinion, not very realistic, just editorial. It's surprising maybe how many papers get written in my world, more in the cryptography world, and the multi-party computation, and that there's a ton of papers. And one of my pet peeves is, just because I have the stage here, is that many papers are written and don't even say that what their synchrony model is. And it seems like the default implicit one is synchronous, which, okay, end of rant. Asynchronous, I think, is the way to go if you can get there. The idea here is that safety and liveness should just always hold without any synchrony assumptions. And while it's not very practical, I mean, but there's been a lot of progress made in the last decade or so on making these things practical. So, but even still, the asynchronous protocols that are out there today for this problem have pretty good throughput that can do as well as any synchronous or partially synchronous protocol, but their latency is still leaves a little bit to be desired. So even now, the kind of the pragmatic compromise is partial synchrony. So we assume that we only demand liveness holds during periods of synchrony, but safety should always hold. And like I said, this is a pragmatic compromise, and it's what I'll be focusing on in this talk. Okay, so in the beginning, there was PBFT, and there's been a gazillion, it was introduced 25 years ago now. There's been a bazillion papers written on this protocol and a bazillion variations on it. So let me just kind of highlight a few things. Well, first, just this is the first practical protocol in this area. It's optimally resilient, withstanding up to T, strictly less than N over 3 corrupt parties, and it's optimistically responsive, which is a nuance that sometimes people worry about in the sense that there's no, as long as everything is going well, the protocol will run at network speed. There's no artificial slowing down or hitting the brakes to slow down the protocol. PBFT employs a stable leader, and from time to time, you'll have to change the leader, especially if the leader is crashed or corrupt and not behaving correctly. And as everyone here knows, then you have to go through a kind of a view change protocol to change the leader. And as is well known, one of the headaches of PBFT is that this leader change protocol is somewhat expensive and I would say somewhat complicated. Also, as has been noted, the leader can become a bottleneck in terms of network bandwidth. And in the last number of years, there's been a lot of papers that kind of point this out, also with some actual data, which I find interesting. So there's this honey badger paper that came along a while ago. It works in the honey badger itself as an asynchronous protocol, but they wanted to compare themselves to the classic PBFT. And you can see here, this measures, so on the x-axis, we have the number of nodes from 8 up to 64. And on the y-axis, we have throughput. And you can see for PBFT in blue here, it's falling sharply as the number of nodes increases. And they're very proud of their protocol. It doesn't fall nearly as quickly. Similar observations were made a bit more recently in other papers, including a nice paper that on a protocol called MIR-BFT. You can also see here, again, we have on the x-axis the number of parties from 20 up to 100, and here's throughput. And you can see the throughput on this yellow line dropping really quickly as the number of parties increases. And here it's quite clear. It kind of, well, believably, it looks like it kind of drops as 1 over n as n increases. And I found these papers and others like them interesting because they address an issue that oftentimes gets overlooked. Just very simple, bandwidth limitations. When you have a leader in a protocol, he has to disseminate a block or a batch of transactions to everybody else typically. And unless you're going to do something like a gossip protocol or something like that, which has its own problems in terms of increasing the latency and creating possibilities for attack vectors if your neighbor set is too small and you're only talking to corrupt parties. So if you just take the most naive way of implementing something like PBFT or any leader-based protocol where the job of the leader is to disseminate a batch, then what you're going to do, I guess, is just the leader will send each batch over one, say, SSL channel to every other party, transmitting the same data n times to n parties. It's kind of the only way to really do it if you're not going to do something like an overlay network or a gossip protocol or something like that. And so that's where this 1 over n drop in throughput comes from, is simply the bottleneck just becomes the leader disseminating the same block to all the other parties. And that was measured empirically in these papers and others. So what I want to talk about, and I'll come back to this issue a little bit later. so in this paper, I wanted to look at leader-based protocols that didn't have these limitations of complex and slow view changes and the leader bottleneck. The starting point for this work was this protocol that came out in TCC last year. It's called Simplex, not to be confused with that other algorithm. I'll just say this off the top. It's a beautifully simple, elegant, and easy to analyze protocol. So I'm singing its praises, hence the title. And I think it's so great that if you're like teaching a class and you're going to just teach one protocol on leader-based, partially synchronous protocols in this area, you might as well teach this one. It's just that simple and that elegant. And I don't see any, and it also has very good performance metrics. So it employs rotating leaders, so you can change the leader in every round. It has excellent block time, so you can start anew when things are going well. A leader will publish a new block every 2 delta time units, if delta is the network latency. And the commit latency, the time from the leader proposing a block to it being committed by all parties in the optimistic setting when everything is going well, is just 3 delta. Like PBFT, it's optimally resilient and optimistically responsive. And like PBFT, if implemented naively, the leader becomes a bandwidth bottleneck. Now, this paper was published in TCC. They didn't really consider too much. I mean, they did look at latency issues, but they didn't really talk about communication complexity or throughput or such things in any detailed way. One reason is that the protocol, despite the fact that I'm singing its praises, one of my critiques of the paper itself is that it's presented in a very underspecified way. Or if you actually read the paper, you'll see that the protocol itself has the leader like broadcasting the entire blockchain from Genesis to every party in every round. So that's clearly not practical. So one has to think a little bit about how to like specify that correctly and in a simple way and in a way that you get nice properties. So one contribution is to take the Simplex protocol and adapt techniques that were presented or briefly mentioned in the previous talk about asynchronous verifiable information dispersal, or AVID techniques. These are techniques that use erasure coding and maybe Merkle trees to do the kinds of things that people have been doing quite a bit in different protocol settings for the last almost 20 years. So yes, you could say, well, it's pretty easy to just adapt these techniques, and it's true, it's not too hard, but you have to be a little bit careful about doing it in such a way that you don't mess up the block time and commit latency properties. Then you want to avoid introducing any extra latencies into the protocol. And what this does importantly is it eliminates the leader bottleneck. So the communication complexity becomes linear, and more importantly, it's balanced. So every party, including the leader in every round, is sending out the same amount of data onto the network. So it balances out the communication nicely. It also maintains a simplicity and efficiency of Simplex. So like I said, the block time and commit latency doesn't increase at all. And because of the balanced block dissemination, it much improves the throughput given bounded bandwidth. And a lot of the underspecified details in the original TCC paper are filled in here. So that's the first contribution, kind of bolting on AVID techniques to Simplex, specifying the details of Simplex, and then showing how to get better throughput by doing so. The second contribution is to introduce a stable leader variant. So Simplex, as designed, rotates leaders every round. That's actually important. There's some nuances that you have to be careful of in creating a stable leader variant. And you want it to be the case that if the protocol for changing the leader is really no more expensive than the usual round changing in the rotating leader variant of Simplex. So it costs almost nothing to throw out a leader. But you want to make sure that you throw out a leader as soon as they're unresponsive and not wait too long. Introducing a stable leader has a couple of advantages. One is when you get down into the details of how you might implement this, it allows for more pipelining, which can give you better throughput. I won't have time to go into how exactly that happens, but the basic idea is that the leader kind of knows he's an honest leader, and so he doesn't have to wait around to see what block was decided upon in the previous round, because he knows what it was, because he broadcast that block. So he can start transmitting the next block and kind of faster than he could if he were just some rando leader coming in following some other rando leader, right? So that way you can do some more pipelining and get better throughput. Also, this allows you to quickly move on from crashed or corrupt leaders. I mean, stable leaders in general have this advantage, right? If you have if some percentage of your nodes are crashed, then, and if you're constantly changing leaders, then one out of every, whatever percentage of the nodes are crashed, you're going to like stall and change and just wait for timeouts and whatnot to move on. This way, when you get a good leader, you're going to run for a while, and so the so the total amount of time you spend stalled and doing nothing, recovering from crashed leaders, becomes a much smaller percentage of the whole. And the downside of stable leaders, one big one, is that you kind of lose some fairness properties there, because a stable leader is there for a while, and if he's malicious, he can be kind of performing his job, but maybe censoring some transactions. Maybe you can mitigate against that. The third contribution is to actually adapt some even better AVID techniques than what have traditionally been used over the years. Just this past year, in joint work with Thomas Locher, we developed some new techniques that actually allow you to, we developed these ideas for reliable broadcast and presented some variations of BRCA broadcast, and basically allow you to double the throughput of that. And these can be adapted, but it's a bit tricky, and it takes some care to apply these to dispersed simplex. And this leads to, unfortunately, a somewhat more complicated protocol, because these techniques are a little bit messier. But it can double the throughput of the protocol. So it's a trade-off. Some performance estimates. So I tried to do some, I didn't implement a full system, but I tried to make some assessments of what's going on here. So this is based on some micro benchmarking, some realistic network assumptions, and then just some back-of-the-envelope calculations. It's not a fully integrated systems test, so take it all with a grain of salt. So I start off with about, I take n to be around 100. I assume 1 gigabit per second network speed, so everybody can upload and download at this speed. And I'll assume that it takes 100 milliseconds for a message to be transmitted from any one node to any other node. Assuming commodity hardware, one interesting thing is erasure coding. If you haven't been paying attention, there's been a lot of really impressive improvements in this space just in the last few years. There's been a few very nice papers that were written, and I stumbled across all of this on GitHub. And then thanks to GitHub and the ethic of code, free code sharing and whatnot, there's been several iterations on this. So this is a beautiful library here that just for any that works on 2 minutes. Okay. Blah, blah, blah. Stop, go. Some throughput and latency things. Dispersed simplex, based on all of this, I get a throughput of 18 megabytes per second, so however many transactions that is, with a commit latency of half a second. If we use the stable version with the extra pipelining that I told you about, we get half a second. Better AVID, the more advanced AVID techniques, we double the throughput again. Commit latency stays the same. If we compare to hot stuff too, I'm really out of time, but I have to make a little editorial about hot stuff too and their ilk. A lot of papers in the literature seem to be focused on avoiding this all-to-all message pattern, and without any regard to like how you're actually disseminating blocks. And if these blocks are at all large compared to n, it's just a misguided task. I mean, you're just kind of like optimizing the wrong thing in terms of how these things work. So if you look at the throughput under the same constraints I have here, it's going to be about 1 megabyte per second with a lot longer commit latency. Conclusions, the leader is the bottleneck of PBFT, and you can get rid of that, and that's caused by unbalanced block dissemination. We can eliminate the leader bottleneck without eliminating leaders, by the way. So this paper discusses how you can do that. There's a whole other line of work, based on DAG-based protocols, which are very cool, and there may very well be nice for other reasons, but eliminating the leader bottleneck is not, I don't think, the main reason you want to go after DAG-based protocols. Because if you do the block dissemination correctly, for leader-based protocols, you don't have those problems. And also, like I said before, reducing the communication complexity without balancing the communication doesn't really improve overall performance. And in fact, both the MIR-BFT papers and a lot of the Narwhal and Tusk DAG-based papers kind of look at that issue and give empirical results as well. So so you should really look at the maximum amount of data that's sent out by each party as a measure of communication complexity, not the sum over all parties, because that really captures the max captures the bottleneck effect. And I'm done, and I'm sorry if I went too long.
Any questions? Okay, I have a question. So you did a great job kind of building suspense about that eliminating leader bottleneck, but your protocol is still leader based. So what was the trick to?
Just erasure coding. I mean, just don't send. You want to just balance the communication so the leader isn't doing all the communicating. So, and that's not a new trick, but adapting it to this protocol without increasing the latency and maintaining all the other nice properties was maybe an interesting exercise. And also, yeah.
Okay. Yes, please.
Yeah, but it would be. Yeah, I can't measure it. I mean, if yeah, it's kind of just underspecified, so it's hard to make a fair comparison. But it would be a factor of n. If you just assume the most naive thing, it would look a lot like hot stuff, basically.
Can you maybe comment on your pipelining technique? Is it similar to hot stuff, or it's a different kind of pipelining? Because obviously you have this problem that you may create holes if you pipeline, right?
I think it's similar. I think the pipelining is similar in principle to what happens in hot stuff.
Okay. Right. So let's thank the speaker again. Right. So our next talk is going to be a recording because the speaker can't come due to the visa complications. So for that reason, any questions after the talk? Right.
Are we ready?
Yeah. So this is the next talk, and this is a brief announcement. Best possible unpredictable proof of stake, and the speaker is
I don't remember.
presenter, yes, Zhenghao Lu from Shanghai Jiao University.
Unpredictable proof of stake. This is a joint work with Lei Fan, Jonathan Katz, Fu Hai, and Hongsheng Zhou. Cryptocurrencies have proven to be a big success. These protocols are run by a large size of nodes using the POW consensus. The miner who discovers a solution to the hash-based POW puzzle becomes the block creator. However, since the miner would continuously searching the solution, the POW consensus requires lots of computing power. For example, the electricity consumed by Bitcoin exceeds that of an entire country. Using resources like coins to secure blockchain is desirable. If successful, the new system would not rely on extensive computing power for security. Indeed, using coins to construct cryptocurrency has been considered. We roughly categorize these protocols into two types. One follows the design style like Bitcoin, while the other is based on BFT. Examples of Bitcoin like POS include Stonewhite and others. They are non-interactive and have low communication. Our work focused on Bitcoin-like POS protocols. We first examine the security properties that POS protocols need to satisfy. One important property is predictability, which means that players are aware that they will be selected to generate blocks before they actually generate. Attackers will use it to carry out self-mining or bribery. Ideally, we want POS protocols to achieve the best possible predictability. That is, beyond the next block, no one should be able to predict who will generate the subsequent blocks. Other fundamental security properties have been defined in previous work, such as chain growth and common prefix. Our first result is an impossibility result. We show that for any single extension POS protocol that achieves the best possible unpredictability, it cannot be secure if the honest players control less than 73% of the stake. To explain this result, we first need to clarify what a single extension POS protocol is. Assume an honest player has a local train set. First, he will select the longest train. Then, the player will attempt to extend it. Note that in each round, the player will only attempt to extend one train. All existing Bitcoin-like POS protocols can be classified as single extension protocols. However, when a player is malicious, he can carry out any unconstrained attack. For example, he can attempt to extend every train. Unlike POW, extend trains in POS is cheap. Therefore, the attacker can easily do so. We show that if an attacker attempts to extend all trains, his stake would be amplified by a factor of E, where E is the natural logarithm. Based on this fact, we can finally prove our impossibility result. The natural question arises, can we overcome the impossibility? That is it possible to obtain a protocol that achieves all security properties with a smaller fraction of honest stake? That is the Chinese idiom called 以毒攻毒, which can be translated to using poison to cure poison. It means to counteract a negative situation using a similar strategy. In fact, if we require honest players to adopt the attacker's strategy, attempting to extend all trees, then only 51% honest stake is needed. However, such solution is inefficient. Our novel design leveraging the d-distance greedy strategy enables the trade-off between efficiency and security. We first give the definition of distance between two trains. Given two trains C sub 1 and C sub 2, the distance between them is defined as the smallest number L, such that removing the last L block from C sub 1 results in a prefix that matches C sub 2. For example, assume we have two trains C sub 1 and C sub 2, then the distance between them is 3. Then we define the d-distance greedy strategy. A player using this strategy would extend every train if the distance to the longest train is less than d. Again, we give an example. The number marked on each block represents the distance from the longest train to the train ending with that block. If d is equal to 1, then the honest player will try to extend blocks b sub 3, b sub 4, and b sub 4 prime prime. This slide shows the entire process of our protocol. In short, in each round, a player attempts to extend multiple trees. By employing a novel analysis framework, we derive upper bounds on the proportion of honest player utilizing a greedy strategy. We find that if d is equal to 50, then we only need 57% stake to be honest. More results can be found in our online version. Thanks for watching.
Right. Our next speaker in this session is Alexei Gotsman from IMDEA Software Institute, and he will talk about vertical atomic broadcast and passive replication.
Okay, thank you very much. And this is joint work with Manuel Bravo, who's over there, Gregory Chokler, who somehow managed to chair the session with his own paper, and Alejandro Nasser, who should be somewhere there, and Christian Roldan from IMDEA. Okay, so I'll be talking about how to implement fault-tolerant services, and as we all know, we cannot do this using just one computer, right? Because what if this computer fails? And the solution is to replicate them, so run multiple copies of them.
So the classical way of doing this is state machine replication. It's also known as active replication. In this approach, you define the service as a deterministic state machine. And when the clients submit commands to be executed by this service, you propagate commands to all replicas using atomic broadcast. And this can be implemented, say, using Paxos. And so because atomic broadcast ensures that each replica, all the replicas get the client commands in the same order and the service is deterministic, then all the replicas will behave the same. And so in the end, you'll get a linearizable service that behaves as though it was running indeed on a single reliable machine. And of course, there's a classical lower bound saying that to do this, you need 2f+1 replicas if you want to tolerate f failures. So this is the classical story that we all know. There's been tons of papers on Potsi disk about this. But the practice is actually often quite different. And the issue is this 2f+1 is kind of expensive. So in the cloud nowadays, the cloud providers run tons of these services. Right, and all these machines cost money. And in principle, f+1 should be enough to keep the data durable. All you need to do is to, when you execute a command to update all the replicas, right, then even if f of them fail, there is still one that survives, right? So in principle, it feels like f+1 could be enough. Now, upon a failure, you would need to then reconfigure the system, because if you have to update all the replicas to execute a command, then a single failure would block your system. So reconfiguration here is the process of changing the membership of the system. And unfortunately, to do reconfiguration, you need consensus because you may have multiple processes trying to reconfigure the system. And for this, you cannot get away with f+1 replicas. So of course, we can't beat the lower bound. Now, fortunately, there is a solution out of this conundrum, which is what's called the vertical approach. So you structure your system into two layers. You have the replica storing the actual data, and there are f+1 of these. And then there is the configuration service that only stores the metadata describing the membership of the system. And this can be a service in practice, such as like Apache Zookeeper or etcd. And so then what happens is that you use f+1 replicas for the bulk of your data, so that you save on costs. And you use two f+1 replicas to store very little information about just the configuration of your system, like what its members are. More formally speaking, the data part of the system is essentially asynchronous, and it uses the configuration service as a reliable oracle. And then the oracle, that needs two f+1 replicas, and of course it also needs synchrony assumptions to be implemented because it solves consensus. So there have been a couple of papers on this. The first paper that proposed this was Rambo from Disk 2002, and then there was Vertical Paxos from Potsi 2009, but there hasn't been a ton of work on this approach in the theory community. So Paxos-like implementations over 2f+1 replicas, they are well understood both in theory and in practice. So in industry, I think there is no problem nowadays in how to do like a correct Paxos implementation. But the vertical implementations have been much less studied. So the vertical Paxos, which is a very well-known paper, considers only single-shot consensus. It doesn't consider atomic broadcast. And of course, you can do atomic broadcast out of consensus black box, but it's not efficient, and there is no direct implementation written down anywhere. And this approach is widely used in practice because it saves you money, but there are actually lots of bugs. So to give just one example, so Kafka, which is a very well-known streaming platform that uses vertical approach, and for years it had a broken replication protocol, like completely broken. And so in this paper, we try to fill in some gaps and do a theoretical study of these kinds of vertical atomic broadcast protocols. So we consider a formalization of a reconfigurable version of atomic broadcast, which is what you need for active replication. So this reconfigurable means that you can change the membership of the system dynamically. And then we propose what we call a vertical atomic broadcast protocol. So this is an implementation of this reconfigurable atomic broadcast according to the vertical approach. So that means f+1 replicas for the actual data and the configuration service on the side. This protocol has been rigorously proved correct, so it can serve as a blueprint for future vertical systems. And it has nice performance properties. So as I'll explain, it is tight on the downtime during reconfiguration. And we also consider the generalization of both the broadcast concept and the implementation to passive replication, which is an alternative way of implementing state replication. So I said a couple of maybe unfamiliar words, so downtime and passive replication. So in the rest of the talk, I'll elaborate on these and also describe our contributions. Okay, so let's start with the downtime. The issue is that often you use reconfiguration not just to deal with failures, to remove like failed processes, but also on a purely functional configuration that generally works all right. And the reason why you may do this are things like upgrades. You may need to remove a replica to upgrade its software, or you may be load balancing among a larger fleet of servers because you may have multiple instances of your system running across like a fleet of servers and need to move stuff around sometimes. And in this case, it's kind of annoying when the system is unavailable during the reconfiguration, and that's what we call downtime. When if a user submits a request to the system, this request will have to wait until the system reconfigures, and so the latency of this request increases. Okay, and so let me explain why this happens, why you always get downtime with the classical reconfiguration approach. So in the classical approach, like say vertical paxes, if you want to reconfigure a system, say there's usually a process who's trying to perform a reconfiguration, then it's going to do the following steps. So first it's going to stop the current configuration and retrieve its state, right? So because it's stopped, it can actually look at what its state is, and this is going to be the final state of this configuration. Then it's going to go to the configuration service and create the next configuration there, say what kind of changes it wants to make. And that may involve, for example, removing one replica and putting another one in its place. And then once it's done, and so that requires solving consensus, because that's what the reconfiguration service does, then the process that performs all this will start the new configuration with the final state of the previous configuration, and it will go on processing requests. Of course, you may have several processes trying to reconfigure the system concurrently, so that's why you need the configuration service to ensure that only one of them succeeds. So in principle, the operation you perform on the configuration service is a CAS. Now, the problem here is that between the steps 1 and 3, the system is unavailable, and so that's where the downtime comes from. So here's the idea we use to minimize downtime. So we use atomic broadcast, like in a classical sense. Usually, like all these protocols use a leader, like Paxos, for example, right? And the leader in the reconfiguration setting is determined by the current configuration. So the current configuration says what the membership is and who the leader is. And the other followers other processes are followers. So they just record the decisions taken by the leader. And so what we'll do is, we're in a vertical setting, so if I want to execute a command, I need to persist it on all the replicas in the system. So a broadcast, atomic broadcast that I'm using can only deliver a command to this application that I'm replicating only after all the replicas recorded. That means that all the replicas, each of the replicas knows about all the commands that could have been executed. And so what we'll do in reconfiguration is to select a new leader from one of the members of the last operational configuration, and then this process will know about all previously executed commands. So let me elaborate a bit. So here the reconfiguration steps are going to be as follows. If I have a process who wants to reconfigure the system, then what it will do is it will go to the configuration service and start creating the next configuration there. And meanwhile, the commands keep getting processed. So for example, you may have a command C1 that was replicated everywhere, so it could be executed, and then a command C2 that maybe got replicated at a couple of replicas but hasn't finished replicating. And then when the configuration service solves consensus and says, okay, we have created the next configuration, here you go, then we'll send a message to the new leader, who's one of the processes from the previous configuration, and tell it, hey, you're the new leader. And we know that this guy will be aware about all the commands that could have been executed by the system. So in this case, it knows about C1. It doesn't know about C2, but that's all right, because C2 couldn't have been executed, because it hasn't been replicated everywhere. And so when the leader receives this message, it immediately knows what its starting state is. It will stop participating in the old configuration, so that will stop it, and immediately start participating in the new configuration. And so this period between stopping the previous configuration and starting the new one is what we call the downtime, and here it's 0, so kind of the best you can have. Okay, so this is a very simple idea. The implementation is a bit technical, and so there is a full protocol and proof in the paper. I just want to highlight a couple of challenges. I don't have time to go over this in detail, but one problem is that you may have uncompleted reconfiguration attempts by processes that failed, right? So there's one process that tries to do a reconfiguration, fails midway, then you need to spawn another one to try to do reconfiguration. And so it may be actually tricky to figure out what the last operational configuration is. We may also have multiple processes trying to reconfigure the system concurrently, and we need to ensure that they don't interfere with each other. And to achieve all this, we play some games with Paxos ballots, so you may want to check the paper if you're interested, but I won't have time to talk about this. Okay, and that's because I need to talk about our second contribution, which has to do with passive replication. Okay, so in active replication, every process executes every command, right? So you have these 3 commands, C1 to C3, then every replica executes them. That's suboptimal if the computation you need to do to execute a command is expensive, and it's just inapplicable if the computation is non-deterministic, because you may get different answers at different replicas. And so to deal with this, there is this alternative approach called passive replication. So in this case, commands are executed at a distinguished leader or primary process. So it can be the same leader process used by the underlying broadcast, like a Paxos-like implementation, but principle doesn't have to be, right? So this is all at the replication level. And then what this leader does is it executes commands and then replicates their effects to other replicas, right? And this can be done using, again, some black box broadcast, kind of like a version of atomic broadcast. Now, there is a trickiness here. So just to give an example, like if I have a command that says assign x to a random number, then the leader will execute it. Let's say the random number it generates is 42. So what it will do is it will replicate an effect to other replicas saying, please set x to 42. Right? And if I have an increment that was done in the state sigma equals 0, then the effect you're going to have is that you increment it to 1, so you'll tell the other replicas, please write 1 to x. And so the trickiness here is that actually if you use atomic broadcast to propagate these effects to other replicas, then this is not sufficient to get a linearizable service. And this was something that was observed by Junqueira and Serafini in DISC 2013, and they also proposed an alternative, a stronger primitive that is actually sufficient. So it's called primary order atomic broadcast. The problem is that in our setting, it would increase the downtime during reconfiguration, which is something I don't like, because you may have noticed from the first part of my talk. And so we can actually do better. And so in the paper, we show how to do this. So let me sketch what's going on here. First, let me explain why atomic broadcast is insufficient and what primary order atomic broadcast does to address this. So let's go back to our example with the increment. So the leader, it executes one command after the other. Let's say it may execute like 2 increments, and so this will move your state from 0 to 1 to 2, right? And then it will generate these updates, or first, assign x to 1, then assign x to 2. Now, each of these effects, it only makes sense in the context of the state where the leader generated it. It's useless to apply it to any other state. And so if you use just atomic broadcast to propagate these effects, then this may be violated, because atomic broadcast, what it can do is it can just reorder these effects, right? It has to ensure that the order at all replicas is the same, but there are no guarantees about what kind of order you get, right? And so in this case, if atomic broadcast delivers first the effect x equals 2, and then the effect x equals 1, then the final value of the counter will be 1 at replicas, which is incorrect. It should be 2, because I did 2 increments. And so the primary order broadcast, what it addresses it in 2 ways. First, it nominates the leader, so it tells the replication layer who the leader should be, and this becomes the part of the configuration. Now, of course, in the Paxos-like protocol, it's going to be the Paxos leader. And then it will also respect the order of leaders broadcast, right? Essentially just preserve the FIFO order. Now, this requirement is not very onerous. It's very easy to do. Unfortunately, there is another counterexample that is much more difficult to address. and that has to do with leader changes. So let's say we have a system, and the first process is the leader, so it tried to broadcast 3 commands. So they had to be replicated, so it computed the effects, sent these effects via the broadcast. And now let's say this leader fails, and then we say, oh, well, we should nominate another leader. So let's say this is the last process. Now, by this time, various processes in the system may have delivered different subsets of these commands. For example, the second process may deliver the effects of commands C1 and C2, and the third process may deliver only the command C1 for now. The question is, what is the starting state of the service that the third process should start from when it computes the effects of new commands, right? And it cannot just take the state, whatever state it had from the previous configuration, because it doesn't know the whole information, right? So here, it only knows about the command C1. If it now says, okay, I'm going to compute another, like somebody submitted a command C4, so I'm going to compute its effects, send it to broadcast, then suddenly C2 may get delivered from the previous configuration. Now, if you imagine that all these commands are increments, then what this will do is it will move your state from 0 to first 1, then you compute another increment, so 2, and then you get the effect of that old increment from the previous configuration, and the effect is assigned, state to 2, so you get 2 again. Now, that's wrong because I did 3 increments and I got 2 in the end. And so the leader cannot just start broadcasting straight away, because that's an incorrect result, contradicting linearizability. And so what the primary integrity property from that old disk paper says is that a process can only become the new leader after it delivers all commands broadcast in old configurations that are delivered by any process. So in this case, what this means is we have our command C1 that's been delivered by everybody, but we also have command C2 from the previous configuration that was also delivered by process 2. And so this new leader has to wait until it first delivers C2, and only then it can broadcast this new command C4. And so now if we, again, imagine that all these commands are increments, then the effect is going to be to increment the value of the counter from 1 to 2 to 3, so that you're going to get the correct result. Now, the problem is that in the implementation, delivering all these pending commands requires making sure that they're persisted at all replicas, and that requires recording the commands at all replicas, and that's downtime. So that's what we are trying to avoid. And so in the remaining 1 minute of my talk, I'll just try to give you the idea for minimizing the downtime. So the insight we exploit is that inside the broadcast implementation, we already have all the commands that could have been delivered, right? So all these pictures I've been showing you were at the replication layer. And now if we look inside our broadcast implementation, we do have access to this information because any process knows about all delivered commands. And so our broadcast extends the API so that the leader speculatively delivers all the command effects that it has. And this allows it to the replication layer to immediately start broadcasting because it knows what kind of state it should start from, and this leads to 0 downtime. Of course, it wouldn't work if we just speculatively delivered anything without any additional guarantees, because, in this case, what if I speculatively deliver C3? What if it just disappears? But fortunately, our broadcast is engineered so that it guarantees that if any of the commands broadcast by the leader are ever delivered, like the command C4, for example, then the previous commands that were speculatively delivered to this leader, like C3, they will also survive, so they will also be delivered by any process that knows about C4. And so in the paper, we present a full specification of the speculative broadcast. You need to be a bit careful to make sure that that it satisfies all the right properties. It's a bit of a delicate balance because it has to be strong enough to be usable as a black box to implement linearizable passive replication. But on the other hand, it has to be weak enough so that it could be implemented by tweaking our vertical atomic broadcast protocol and preserving the 0 downtime guarantee. And so I'll just leave the conclusion slide here because I'm a bit out of time, and I'll be happy to take questions.
Any questions?
How well do you understand your paper?
I can't really ask any questions, so please. think of some question. Yeah.
From my understanding, essentially the leader kind of enforces the order of undelivered or essentially delivered commands by including them in the causal history of the command.
There is an implicit notion of causality. Now, there is no explicit data about causality. It's not like you send a list of commands, but the protocol essentially ensures that some notion of causality is going to be preserved, including across configurations. So if there was something in the old configuration that survives, so the new leader should know about it, that before the leader does anything, it will have to, well, in the old broadcast, we have to deliver it. In our case, we have to speculatively deliver it. So it doesn't quite know if it's durable, but we prove that it's going to be all right in this case.
Yes, please.
Say downtime is minimized.
I mean, it's zero. Okay, so it's zero here, right? So there's no lower. Now, that said, terms and conditions apply. This is zero for our notion of downtime, right, which is from the stopping of the previous configuration to the starting of the new one. But after starting, like if you replaced some replicas, you would still need to say initialize them, so to transfer the state. In practice, may not be bad because you often maintain some warm replicas that sort of have receive updates best effort, right? So really, there will be some downtime. That's why I sort of use the in practice, right? That's why I use the word minimize. But this interval that we consider, which is from stopping to starting, that's zero, right? So can't do better. Well, you could just submit the, yeah, sure. This protocol essentially has pipelining, right? So what this does, all the speculative delivery, is you say, okay, I'm going to assume that what I have is correct, and I'm going to start immediately sending new commands, right? And I know that if what I had is incorrect, it's going to get lost or something, then everything I'm going to do is also going to get lost. So I'm not going to do anything strange. Yeah. So essentially, the protocol has that kind of pipelining in it.
Right. Let's thank the speaker again. Okay. Our next speaker is Ahmed Kazi from SIPSA Helmholtz, hopefully I pronounced this correctly, and Saarland University in Germany. Yeah, please take it away.
Thank you. So this is joint work with Fabian Frey, Rangelis, and Alexander Nolan are all here in the room. And I'm here to talk about content oblivious leader election on rings. So let's get started with the model that we're considering. So we're considering ring networks, those are just cycles of n nodes. We assume that every node has a unique identity. And now let's talk about how they exchange information. And if you have attended Aran's great workshop on Monday, then you already have a head start. But to get everyone up to speed, so in the standard setting, we can think about a node sending a message to its neighbor. And if you're on the receiving end of this, you receive a message, you read its content, and you learn something. This is information you learn. Now assumes that you figure out that there is an adversary on the link between you and your neighbors that corrupts every single message. So naturally, we're going to stop trusting the content of every message, and in fact, it would be pointless to even read the content of the message. However, the fact that this message exists still conveys some information, namely that your neighbor is still alive. So you consider every message as a pulse, really. It's just a sign of life. And this is why our model is pretty harsh, because we need to design algorithms that work regardless of the content of every message. This is what we call being content oblivious. And if you had some hope that we can maybe infer something from the timing information, unfortunately, this hope is also out of the window because we're working in the asynchronous setting. So where does the information then come from? It's not the content, it's not the timing. It seems that all that a node has is really whether a message exists on one of its two ports or not, and the order in which these messages arrive. So what can we achieve despite this noise? And it turns out, as the title of our paper spoils, we can elect a leader, even despite these circumstances. And more concretely, we get the following theorem. So if we get an oriented ring of n nodes with its unique IDs, there is a quiescently terminating content-oblivious algorithm of this message complexity that elects a leader. Let's unpack what this means. So what is an oriented ring? And we think of every node as having two ports. Let's call them the positive and the negative one. And we call the ring oriented if every positive port connects to a negative one. So what I have drawn here is an example of an unoriented ring because of these two positive ports facing one another. Now, if we relabel the ports correctly, this gives an oriented ring. So a terminating algorithm. So what this means is just every node at some point outputs something and stops computing. And in particular, in the case of leader election, we want one node to return leader and everyone else non-leader. Now, what does quiescently here mean? What we mean by quiescence here is that by the time the last node terminates, we require that no pulse is still being transmitted on the system. And the reason this is important is in the context of composing this with another algorithm. So usually we don't run leader election for the sake of running leader election. We want to still compose this with another algorithm. Let's say broadcast a message afterwards. And this usually isn't a problem in the standard setting where you can trust the content in the message, so you can tag every message with the algorithm that it comes from. However, in our setting, we cannot trust this content, so the pulses corresponding to these messages are identical. That's why we need quiescence. We need to run these algorithms sequentially. We cannot run two algorithms in parallel. So the message complexity we get is just it is proportional to the product of n and the largest ID in the network, and this is just a sum of the number of messages that are sent throughout the execution of the algorithm. So this is the case for oriented rings. What if the ring is unoriented? Well, we can turns out to also elect a leader and can also orient the ring. However, what we lose here is termination. Otherwise, this would have been theorem 1. Right? What we get instead here is what we call quiescent stabilization, which means that we at some point write to an internal register the right state for every node. So exactly one node identifies itself as a leader internally and labels its ports correctly. All right, so this is what we can do on top of the system, but this even has even further implications, especially when you consider the previous work on this by Sensor Hell, Cohen, Gillis, and Sila from POTC22, who consider exactly the same setting and design a compiler that basically is able to simulate any synchronous computation on a ring in the content oblivious setting, given that the network is two-edge connected. However, the catch there is that they assume that there is a pre-existing leader to orchestrate this communication, and they conjecture that this assumption cannot be removed. Well, our theorem 1 basically disproves this conjecture, specifically for the case of rings, which are the simplest example of two-edge connected networks. And even more, it shows that any non-trivial content oblivious communication on rings is doable by combining the two works together. Just we run the theorem 1 to elect a leader and then the compiler from their work. And then we get the following very powerful corollary that shows that any synchronous algorithm on rings can be simulated in a content oblivious way. All right, so this was the what. This is what we did. Let's answer the harder question, which is how. How do we elect a leader? And this would be a two-step process. Our first step is, let's forget about termination for a moment, and let's consider we're going to build a useful building blocks that we're going to use later. So first observation is that the fact that the ring is oriented defines a natural notion of a channel. Let's call it here the clockwise channel, which means if every node just sends pulses throughout its positive port and receives pulses from the negative one, then this gives us our channel. And what we're going to do here is design an algorithm that only uses this channel. We call it the NT election, non-terminating election algorithm. And what this algorithm has access to, what it can manipulate, is just the identity of a node, which we think of as a positive integer, and the number of pulses that have been received thus far. So what can we do given these two players? Well, what the algorithm does is just when the node wakes up, it activates the channel. In this case, it's a clockwise channel, sends a pulse, and then keeps forwarding any pulse that is received. This happens all the time, except for a single time, where the number of pulses exactly matches our current ID. In this case, we don't send any pulse, but otherwise we keep sending pulses. So this is how it looks like. In the beginning, every node sends a pulse. There are n pulses in the beginning of the network. These pulses keep going around. When a node receives a pulse, let's say this is the node with ID 7, 1 is not equal to 7, so this pulse is forwarded. This pulse eventually reaches the node with ID 2. It gets forwarded, and then at some point, this node with ID 2 will receive a pulse. This matches its own ID, so it will consume this pulse. All right. So what's interesting about this building block? So let's maybe have a look at how these variables, these two players, evolve through time. And in the beginning, the number of received messages is clearly 0. And at every event, this grows by 1. So this is just an identity function. It grows like this. And in this drawing, I assume that it intersects with the ID. Do we know that this happens? And this is actually this is precisely the first property, which I'm going to call here the intersection. And it says that this intersection does always happen at every node. And the reason is, let's call the network alive as long as there are pulses in the network. Because as long as there are pulses in the network, these pulses will be received by someone, and progress will be made towards this intersection. And so initially we have n pulses. Every node reaches this intersection event and consumes a pulse. So as long as some node hasn't seen the intersection yet, then this means that there's at least one pulse in the network that will keep moving around and make progress. The second property just relates the number of sent messages and received ones, and this is just a simple observation because in the beginning we send an initial pulse. This is one more than what we receive, and then when we see the intersection, these two quantities basically reconvene. And the number of sent pulses becomes equal to the ones that we have sent. What this basically says is that the node effectively behaves as a link after this intersection. All right, so now the third property establishes some order between all of these intersection events and says that the leader, the one with the largest ID, of course there is no leader yet, this is the intended leader, this is the node at which this event happens last. And to see this, let's assume this were in the case, meaning that let's assume that the leader sees this intersection while some other node didn't. Let's find the nearest such node, let's call that V. Now recall all of these nodes in between have sent and received exactly the same number of pulses, so they're practically edges, so we can ignore them. Now this node L cannot have received more than what V has sent, which is one more than what has received, which is at most its ID, which is strictly less than the largest ID. That's a contradiction. Now combining all of these three properties gives us the fourth one, which I'm going to call quiescence, which means that eventually every node will have sent and received exactly the same number of pulses, which is equal to ID max. Intuitively, what this means that eventually all nodes will learn what the largest ID is, right? Because they will reach, at this point where they reach ID max, and they will not receive any further pulses. Well, then what's the problem? If they learn what ID max is, why can't they just compare it to their own ID? If it matches, then they know there is a leader and terminate. And otherwise, they terminate as non-leaders. Well, those nodes don't have access to the black line up there. They don't know that they have reached. They don't know they have already learned what ID max is. This is what we know as global observers. So what can we do to fix this? This is a good time to recall that we only made use of one of the channels, the clockwise ones, and we have another channel to utilize. And now this is a hypothetical scenario that will show us, give us some intuition on what we can do with the other counterclockwise channel. And now we're going to abuse the fact that we're like external observers to imagine this algorithm that has the first step as basically what we have already done. It's just a run of the previous algorithm in the clockwise channel, just as before. And when it ends, which we can only detect as global observers, it starts another run in the anti-clockwise channel. What does this mean? Just as before, we wake up, we send a message over the negative port, and whenever we receive a message, we forward it, unless we see the intersection, and then we consume that pulse. Now, how does this look like visually? Well, it's just the same as before, except that now we have this event of the number of pulses received from both sides being equal. And this is what we can use to drive termination. When this happens, this is our signal to terminate, and at this point of time, we know that exactly one node has this point coinciding with its own ID. Precisely, that is the node that has the largest ID, and this is the one that will only terminate as a leader and everyone else as a non-leader. Right, but what we did here is not possible. This is what we did as global observers, so what can we do instead? Well, this suggests that we can shift basically the two runs. Maybe so what we did here is a bit extreme. We shifted the two runs all the way apart, but it is actually sufficient to just start the second run a little bit behind, and more precisely, can start it at the first intersection event. When the current node sees its own ID in the clockwise number of received clockwise pulses, we can start the second run. And we claim that this is a final algorithm. So how does this look like visually? Well, the first stage is just as before. This number of received pulses keeps growing until the intersection event, and at that point, the anti-clockwise channel is activated, and we start receiving and sending pulses in this direction. And what happens here, or what we're expecting to happen, is that we're going to keep receiving pulses. These two quantities will grow, and eventually we're going to find this point that we're going to use to drive intersection at the end. Except that this may not be the case, right? It all depends on what happens in between. So imagine the case where these two quantities intersect earlier than this point. This will lead to an early termination for one of the nodes, which means that it will basically cut the network, right? This disturbs the communication in the channel, so this doesn't work. Fortunately, though, we can actually show that the number of received pulses in the anti-clockwise direction remains well below the ones received in the clockwise direction until the very end. And this is a simple argument. I'm not going to go through it in the interest of time, but feel free to ask me about it later. But it rules out any such bad event, and it says that what should happen is something that looks like this. The blue curve always remains below the red one, and they only meet in the end. And the remaining of the argument just goes through. All right, so what about the message complexity? We know by property 4 of the first algorithm that everyone sends and receives max ID. So this gives right away this complexity, which is unfortunately is dependent on the largest ID. So a natural question to ask is whether we can remove this dependency. Or in particular, can we get a polynomial message complexity or any function of n? Unfortunately, the answer is no, because we show a lower bound that has max ID. It has a dependency on max ID. And this uses a similar idea to a work by Diniz, Moran, and Reisbaum from Stock 1999. And I'm going to outline the proof sketch. First, this is the theorem that we get, that any terminating content-oblivious leader election algorithm sends this many messages. The idea is to run this algorithm in isolation. Basically, we isolate some node, give it ID, run the algorithm, and because the algorithm is terminating, we know that it has to terminate, concluding that it's the only leader there. We record this transcript, the input that it has seen as a binary string. We call that a solitude pattern. What we know about solitude patterns is they all have to be different, because otherwise we can just put two of them, two nodes together that have the same solitude patterns. They will behave similarly. They will eventually both terminate thinking they're leaders. So this doesn't work, which means that we have that many distinct solitude patterns. Accounting argument shows that we have at least n pattern sharing along prefix, and then with some help from Burns from the 1980s, who showed a lower bound in the message passing setting, we can combine both lower bounds and get our third lower bound. Okay, so this was the oriented case. Now, how about the unoriented case? Just to give some intuition, right? This is how we thought about the clockwise channel, is that every node sends, the rule for every node is to send messages only through its positive port and receive ones from the negative one. So let's look at how a pulse looks like. This one is sent from the first node, it's received the second one. This rule keeps going through, which means that the pulse completes a whole cycle. This defines a channel. If the ring is, however, unoriented, the following can happen. So this pulse goes through the first node and gets stuck at the second one. This doesn't fit the rule, right? You need to receive a pulse through your negative port. This node has a different understanding of what this clockwise channel is. So we need a different understanding, a different definition. If we want to complete a channel or compute anything, we need a different rule. And this rule would be just, if you receive something from a port, just forward it through the other one. In fact, in this case, we don't even need labels. So this lets us get this channel. And it means that even when we have unoriented rings, we have two channels that we can use. Right? So the high-level idea now is that we get two channels that we can now make use of our building block that we have introduced earlier. We can have two parallel runs of the non-terminating leader election, but with two different IDs. I'm not going to go through a lot of the details here, but the idea here now is that we have two channels. They're basically in a race, and the channel that receives more messages in the end is the one that declares itself as a clockwise channel. And in fact, with a very simple modification, we can get the leader election as well for free. All right. So now I will conclude with the main takeaways of this work. So we have shown how to elect a leader in a content-oblivious way in a ring using number of pulses that is proportional to n times the maximum ID. This was only the case for rings. So this begs the question: is what exactly happens in general two-edge connected networks? Can we even elect a leader there, or is it impossible? We suspect it's impossible, but we still haven't found the proof. We have shown that this leader election algorithm can be composed with a compiler from CCG S22 to achieve general content-oblivious computation in any asynchronous ring in a content-oblivious way. And finally, the lower bound also shows that we cannot remove the dependency on maximum ID. But this, again, begs the question whether we can raise this lower bound to match our upper bound. This, for sure, we believe. We believe that the message complexity of our algorithm is tight, but we still need a proof. Besides this, we have another result in our papers that you can find by scanning this QR code, which is in the case of anonymous rings where we don't have IDs. If you don't care about termination, and if you're fine with being correct with only high probabilities, then you can still elect a leader in a non-terminating way. So that's all I wanted to say. Thanks for listening, and thanks to my co-authors. I'd be happy to take any questions.
Any questions? Yes, please.
So you assume that when you have the numbers, they are, it's also possible to find a leader, or?
So there has to be an order. They have to establish an order, even if they're not natural numbers. But we crucially make use of the fact that they are numbers because we need to compare them against the number of pulses that are received, which is a number. So if they cannot be mapped to numbers, let's say, they're strings. If there isn't a function that hashes them to a number and maintains orders, then I wouldn't see how it's possible. So okay, well, what you're saying is, if there are not numbers and if there isn't an order, this means that the IDs are not unique, and some of the arguments here rely on the IDs being unique. If two IDs are the same, some of the arguments don't work.
Real numbers, for example, are being
Offline in the interest of time, right? Okay. Yeah, let's send the speaker again. So our last talk is a brief announcement that will be presented by Mohsen Lissani. And the title is Configurable Heterogeneous Quorum Systems.
Right. Hello, everyone. I'm Mohsen Lissani from University of California, Santa Cruz. I did this work with my student, Xiao Li. I have 4 minutes to talk about this project. I invite you to read the paper. There are so many different things. In these 4 minutes, I try to just present the leave protocol. So I tell you how you can let a process leave a heterogeneous quorum system. And to do that, I just show you a few animation. I try to give just the intuition of the protocol with a few examples. So last year at DISC, actually, we defined heterogeneous quorum systems with the goal of bringing openness and heterogeneous trust into quorum systems. So here's an example of a heterogeneous quorum system. Each one of the processes can define their own quorums. So here's one quorum for process 1, 1, 2, 3, and here's another one. And as you see, in contrast to symmetric quorum systems or classical ones, here the quorums are not necessarily the same across different processes. I need to define a few properties of these quorums systems to be able to present the protocol and the conditions. So the first one is quorum intersection at a set O. So if we take the set O as 1, 3, 4 here, if you look at 2 quorums of any well-behaved processes, we want to have at least one node in the intersection of them in this set O. So in this case, the process 4 is in the intersection. The next property is availability inside a set O. So again, the same set 1, 3, 4. Availability requires that every one of the processes inside this set has a quorum that also falls in the set. So for example, 1 has 1, 3, 4, that does fall. 3 has 3, 4, that also falls in the set. And finally, 4 has 3, 4, that falls in this set. So the first 2 properties you might have heard in different forms. We have a new property that we realized we need in heterogeneous quorum systems. It's implicitly provided in symmetrical classical ones, but here we need it. This property, again, for the same set 1, 3, 4, states that if you look at any quorum of a well-behaved process, in this case, we are looking at quorum Q of process 3, then if there is a node inside this set, in this case, process 1, inside the set 1, 3, 4, then we want this process 1 to have a quorum that I call Q prime, such that all the well-behaved processes of Q prime fall inside Q. And that is the case here because process 2 is Byzantine here. And that was why we didn't specify any quorums for it, because it can't have any quorums, it can behave arbitrarily. So the well-behaved process of Q prime do fall inside Q. So if a quorum system has all these 3 properties together, we call that quorum system an out-leaved quorum system. Our reconfiguration protocols take a quorum system that is out-leaved and transform that quorum system into another out-leaved quorum system. It's a property that we preserve. So I need to introduce the notion of a blocking set. If I have a process with its quorums, a blocking set is a set that intersects with every one of the quorums of the process. In this case, you see the set of processes B has an intersection with all of them, so it's a blocking set. I'm going to use this important lemma for blocking set in the next slide. So we can quickly go over this. So if we have a set O and our quorum system is available for this set O, and we have a process inside O, by definition, there must be a quorum of this process inside O. And if you then consider any blocking set, that blocking set has to intersect every one of the quorums, including Q2. And that means that we have this fact that B intersects with O. So any blocking set will intersect with this set O that I have been talking about. All right, so here we're looking at the leaf protocol. Again, a very simple sketch. I'm trying to just communicate the local condition that we should have. This is my last slide. This is the condition that we should have, the local condition that we can check for P star to make sure that it's safe for P star to leave. So we're looking at two quorums, Q1 and Q2, and they have P star in their intersection. So if P star wants to leave, is it safe? Do we still have some other node in the intersection? So Q has quorum inclusion for O. By definition, that means that P star must have a quorum Q1 star inside Q1 and Q2 star inside Q2. The condition that we check for P star is this, that the intersection of any pair of its quorums, set minus P star himself, should be P star blocking. And we know that Q is available inside O. Immediately by the lemma that I presented in the previous slide, we have that the intersection of these Q1 star and Q2 star, set minus P star, intersects O. Right? That's immediately coming from that lemma. And that means that there is another process P2 star in O inside the intersection. So it's safe for P star to leave. I hope that you read the paper. That was just the intuition. A very simple condition that we can check locally, and we keep all the properties that I mentioned. So questions I will be glad to answer.
Maybe one quick, really quick question. No. Okay, so let's thank the speaker again. And that concludes our session.
computing. And the first paper to be presented is Quantum Byzantine Agreement Against Full Information Adversary by Longchen Li, Xiaoming San, Jiadong Zhu, and Longzheng is going to present the paper.
Okay, now let's get started. My name is Longchen Li, and thank you for the introduction. I'll be talking about Quantum Byzantine Agreement Against Full Information Adversary. And first of all, I'm from the quantum community, so if I say anything wrong about distributed computing, please correct me, okay? I'll start with the definition of Byzantine agreement. I know you guys are very familiar with the topic, even more familiar than me, but I'll still go through it to make sure we're on the same page. And there are n players. Each player holds input bit xi, and they want to agree on output bit y while tolerating at most T40 players. And there are 3 requirements. First, all these players have to output the same bit. Second, if all these players have the same input B, then their output should be B. And the third one is that all these players have to terminate with probability 1. And here's an example. If all these players initially start with 0, then after final round communication, they have to output 0. If they start with 1 instead, then they should output 1. And if they initially start with different input, then outputting either 0 or 1 is okay, but they have to agree on the same output. So we model the 40 players' behavior by an adversary, which we assume is adaptive and computationally unbounded. Even under these assumptions, there are still many types of adversary model. We characterize them by 2 dimensions. The first dimension is knowledge adversary. The weakest adversary model we can have is what we call private channel model. In this model, honest players will have private communication links and private memory. The strongest model we can have is full information model. In this model, adversary basically know everything, including messages and the local variables. And the second dimension is type of fault. The weakest fault is fail stop fault. In such case, 40 players only stop participating in the protocol, that is, they crash. And the strongest type of fault is the Byzantine fault. 40 players will behave maliciously, and they can arbitrarily deviate from the protocol. Now, our network model, we assume players will have pairwise communication links, so the network is fully connected. And we consider 2 network models, synchronous and asynchronous. The difference is that in the synchronous network, message delay are bounded by some non-bound, and in the asynchronous network, message delay can be arbitrary. And we care about 3 parameters that measure the performance of a Byzantine agreement protocol. The first one is resilience, the second one is round complexity, and finally, the communication complexity. And round complexity is the most important one. As we will see, we can get quantum advantage on the round complexity. In this talk, we mainly care about Byzantine agreement in the full information model. Here, this table surveys some of the classical results on the round complexity of full information Byzantine agreement. So in the synchronous model, it's proven that classical randomized algorithm require at least quadratic round to solve this problem. And in the asynchronous network model, the problem is more difficult. The lower bound increased to linear. And for a long time, at least exponential rounds are needed to reach linear resilience against the Byzantine adversary. And it was recently improved to polynomial rounds. So as a guy from quantum community, we are mainly care about this question, can quantum help this problem? So before I answer this question, let me first briefly introduce what is quantum computation. And in the classical world, we compute with classical bits, that is 0 or 1. And in the quantum world, we can have something between them. The basic computing unit of a quantum computation is quantum bit or qubit, which can be represented by a 2-dimensional unit vector, alpha, beta, where alpha is the amplitude of 0 and beta is the amplitude of 1. And classical computation is basically mapping bit strings to bit strings. And in the quantum computation, since we are working with vectors, we need matrix. And computing on a quantum state is basically multiplying the state vector with a unitary matrix. And one final thing, when we have a quantum state, we cannot access those amplitude directly. So in order to extract classical information from the quantum state, we need to measure the state. In particular, measure a state alpha 0 plus beta 1. The state will collapse to 0 or 1 randomly, and we will obtain 0 with probability alpha square, and obtain 1 with probability beta square. That's the basics of quantum computation. now we introduce a quantum network model. In the quantum network, each player will be a quantum computer, so they can do quantum computation. And the communication links between them are replaced with quantum communication links. So they can send qubits to each other instead of just classical bits. And finally, I have to remark that in the quantum setting, a full information quantum adversary knows every quantum states in this system. In the more formal terminology, it knows the pure state of the entire system. That's a network model. Now back to our question, can quantum communication speed up full information business agreements? In the seminal work by Benner and Hastim in 2005, the answer is yes. Their results are mainly in the synchronous network model. Recall that in this network model, classical protocols require at least quadratic round to solve the problem. And surprisingly, they give 2 constant round quantum protocols, and thus achieving quantum speedups. So how did they do this? From very high level, their quantum protocols are inspired by some classical protocols in the private channel model. So first, they take a constant round classical protocol in the private channel model, and then they do some quantum modification to it to avoid the use of private channel. Moreover, such modification will not affect the round complexity. Thus, we get a constant round quantum protocol that works in the full information model. So their techniques seem quite ad hoc and only applies to specific protocols. So we are wondering, can we generate the results to more settings, such as asynchronous network? Okay, so we asked the following question. Can we convert any classical private channel business agreement protocol to a quantum full information business agreement protocol while preserving important parameters like resilience, round complexity, and communication complexity? The motivation is that in the private channel model, players are stronger, so it's possible that we design better protocols. And if we can lift those protocols to the quantum full information model with quantum power and without sacrificing the performance, then we can get quantum advantage in the full information model. So what Benner and Hastim show is basically for some specific protocols there, this direction holds. So our main result is showing that actually for a very large class of private channel protocols, this direction holds. And that's our theorem 1, our main theorem. For various models, include synchronous, asynchronous, Felsdorf fault, Byzantine fault, any classical private channel business agreement protocol will imply a quantum full information business agreement protocol with the same resilience, round complexity, and communication complexity, as long as the protocol is non-erasing. So what is non-erasing? Informally, a business agreement protocol is non-erasing if its correctness does not rely on the erasure of intermediate states. In other words, if all honest players save their computing history in the local memory, it will not affect the correctness of the protocol. So how strong is the assumption? Actually, it's a very mild assumption. All the existing protocols we care about, that is protocols with probability 1 and has no cryptography assumptions, all satisfy this property. And there are indeed some other BA protocol which violate this property, but there is a cryptographic or they only succeed with high probability. Now, we can apply our theorem to the best existing private channel protocols and we can get quantum advantages. So our theorem first directly implies all the previous results Benner and Hastim. And in addition, we get 2 new quantum advantages in the asynchronous model. And the first one is a constant round optimal resilience protocol against Felsdorf adversary. The second one is a protocol against the Byzantine adversary, and it takes a parameter epsilon. When epsilon is a very small constant, it basically runs linear round and reach near optimal resilience. And it surpasses the classical lower bound, so we have quantum speedups. And when epsilon is roughly 1 over n, in this case, we reach optimal resilience. But in this case, our quantum protocol also need linear rounds, which does not surpass the classical lower bound. But in the same setting, the best classical algorithms require n to the 12 rounds. So we are still much better than existing classical protocols. Finally, let's talk a little bit about our techniques. So from very high level, I explain a very high level intuition of why quantum help in such setting. So in the private channel model, players have private communication links and private memory, so they can flip private coins. And if a protocol in this setting relies on the privacy of coins, then it will fail in the full information setting, because in this case, a full information adversary can see the coin values right after it's flipped. And however, with quantum computation, we can roughly create the effect of having private coins even in the full information model. How do we achieve this? First, instead of flipping classical coins, we prepare them in quantum superposition states. Note that if we measure the state, it will collapse to random classical coins. But we don't measure yet. We first perform quantum computation directly on those states, and we defer the measurement to the end of the protocol. And this will roughly create the effect of having private coins, because even the full information adversary cannot predict the future measurement outcomes. That's the high-level intuition. Sorry, how much time do I have? Okay. Okay, now we formalize this idea a little bit, and we can get the proof for our theorem. And I already sketched the proof in the synchronous model. Now we have to prove that given the classical protocol, which is non-erasing and needs private channel, we have to we denote it by PC, and we want to construct a quantum protocol PQ that works in the full information model. So without loss of generality, we assume PC has this form in the left-hand side. On the round K, player I first receives messages from the last round, then the sample classical randomness, then a value function which will output MK, BK, and DK, where MK is the message content it's about to send, BK is the message pattern which will determine who is sent message to, and DK is the decided value. If it hasn't decided in this round, then it will be empty. And now we quantize it in the right-hand side. First, instead of sampling classical randomness, we prepare quantum superposition states according to the randomness probability of the randomness. And then instead of evaluate function, we compute a quantum unitary, which will save the output of F to a new empty register. Finally, we only measure the information that are necessary to keep this protocol running. That is BK and DK, because BK determines who I will send message to, and DK determines whether I will stop. The construction is quite straightforward. And now we need to, sorry, I have one more comment. In the quantum protocol, it's necessary to keep the intermediate state S in the local memory to make this computation reversible and to avoid the collapse of the quantum superposition. To resemble its quantum counterpart, we also assume PC save the intermediate state S in its local memory. That will not affect the correctness of PC because that's exactly the definition of non-erasing property. So that's where we use non-erasing in our construction. Now we need to prove that our construction of PQ is indeed a protocol against quantum full information adversary, which is directly implied by the following lemma. So given any quantum full information adversary AQ attacking PQ, we can construct a classical private channel adversary AC attacking a perfect simulated AQ. So if we can attack PQ, we can attack PC. That's basically a simulation proof in cryptography. How is that simulation possible? We will face two barriers. The first barrier is that AQ is full information, but AC has limited knowledge. The second barrier is that AQ is quantum, but AC is classical. So I'll give the intuitions of how to overcome those barriers. For the first barrier, it's kind of easy because in our quantum protocol, the only classical information revealed is BK and DK, which we can safely assume is also available to a private channel adversary. And everything else remains in the quantum state, so actually AQ doesn't know more than AC. The second barrier is more tricky, that is AQ can do quantum computation. For the fail-stop case, let's think of what a quantum fail-stop adversary can do. It can only stop players and filter its messages, but those actions has nothing to do with quantum, so AC can easily simulate those actions. For the Byzantine case, AQ can really do quantum computation. This time, we let AC to classically simulate AQ's quantum computation, since AC is computationally unbounded, so it's okay. But there are some other problems we have to handle, such as in the classical network, we can send quantum messages. And in such simulation, the adaptive corruption also become a problem. And those problems requires more careful handling. And for more details, please refer to our paper. In summary, we provide a general approach of constructing quantum full information Byzantine agreement from classical private channel Byzantine agreement. And by our approach, we get 2 new asynchronous quantum Byzantine protocols, achieving quantum speedups. So there's one topic not covered. That is, our theorem does not preserve the local computation complexity, but it is possible to avoid the blow-up local computation when designing specific protocols. And some open problems, we are interested in under what condition will the reverse of our reduction hold. That is, what kind of quantum full information Byzantine agreement will imply a classical private channel Byzantine agreement with the same parameters. The second one is to apply our technique to other problems. So that's all. And by the way, I'm looking for PhD positions next year. I know maybe it's not the right community to advertise myself, but anyway, if you are interested in my work, please talk to me. Thank you. Any questions?
Questions?
First, thanks for a very nice talk. So I had a question. So you said that, for instance, Kingensea's approach is not, it cannot be translated through your approach, like through your generic kind of translator. Is that correct? Did I understand that correctly? Because they only have this kind of history property that holds only with high probability. Is that correct?
Yeah, but it's because they erase something.
So my question is, like, could you, I mean, can you adapt your emulation specifically for, can you make it work for specific protocols?
I guess we can do some adaptation to make it work.
Mm-hmm.
Yeah, but currently I don't know how to do it.
Okay.
Yeah.
Which part of the emulation that you make is specific for Byzantine agreement, or does this work for anything Byzantine?
Actually, this construction works for everything, but the non-trivial part is to prove that it works for Byzantine case.
I see. You're saying it could potentially work for any other Byzantine.
Other Byzantine.
Yeah, like I guess which part of the construction is specific only to Byzantine agreement?
Oh, only for Byzantine agreement?
Yeah. Agreement. Yeah.
Okay.
Yeah. Like let's say it's some other problem, not agreement. Can you still use the same thing to get like?
I guess with some adaptation we can tackle other problems, but this construction is specifically for Byzantine agreement.
I see.
Yeah.
Just to understand, so this non-erasing property, is it it's like more like memoryless or oblivious protocols? Like you don't depend.
Sorry, the non-erasing property.
Non-erasing, yeah. Can you explain what it is again?
Okay. It means that if honest player save its computing history in local memory, it's okay. It does not affect the correctness.
It's like you don't maintain a memory of the history of the
yeah. I can not. It's okay to not maintain, but maintaining is okay. I want to say this.
I see. Yeah. Okay. Okay. Well, thank you very much.
Oh, thank you.
So the next talk is Byzantine Resilient Distributed Computing on External Data by John Augustine, Jeffin Bijou, Sashar Meir, David Pelik, Shrikant Ramachandran, and Aishara Tiruvengadam. And and Sashar is going to present the talk.
Okay, so hey everyone, my name is Shachar, and I'm going to talk about Byzantine resilient computing on external data. So I'm going to start. By talking about the motivation. Then I'll proceed to explain the model, and then if we get to it, I'll explain some results. Talk about conclusions and future work. So let's start with the motivation. So consider the following story. Let's say that Alice and Bob want to have a bet on a soccer match. So they create a smart contract to do that. Alice bets 20 Ethereum on Barcelona. Bob bets 20 Ethereum on Madrid. The smart contract gets the bets, stores the money, checks the result, and then because we're in Madrid, Madrid wins and Bob gets the 40 Ethereum. But that's not so easy. So for a smart contract to get information outside of the blockchain, it needs to use something called a blockchain oracle. So this is the general structure of a blockchain oracle. On the left side, you see a smart contract that's on the blockchain. On the right side, there's an oracle network that's connected to that data source. The way that it generally works is that every node in the oracle network reads data from the data source. Then they aggregate it into a single aggregator. Sometimes it's multiple aggregators, but for this example, one is fine. Then the aggregator creates a report, uses sometimes quorum certifications, and then it passes it onto the smart contract to be verified, and then the smart contract can publish a final value to the blockchain. So previous research focused on that second part of how to generate reports and verify them. But our research focuses on the first part. So how do we get data from the data source? And the question is, how do we increase collaboration? So in the example that you just saw, every node reads the entire data independently of any other node, which is kind of wasteful. So we introduced the data retrieval model. So the model is comprised of two parts. There's a congested click, which is like a peer-to-peer network. And there's the trusted read-only data source that stores like an array of n bits. So let me talk about the network assumptions. So we assume that we have k peers with IDs from 1 to k, up to beta k of them may be Byzantine. The message size is O of log n, so it's a congested click. The data source stores an array of n bits, which is static. So usually in the context of blockchain oracles, data can change over time, but we assume that the data stays the same. It could be financial data or something like that. And we assume lockstep synchrony. So the way that it works in our model, the round is works like that, like this, like the following. So first, in the beginning of a round, the network can send a query to the data source. For example, give me the value at the ith cell. The data source then responds with the appropriate value. Then the nodes perform local computations and send messages, and that's like one round. So the messages arrive before the next round. So queries once per round at the beginning of the round. Any number of bits can be queried at the same time, and getting them back also in the same round. And the main complexity measure that we are looking at is the number of bits queried by any peer. So the reason for that is we assume that queries are more expensive than messages between peers. Justification for that can be that talking with external APIs is much more costly than sending messages between two machines like in AWS or something like that. So continuing the formalization, we introduced retrieval problems in our data retrieval model. So given a PR network, every peer must learn f of x, where f is some computable function of the input x. X is like the bit vector of the data source. So we focus on specific problems. The first one is download, which is like f is the identity function, so we need to learn the entire input. And the other problem that we study is disjunction, where every peer needs to know just the logical OR of the vector bits. I'll be talking about download in this talk, but you can check out the full version to see results on disjunction. So let's start with the results. So when there are no failures, you would expect the query per machine to be n over k. That's because like every peer can read n over k bits, transmit it to every other peer, and then everyone knows everything. But is it achievable under Byzantine faults? So deterministically, no. Solving deterministic download requires at least beta n queries per machine. So let's look at the proof for that. So you can assume there's a protocol and input that can query a single bit, a single index, at most f equals beta k times during a failure-free execution epsilon of the protocol on x. So this is x, and we can build a dual vector of x to be x prime, where it's the same as x, but we just switch the ith value from 1 to 0. So we can consider epsilon prime to be the execution where the adversary corrupts every machine or peer that tries to access the ith value, and then it makes it behave as if they queried x. So for that reason, every honest peer can distinguish between epsilon and epsilon prime when deciding on the value of I, hence leading to contradiction. We have this lower bound. We also have like a matching upper bound when there's a majority of Byzantine peers, honest peers. So first, like the protocol is first, you can assign bit indices to peers such that every bit is read by 2f plus 1 peers. Then every peer can query his assigned bits and send the values to every other peer. And finally, since every bit is read by a majority of honest peers, taking the value of the majority results in the correct value. This is a simple algorithm, but let's proceed to a more interesting protocol, which is a randomized result. So the randomized result is, you can see the complexity is n log n over gamma k plus square root of n, where gamma k is the inverse of beta, so it's like the honest fraction of peers. So to do that, we use like probabilistic approach. So every peer enters a committee with this probability. Then every peer in the committee queries I and sends the value to every other peer. If there's at least row votes for both 0 and 1, the peers that queried I, the peer queries I, and then he blacklists the ones that voted incorrectly. The reason for that is we can show that there's in the committee there's at least row honest peers, which then means that the committee will have at least row votes for the correct value. And otherwise, the peer can choose the value that has at least row votes. So in terms of analysis of this protocol, it can be shown with high probability. I'll spare you the details, but we can show that with high probability, every committee has at least row honest members. Every honest peer joins at most this amount of committees. And every time a blacklist happens, which incurs a query to happen, there are at least row Byzantine peers that are identified. And so we can do it at most beta k over row times. So if you do the math, and I'll spare you with the math, but the amount of times that a peer queries is the amount of committees that he participates in and the amount of times he blacklists. So it's like the addition of that. If you choose row appropriately, you get the bound from the theorem. Okay, so this is like a list of our results. There's a more interesting, like more sophisticated result, which I can't cover here, on download, which gets optimal or up to logarithmic factor optimal query complexity. And like you can see the results on disjunction. If you want to see more of that, you can check out the full version. To conclude, the traditional BFT model often faces limited resiliency. So you can see it in stuff like the FLP impossibility theorem for Byzantine reliable broadcast. Even when using cryptographic tools, often like the impossibility is when there's a majority of Byzantine nodes. There's also like a problem with connectivity. So in not like peer-to-peer networks, there's like a problem if there's a single node that becomes Byzantine and then it makes the network disconnected, and the honest nodes can't distinguish between a connected network or a not connected network with a Byzantine because of like the Byzantine node. So we propose a new model that separates the data from the nodes of the network and captures real-life applications, which allows improved resiliency up to beta at most 1. So final words. So future work can like be improving the complexity measures and resilience of these protocols. So it's lowering query complexity, focusing on time and messages, which I didn't cover, but we didn't try to optimize them. Improve resiliency, and so another line of work can be trying to change the information from static information to dynamic information that changes over time. That should be an interesting line of work because of the interesting applications in blockchain oracles and other lines of application, and trying to add services to the data source, like having it being able to provide global random bits, for example, is an interesting thought. And that's it. Thanks.
Okay, thank you. Questions? So you have a very cool model where like you instead of distributing the inputs are centralized, but it's hard to learn. But somehow I missed why you went to the click model, like this congest click model right away. Does it make sense to consider this model with other communication patterns?
Yeah. So the idea is to simulate blockchain oracles. It can be done like trying to do like a general graph of communication, but it's easier as a first step to consider peer-to-peer networks.
Because we feel more comfortable with congest. Yes.
So, I mean, it seems pretty central that you're assuming that the message communication is less expensive than the sort of storage access. Like, I mean, to what extent is this a problem that people have recognized in real deployed systems, and to what extent does this apply in a geo-distributed blockchain where I would imagine also messages are expensive?
Well, so if you consider something like a financial API, financial services cost a lot of money. So there's usually just like a fee for use, and then there's a fee for queries, and the fees are very, very high. Like fees can be like up to $50 for like some amount of bits, and then there's a lot of financial information that you need to process. So that's like a lot more expensive than just sending messages over the network.
Okay, well, thank you very much. And with no break, we go to the next session on graphs, rumors, and clocks. And the first paper in the session is going to be on the power of graphical reconfigurable circuits. So this is the paper of Yuval Emek, Yuval Gil, and Noga Arlev, and Yuval Gil is going to give a talk.
Thank you. Yeah, so this is, so I'm currently a postdoc at Weizmann, but this is a work from my PhD, which is joint with Noga Arlev and our mutual PhD advisor, which is Yuval Emek. One second. Okay. Sorry. Okay. So we talk about graphical reconfigurable circuits. This is what we call, in short, GRC. And this is a notion that's kind of lifted from the Amebot model, geometric Amebot, by Feldman et al. They introduced this concept of reconfigurable circuits. So this is biologically motivated, as it abstracts long-range coordination in cell networks via electric signals, so they say. And this is actually became quite popular within this niche community. It's been followed up in various papers. And this is studied strictly in planarly embedded hexagonal grid as networks. And what we aim to do is to generalize this idea into just arbitrary graph networks. And okay, so this addresses networks that fall outside this strict regime, and also allows for the exploration of a richer class of problems. Okay, so I will present the model in two parts. First of all will be the communication part, which relies on this concept of reconfigurable circuits. These are the foundation. And then I will talk about the local computation as distributed graph algorithms do. These are the two components. So the algorithm advances in synchronous rounds, and we define pins as pairs from the set E cross K for some constant K to be determined by the algorithm designer. So for instance here, you have K equals 2. And in each round T, the set of pins is partitioned into what we call circuits. So notice that in each round, the circuit partition can change, hence reconfigurable circuits. Okay. So how do these circuits work? So each node V decides on a local partition that we call RT of V of its incident pins. For instance, you have the blue set, the green set, and the red set. And now we defined a binary relation LT of pins such that two pins relate if and only if there exists a node V such that P and P prime belong to the same part of the partition RTV. So notice that this relation is symmetric and reflexive, so it's very natural to take the transitive closure of this relation, and now we have what we call an equivalence relation. And okay, if we have an equivalence relation, it makes sense to look at equivalence classes, and this is what we call circuits. So circuits are determined by local decisions of the nodes. And why do we care about circuits? Because, as I said, these are the foundation for our communication. In particular, circuit serves as a beeping channel, and beep is just informational signals. So in each round, a node V beeps on a chosen subset of incident pins, and for each incident pin P, V is informed whether a beep occurred on its unique circuit. Okay, and this is what we call no collision detection, because V gets no information for pins on which it beeps, no additional information. So this is the communication of the network, and we also assume uniformity, which means that so each node is associated with a state machine, which is possibly randomized, and generally we will use randomization. And algorithms are required to be boundedly uniform, which means that nodes have no knowledge of global parameters. And the state space, as well as the description of the transition functions, will be bounded just as a function of local parameters, such as degree and maybe local inputs. Okay, so this is just the model, and now I want to kind of exemplify what we can do with this model with the example of the fundamental problem of minimum spanning trees. So the minimum spanning tree problem, we have edge weights, which are integral between 1 and big W. Each node knows the weights of its incident edges. And nodes are oblivious, as we assume uniformity, nodes are oblivious, for instance, to the value of large W. In particular, there's no leading zeros. And the objective is to compute an MST of the graph. So some useful tools. We have a log counter, which is a procedure that can run for theta log n with high probability. Why is this even special? So first of all, this is similar idea to the one used in Gilbert and Newport. And why is this good in this model? Because it allows us to count approximately up to log n despite the uniformity. We have a leader election procedure that elects a single node out of n candidates. This is done with high probability in order log n rounds. And we can do a message passing, which means exchanging 1-bit messages with our neighbors, and this takes a constant overhead. Okay, so these are like useful procedures. So what's the idea for MST construction? So we want to emulate the classic Borovka's algorithm in the GRC model. And notice that a certain obstacle that we face in this uniform model is that edge weights are not necessarily unique. We know that Borovka's algorithm works well with when the edge weights are unique, and we know that a lot of times we can assume it without loss of generality. This is not the case. The algorithm will operate in phases. In each phase, we have a partition of the nodes into clusters, and the reason that this model fits this kind of ideas very well is that we can have a designated circuit for each cluster. And each cluster is looking to merge with a neighboring cluster using a minimum weight outgoing edge. Okay, so phases work in 3 stages. The first is finding outgoing edges, the second is finding minimum weight outgoing edges, and the third will be selecting a single one. And we will focus on the third one, assuming that the first 2 we already accomplished. You have to trust me on that. So let's look at the third one, and suppose that we have the first 2. Suppose that each node knows which of its incident edges is a minimum weight outgoing edge, and we have this cluster. And without loss of generality, we can also assume that each node has at most 1 incident edge that is like a candidate. And the problem is that the cluster may have more than 1 minimum weight outgoing edge. Again, edge weights are not unique. And we need to, and our goal is to select a single one. So now you may ask, isn't it just a leader election? Can we just use simple, classic, good old leader election? And here's the problem. So if we just use within each cluster a leader election, we may have like a sequence of minimum weight outgoing edges of the same weight and create a cycle. So we need to be a little bit more careful. So what will be the idea? So the random bits for an edge will be jointly sampled by both of its endpoints, and we will use these bits. So if the edge is minimum weight outgoing edge for both of its clusters, we will use the same bits. Now if we sample C log n bits, this induces a total order with high probability. And how do we sample C log n bits? With the log counter. And so we can take the minimum, we would like to take the minimal edge with respect to the total order and select this one, and this will avoid the cycle formation. How do we take the minimal edge? So I'm not going to get into the specific, but you can compare bit to bit over the cluster circuit. Okay, so I didn't talk about all the details, but generally speaking, the GRC model admits a fast MST construction. So the runtime would be order of log n times log n plus w. And for instance, in contrast, we know that in Conjust, this is a hard problem, and you have like a lower bound of omega tilde of square root n plus d. And here, the long-range communication, despite being weak, it's quite advantageous. And now we have to ask, can we still, this is still like a congested model, can we still leverage these congestion barriers to get lower bounds, okay? So this is one of these questions that is answered right away because the next section is called lower bounds. So let's talk about two-party. Let's talk about two-party communication complexity. So in two-party communication complexity, Alice received a bit string X, Bob received a bit string Y, and they look to compute a joint function fxy. And the communication complexity of f is the number of bits required for any inputs. So a useful function in that regard is set disjointness. So in set disjointness, we look at x and y as a characteristic vector of subsets between 1 and L. And the disjointness is 1 if these sets are disjoint and 0 otherwise. And it's known that the communication complexity of disjointness on X and Y is omega of the length. This applies even if the parties have access to share randomness, and this is as hard as it gets, making it very useful for hardness result in various settings, for instance, congest. And we would like to use kind of this framework for lower bounds in the GRC model, and particularly we will look at what we call a static cut reduction from set disjointness. Set disjointness is not special in that regard, it's just for the sake of presentation. You can use any function that you like. So let's look at the framework of this reduction. So we want to show the hardness of a graph property pi. And the reduction structure is kind of defining this graph of two potatoes, like you have potato A and potato B, and you have a static AB cut of size Q, and edges within A are fully determined by X, edges within B are fully determined by Y, and the validity of the reduction is that the disjointness of X and Y is 1 if and only if GXY satisfies pi. This is the structure, and the idea is that Alice simulates the nodes of A, Bob simulates the nodes of B, and the idea is to show that they can simulate a GRC round by message exchange. And if they use B bits to simulate a single round, this implies that pi requires omega of L over B bits because they need to send omega of L bits in total. And we will focus on Alice's side, Bob's is analogous, and we will assume K is 1 just for simplicity. This also means that circuits are just sets of edges, so we can use edges and pins interchangeably, and this will make my life easier in speaking about it. Okay, so here's a naive approach. Let's look at Alice's side, and let's look at two cut edges, and we have these squiggly lines that suggest connection within Alice's side, and where you have the blue squiggly line and you have the red squiggly line. And what if Alice sends just a single bit that indicates if a bit went through E on her side? So this means that, for instance, if some node sent a bip on the blue squiggly line, then Alice sends 1, and no node sent a bit on the red line, then Alice sends 0. And now she gets this is a total of Q bits, and now she gets the message from Bob and updates whether or not, like for each node, whether or not it heard a beep on the circuit. So for instance, if Bob sent a 0 on the upper edge, then Alice can update all the nodes incident on the red circuit that they received no beeps. Now what is the problem? Well, here's the thing. The cut edges might be connected strictly through B. So in this case, Alice updated all the nodes incident on the red side, on the red line, has received no beeps. But they should have received a beep because there was a beep going from A to B to A. And okay, this is easily fixable, but there could be a beep going from A to B to A to B to A, and so on. So in particular, the simulation fails. Okay, this is the naive approach, it fails. Okay, so let's fix the naive approach. And the way that we do it is by having Alice assign names to the cut edges such that edges will be assigned the same name if and only if they connect through A. Okay? And now, for each cut edge, Alice will send its name and the naive approach bit. This is Q log Q bits of information, because name size could be order of log Q. And given Bob's message, Alice can get the full picture of the circuit partition of nodes in A and truthfully simulate A. Okay? So if you haven't been following like the last slide and a half, here's a picture to summarize it. Bit is no good, name plus bit is good, okay? And this construction leads to many lower bounds using existing reductions. For instance, there's a known three colorability reduction where L is equals omega of n squared, Q is equals order log n, and we can derive a bound of omega n squared over log n log n. Okay, so wrapping up, we have a new model for distributed graph algorithms, uniform computation. We have reconfigurable long-range channels formed via local decisions, admits fast MST construction. Also in the paper, we show a sparse spanner construction, which I'm not going to talk about, but feel free to ask me about it. Also some decision problems. We also have congestion-based lower bounds by adapting a framework of static cut reductions. And we also talk about in the paper that moving cut reductions, such as the Sarma et al., fail to transfer because they assume local communication and more tailored to the congest model. That's it. Thank you.
Questions? So how do you motivate this reconfigurable circuits in practice?
So I talked about it a little bit. In the Amebot model, they give like this bioelectric signaling type of motivation, and we kind of extend this motivation to the general graphs. Just kind of going for the most general possible. Yeah, that's it. So each machine has kind of a bounded space. This is implied by the uniformity, like the bounded uniformity. So they could have a large degree. This is a general graph. They could have a large degree, and then they have like more memory.
Okay, well, thank you very much. Okay, so the next talk is going to be given by Robin Vacus. It's entitled On the Limits of Information Spread by Memoryless Agents. This is joint work with Nicola Darkivio. And just to mention that Robin is a co-recipient of the best dissertation, POTSI dissertation award this year.
Thank you very much. And indeed, this is joint work with Niccolo Darcivio, who did a wonderful master thesis, so thank you to him. And I'm going to speak about information spread by memoryless agents. And don't worry, it's if you're tired, it will be, I hope, a very relaxing and easy talk to follow. So I will start the presentation by giving some biological motivation for our problem, also because I cannot resist having ants on the slides if I can. And I'm going to ask you to consider the task of cooperative transport. And cooperative transport is pretty common in nature, in social insects and ants in particular. And it happens when a group of individuals need to carry a very heavy load that none of the agents is strong enough to lift on its own. And then they need to cooperate in order to lift it collectively. And I claim that this seemingly very basic task requires to solve two underlying challenges that are very common and also very important in distributed computing. So the first of these challenges is to solve consensus, to reach consensus. And in the case of cooperative transport, it's because you need to align your forces in the same direction. If you imagine that a significant minority of the agents are pushing in a different direction, then the forces cancel each other and the load is slowed down. So you want to be good at cooperative transport, you need to be good at consensus. But unfortunately, this is not enough on its own, because of all the possible directions where you can push, they are not equally good. One of them is going to correspond maybe to a shortest path to the destination, which could be the nest. And in fact, there is empirical evidence that for some species of ants at least, most of the individuals in the group, they have no clue where to go. They might have like a good idea of where the nest is, but it's not the same thing as knowing a good path for the load. Maybe there are obstacles that you need to navigate. And the biologists, they also noticed that sometimes a knowledgeable individual will join the group, he found a good route, and he is able to guide the others to the nest. So the second problem that you need to be able to solve is one of information spread, where you need to get the information from an informed individual and propagate it to the population. And in the case of cooperative transport, you have very little to play with in terms of communication. Maybe the ants, they can only kind of feel the forces that are applied on the load, and they cannot communicate from one to one. So from a distributed computing perspective, we can ask ourselves like how easy it is to solve this problem with a weak communication. And so for that reason, we consider the following problem. We have a discrete time process where the agents, they have to choose in every round between two different opinions, 0 and 1. And these opinions, they could, for instance, represent the directions in which to push the load, but they could also represent any other kind of option that you have to pick from. And again, these two opinions are not equally good. One of them is better, and we call it the correct opinion. And in this talk, I'll assume that the correct opinion is initially known by a single agent, that is the source agent. And also we assume that at all times throughout the execution, the source adopts the correct opinion. So it's always going to passively support it somehow. And of course, the others, they have no clue at the beginning of the execution what is the correct opinion. So I was speaking about weak communication, and for that, we assume that in every round, the agents, they simultaneously receive some vector ST of I. And ST of I is just a vector of size L, where L is a parameter. And the elements in S, they are basically the opinion of one agent that have been randomly sampled in the population. Okay, so you can think of S as kind of a noisy snapshot of the configuration of the system at run T. Or alternatively, you could imagine that it's kind of a noisy estimation of what is currently the fraction of agents with opinion 1. Also, you could imagine that it's kind of, you feel the forces exerted on the load, but you cannot know exactly how many agents are pushing left and right. And then we are going to restrict attention to memoryless protocols, where in order to compute your next opinion, you have to only look at what sample you just received in the current round, and possibly the opinion that you had in the previous round. So this is a pretty strong restriction, in fact. For instance, it prevents you from estimating the tendency of the dynamics. By that, I mean that if the number of 1 in the population is increasing, you cannot know. You only know what is currently now. And in addition, we allow the protocol to be probabilistic, to be random. And of course, the goal is for all agents to eventually adopt the correct opinion and remain with it forever. So as a protocol designer, again, we have very little to play with. So maybe if you look at the problem for the first time, you want to do something simple. And since we have to reach consensus, maybe we can do majority rule. So for those who don't know, like here, an example with L equal to 3, I look at my samples and I adopt whatever opinion is in the majority. So indeed, with this approach, you would get consensus in just log n times with a high probability. But it's pretty bad at getting the correct opinion, especially when you start from a configuration where you have more agents with the wrong opinion. So in this case here, almost everybody is wrong, and the majority rule, you would need exponential time before you stumble across the correct opinion. So the question that we ask is it possible to have a self-stabilizing protocol? So here, self-stabilizing is a big word because our system is extremely simple. So I just mean, let's say, a protocol that might converge from any initial distribution of opinion 0 and 1 in the group. And in fact, perhaps surprisingly, yes, you can solve the problem with a protocol that's called the minority dynamics. It's pretty fascinating. It was introduced in Soda this year. And it's kind of the counterpart of the majority dynamics. So to run this rule, you just look at your samples, and you only consider the opinions that appear at least once. So here, in this sample, both 0 and 1 appear. And you take whatever is the minority. And instead, if only one opinion appears, like your sample is unanimous, then you adopt this opinion instead. So this protocol would be well defined also for more than 2 opinions, but here we are going to stick to the basic case. And when you look at it for the first time, maybe you have a hard time imagining what collective behavior is going to emerge from the rule. So the easiest thing you can do is to simulate it to see what happens. So here with the x-axis, you have the time, and the y-axis is the number of agents with opinion 1, which I assume is correct in that case. And this is for like 10,000 agents and L equal to 57, which is a pretty arbitrary value. And what you see is that basically the process seems that it doesn't have any pattern. It's very chaotic. But in a relatively small number of rounds, it's able to somehow converge to the correct opinion and get stuck with the correct opinion. So it seems that it solves the problem. But what you cannot see on this slide is that if I decrease L, for instance, I take L equal to 20, you would have to wait a very, very long time before you get the same behavior. So it would be chaotic as well, but you would not get convergence fast. And the big question is how large L has to be. And this is the main result in the paper I just mentioned. They show that if L is at least square root of n log n, then you would have polylogarithmic convergence times with a high probability. And now we are left with the following problem, is that they do not give any reason why square root of n log n is necessary. It's quite arbitrary, and basically this is just to make the analysis work. But it's very possible that with a smaller sample size, the minority dynamics would work. And beyond the minority dynamics, there might be other protocols that are efficient to propagate information and reach consensus that we do not know. So this is like the kind of the technical context of our work. And on the biological side, it's also very interesting to understand what are the minimal requirements to solve this problem, which is, I think, quite natural and quite important for biology. And here I want to stress that the model is not realistic in the sense that we know that ants, they have access to memory, and the minority dynamics is not something that you would see in nature, I mean, as far as I know. But it's still an interesting model to understand, because if we can show somehow that without memory, the problem becomes extremely difficult, algorithmically speaking, then it's a good argument to justify that biological entities, they would evolve memory at some point. So it's something that is hard to say if you always stay within the biology approach. Unfortunately, we are not able to answer this question completely, but we make a first step, say, in that direction. And our main result is that when L is bounded, if it's just a big O of 1, then basically you cannot have a protocol that solves the problem efficiently. And more precisely, for any epsilon, if you only have n to the 1 minus epsilon rounds, which is, of course, much more than log n, then your success probability will necessarily tend to 0. And how much time do I have? Sorry. Okay. So I'll try to sketch the proof quickly. I think it's a pretty simple proof. So just for the sake of simplicity, I will drop the dependency of the protocol on the previous opinion and on the number of agents. But the lower bound, it would hold also when the protocol can depend on these quantities. And if we make these assumptions, then the protocol is very easy to describe mathematically. It's just a function from the set of integers between 0 and L and the interval 0, 1. So the input of the protocol is how many samples did I receive in the current round. And the output is what's the probability that given that I will adopt opinion 1 in the next round. And if we want to understand how the process works, we want to look at how many agents have opinion round 1. Because since the agents, they are indistinguishable and they have no memory, this is enough to characterize the system completely. So we can compute the expectation of this value in the next round. And it's a very simple expression. Each term in this sum, it made up of the probability to see exactly k samples equal to 1, and then, and then what's the probability that I adopt 1 conditioning on getting this sample. So if I fix an arbitrary protocol, doesn't matter which one, you will see that this function of x here, it has some graph. And I claim that if you want to achieve consensus one day, you need to satisfy this boundary condition, because if you are in a situation where everybody thinks 0, you cannot have agents randomly adopting opinion 1. And the same on the other side. And just to get a little bit more insights, anytime the blue line is above the black line, it would mean that the protocol has a tendency to make the fraction of 1 increase, and conversely, when the blue line is below. And finally, when it's equal, then you have some fixed point where the protocol in expectation doesn't change. So just to see it a bit better, I removed the x to the function I just plot. So now it's just a flat line, and whenever this function f is positive, it means the bias is to increase, and vice versa. And to do the proof, we just distinguish between two cases. We look at how the function f looks like before its first root. So here is the case that it's positive, or non-negative at least. And then we are going to assume that the correct opinion is 0. So the configuration that the system wants to reach is on the far left, and we assume it starts on the far right. And then we use the hypothesis that L is small in a few ways. The first is that f is a polynomial which is a degree at most L. So it means that the green interval here must be large enough. And then we are also going to show that from the area outside of the green interval, there is a very small probability that you jump sufficiently close to consensus. And finally, within the green area, we can show that your convergence time will be smaller than one of a random walk, because you have a positive bias to the right, or at least a non-negative bias. And then it's kind of a slightly different trick when the function is negative before the first root, but with the same ingredients. So again, the interval is constant size for the same reason, and then you reverse the correct opinion. You make it that the correct opinion is 1. And again, you say that from within the blue area, it's difficult to jump in just one round. And again, you make a lower bound by just dominating the process by a random walk. And to conclude, some interesting open questions. The first one is, of course, there is still a huge gap between what I said of the minority dynamics and what our lower bound is. So I think our results, I'm pretty sure it's close to, I think it's pretty difficult to improve the lower bound. And in contrast, I think the upper bound is where there is a slack for improvement to reduce the gap. So if anyone has idea about how to analyze the minority dynamics, I'm interested. The second open problem is maybe a bit less interesting to me, but nevertheless can be technically challenging, is that there is a chance that this result can be generalized to constant memory protocols, but then you will need to handle a lot of new technical issues. And thank you for your attention.
Questions?
So why can't you converge to the wrong opinion?
With what?
With the minority dynamics.
Okay. Okay, so I'm going to put...
I mean, is it that the one that has the right opinion is forbidden to change it, or?
Yeah, exactly. So this is something I said in the setting, is that
Okay.
if you are the source, you do not run the protocol. Instead, you just always display the correct opinion.
Okay, I missed that. Thank you.
Okay,
Thank
so in fact, it would propagate to the others. Yeah. What? I think here we do not analyze any protocol. We just make a lower bound. So I guess maybe the lower bound would also work if the proof is allowed to change. But yeah.
Okay, thank you very much. Sorry. You took your time.
Does this result hold even in the asynchronous world? This minority dynamics, will it converge in an asynchronous world?
Okay, it's a good question. And no, in fact, I think it's a pretty artificial protocol in the sense that if you update the agents one by one randomly, then it will absolutely not work. You need synchronization because the success relies on the fact that sometimes you will reach some proportion of 1, such as everybody will see not unanimity, they will see a small minority, but they will all see the same minority. So they will all jump at the same time to the consensus.
I see.
In a synchronous setting, it doesn't work. So I don't think this is practical. It's like purely mathematical protocol, but still quite interesting.
In the biology case, then you have like continuous time, right? So
yeah, of course.
Do you think like this thing is actually what gets done in practice, or?
No, I'm pretty sure it's not. Okay. So, but it's like just a way to understand like algorithmically what is possible or not. But I don't think it's practical.
Thank you.
Okay, thank you very much. So the next talk is going to be given online. Yeah, this is a brief announcement which concludes today's program. Clock distribution with gradient TRIX by Christoph Lenzen. Sorry, Trix. Okay, sorry. Yeah, clock distribution with gradient tricks by Christoph Lenzen and Shreyas Srinivas. And Shreyas is going to give the talk. The microphone is disabled. Yeah, Shreyas, your microphone is disabled. At least it appears so. Okay.
Hi, I didn't record it. I thought you were supposed to play that. Sorry.
Yeah, just 1 second.
No worries, we have to talk. It's just being.
Hello all, I'm Shreyas and today I'm presenting a brief announcement on clock distribution with gradient tricks. This is joint work with Christoph Lenzen. Suppose we are given a D cross D grid of nodes in a plane. This can happen in, for example, a VLSI system where each node represents a clock island. And suppose each node has an imperfect local clock source. Our goal is then to provide synchronized clock pulses at each node. This means we need to provide a graph topology to connect the nodes and a protocol for delivering synchronized clocks. The goal is to minimize both local and global output clock skews, where skew represents the difference between the value of the output clocks at any instant. We would like our system to be resilient to a reasonable distribution of permanent faults, as well as resilient to total network failures in a transient manner by being self-stabilized. Intuitively, one might assume that a fully connected network offers all the resiliency one needs, and indeed there are algorithms by Lynch and Welch, as well as Shrikant and Tuve. However, although these networks provide optimal skews and are very fault tolerant, there's no conception of local skew in these networks, and they are impractically dense for the applications we have in mind. We could use a sparser grid and the GCS algorithm of Lenzen to synchronize clocks on top of it. The GCS algorithm asks us to adjust clocks gradually towards the midpoint of that of the neighbors for each node. This achieves optimal global and local clock skews, and this algorithm is also self-stabilizing. However, it is not even resilient to one Byzantine fault. We can bring back some fault tolerance at a local level by replicating all nodes by a clique and all edges by a biclique. And this, in addition to the previous results, also gives us fault tolerance up to 1 fault per clique. This was accomplished in 2019 by Bund et al. However, this network is also impractically dense for VLSI applications. There's another line of work called clock distribution, and in this work, in this line of work, the TRIX grid is the most recent. Here you assume that there's a row of nodes at the bottom of the network which are capable of generating well-synchronized pulses. And nodes in each subsequent layer receive copies of each pulse and then forward them according to a pulse forwarding rule. For example, in the TRIX grid, each node receives 3 copies of pulse and forwards on the second copy. This makes the system resilient to up to 1 fault per in-neighbor for each node. And we also get self-stabilization for free because as new and new pulses generated, faults from the older pulses are flushed out. And as you can see, this network is also sparsely connected. Thus, we have 2 key takeaways. One is the GCS provides optimal skews, but requires excessive replication to default tolerance. On the other hand, you have the TRIX distribution scheme, which has a sparsely connected network and achieves great fault tolerance, but has suboptimal skews. The question is, can we get the best of both worlds? Our answer is a qualified yes. We take the topology of the Trix grid, and instead of naive forwarding algorithm, we have a complex pulse forwarding scheme where each pulse is held back by a node and forwarded after a certain waiting time, which is determined by the GCS rule when multiple copies of the pulse arrive very close to each other, and jump to the median-ish rule when the pulses arrive, the copies of the pulse arrive far apart. This gives us very good fault tolerance properties. For reasonable random distribution of faults, we get only constant overhead on local skew, and self-stabilization is guaranteed by the direction of propagation scheme as in Trix. Now, this leaves some open questions. Can we achieve the same self-stabilizing and fault tolerance guarantees on a non-directional network? And can we handle more local faults while still maintaining the gradient property of GCS? And how does one even compute average case Qs? That's the end of my talk. Thanks a lot. I look forward to questions.
Thank you. Okay, so we have time for 1-2 questions. Quick. So after reading your paper, there is this probabilistic stochastic model of the adversary of failures. Why did you choose these particular probabilities, like 1 over square root of n?
So if you read the paper, you'll see that there's also a sort of worst case fault model where we assume that if there are at most f rows which contain localized faults, then you have some blow up of the skew. But in the kind of VLSI systems we are looking at, faults usually come from process errors and voltage fluctuations. And these kinds of transient and permanent faults are not necessarily worst case distributed. There's no adversary who's putting pin tribute checking this out. But the probability itself was chosen because we believe that's the best probability at which you can still get non-correlated faults. If you go for more than O of 1 upon square root of n, then you start getting correlated faults, and basically then there's no fault tolerance guarantee you can get out of it.
So to what extent is the algorithm something you could actually implement on a VLSI system? Like, this is a question from someone who's never implemented something.
That's a good question. So we haven't actually implemented this algorithm for this paper, but we already know how to implement some of the components that go into the algorithm itself. So for example, we know how to measure time differences in the fine tuning by using the TDC. We know how to compute the latest block that's arriving, the earliest block that's arriving, and so on. So I would say that this is fairly feasible to implement in a way that synchronizes these clock islands on modern systems of chip.
Thank you.
Okay, well, thank you very much. Let's thank the speaker and all the speakers of this of today's session. Okay, don't miss the banquet.
Another happy hour